Gaurav, Subodh has joined as an attendee. Can you just move him to a panelist?
Subodh is a panelist. He is not there.
He is there in the attendee list. I can see him.
In this case, we cannot upgrade him. He has
What?
joined using the this WebEx application.
He was not able to join using the application. He has joined as a browser through browser. So there is a join through browser.
Upgrade anyone as a panelist. Can we give him microphone permissions? Okay, upgrade it. I think. Microphone. So, hi Subodh, can you hear us?
I can hear you, but
Okay, thank you. So I think we can manage this way, maybe because we can only connect with you through the audio, because otherwise WebEx requires the application to be installed on the laptop if you need to be upgraded as a panelist. So we can start the session, I guess.
are you able to hear me? Hello?
Yes, Subodh. Yeah, we can hear you.
Oh, great. Finally. Okay, let me know when to begin. I'm sorry for the delay.
No
Good
problem.
morning to you all, and welcome to the third day of ICVGIP. And it's our pleasure to have Professor Subodh Kumar from IIT Delhi to chair the plenary talk of day 3. Thank you. Over to you, Professor Subodh.
Hi, good morning. It's my pleasure to introduce Jonathan Regan-Kelly. Jonathan is Yeshcha and Harold Edgerton Assistant Professor at MIT EECS and also Berkeley EECS. And if that's not enough top colleges, he also has an MIT PhD and a Stanford postdoc. He's an accomplished researcher. He this year received the SIGGRAPH Significant New Researcher Award. He also has received an SF Career Award, Intel Outstanding Researcher Award. He's been a finalist for technical Oscars. His work on OpenFab and Halide language were also featured in CACM research highlights. So, and the list goes on, right? I just need to stop at some point. Jonathan works in the graphics systems. And in this age of building layers and layers of abstractions to hide the lower levels, Jonathan wants to go in the opposite direction. He says, wait a minute, you need to look at the whole gamut if you really want performance, and that has opened lots of eyes. But I'll let Jonathan talk about his research rather than me talking about it. So, but I'm sure you'll enjoy his talk very much. Jonathan?
Thanks for the very kind introduction. It's good to be with you all. Let me see if I can get screen sharing going. All right, can you see my slides all right?
Yep.
Yes.
So, hi everybody. Thanks for having me and thanks for coming. I'm sorry I can't be with you all there in person or wherever you are all around the world. Hopefully one day in the future we can. But today I want to talk about some threads that have run through my research over the years. So most graphics and vision research focuses on developing new applications and algorithms. But I want to share some of my experience building systems for processing visual data. And I think this is a great area for systems research, and that systems are a great opportunity for graphics and vision researchers because visual data is central to most of the ways that we use computers today. So not just in the traditional places you think like games, movies, and cameras, but also in everything from robots and self-driving cars to mapping the world to 3D printing, science, and medicine. But as successful as it is, visual computing has an almost unlimited demand for more performance and efficiency. So in rendering, for example, even using the same GPU as a PC game, a movie frame is still 6 orders of magnitude from real time. On the internet, basically all the biggest data is visual. So by 2015, YouTube was already ingesting 400 hours of new video every minute. But even that's just a trickle in the sea of active cameras, from medical scanners to smartphones to gigapixel telescopes. And we're developing powerful techniques to analyze this data, but they're expensive. So running one state-of-the-art object detector can take a large GPU just to process sub-VGA resolution video in real time. And while hardware has been getting more efficient for deep learning, the models have been getting more expensive at an even faster rate. So you might have seen this graph a couple of years ago from OpenAI, tracking the amount of compute invested in training state-of-the-art models from 2012 to 2018. But I think it's terrifying. So that's a log scale of compute on the y-axis. So in 6 years from AlexNet to AlphaGo 0, there's been a 5 order of magnitude increase in compute for training. In the last 2 years, we've carried this even further with things like GPT-3. Now, in general purpose computing, building web apps and iPhone apps and things like that, I think a combination of new languages, libraries, and systems have driven programmer productivity through the roof over the past few decades. But the kinds of high performance implementations that visual computing problems need, I'd argue are harder than ever to build today. So for example, Photoshop wanted to add an algorithm that was published at SIGGRAPH about 10 years ago. It's pretty easy to describe in at most a couple hundred lines of code. But to get it into production, one of the best engineers at the company had to spend 3 months re-implementing and optimizing. And the end result here does the same exact computation, an order of magnitude faster, but it needs code that's at least an order of magnitude more complex. So my group's research is all about making this easier. So we build languages, systems, architectures, and algorithms for these kinds of problems in visual computing. And specifically, we've worked a lot on high performance image processing for computational photography and vision, 3D graphic systems from offline and real-time rendering to simulation and 3D printing, and most recently at the interface of machine learning and systems. And this includes both the application of machine learning to optimizing our systems and new programming systems that broaden where we can apply machine learning, especially for vision and graphics. And throughout this work, I'm going to show that the key challenge is to reorganize or restructure computations and data. That our ability to do that is deeply connected to the dependencies in a given problem. And then that to make progress, I think the key insight is often to use domain knowledge to define abstractions that structure the possible dependencies in organizations. And ultimately, I'm going to show that by changing how we build systems from applications all the way down to hardware using this kind of idea, we can enable radically simpler code and more efficient systems and hardware in the twilight of Moore's law. All right, so what determines the performance and efficiency of apps like I've been talking about? It often seems like performance optimization is about low-level hacks and tricks, but the big issues are actually really fundamental. But first, we can just do less work. Computation takes energy and time, so we can be faster and more efficient by just doing less. And second, we can do more things at once and exploit parallelism. Now, superficially, this seems easy. All these graphics and vision applications are enormously data parallel. It's actually the fact that we have millions of pixels, objects, and neurons that makes us care about performance in the first place. The real challenge is that these millions of data parallel computations aren't independent, so they have to be able to communicate with each other. But the same hardware trends that have pushed us from one to many cores have also made communication and data movement dominate the cost of computation. And by communication, I don't even mean over networks, I mean inside a computer and even inside each chip. It turns out that the simple physics of the way we build computers mean that storing and moving values is literally orders of magnitude more expensive than computing them in the first place. And as a result of that, locality, or moving data around as little as possible, is often the critical issue in modern systems. And because of this, it can often be most efficient to make some surprising trade-offs, like redundantly recomputing values that are used in multiple places instead of storing them and reloading them from memory. Now, given these factors, how can we understand the performance of a system? We usually think of it in terms of two layers. We have, the hardware of our computer and the program that we're running on it. But the key factors of locality, parallelism, and the amount of work depend heavily on how exactly the computation is mapped to the hardware. So a key message I want you to take away from this talk is that because of this, you should often think of the program actually as two separate concerns. What I'm going to call the algorithm, or the fundamental operations that need to be performed, and then the organization of their computation, including where and when those operations are performed and where their results are stored and loaded. Okay, so what do I actually mean by the organization of computation? Let's look at a simple example. In lots of applications, we can think of the fundamental computation as some kind of a data parallel pipeline. We have a graph of major stages or kernels, and we have data being produced and consumed by each stage. And these data can be anything: pixels in an image processing pipeline, triangles in a 3D renderer, finite elements in a simulation, or activations in a deep neural network. And the basic idea is the same. But now, how can we organize the computation in this pipeline? If we zoom in and just think about two stages, we're computing a whole bunch of values at each stage. So we wind up having lots of choices about where and when we compute and store each value. And one obvious thing we can do is perform the computation, what I'd call breadth first. So for each stage, we compute every value in that stage before moving on to the next. So in a 3D graphics pipeline, for example, this could be rasterizing every triangle before shading. It's trivially parallel. We have to have somewhere to keep all the intermediate results. So it requires storing them in a large memory. And we can immediately see that this throws away any potential locality between the two stages. Because by the time we get around to computing the second stage, all of its inputs have been stored far away. So we have to load them all back in to compute that next stage. With locality in mind, it seems like we want to interleave the computation of the individual items in each stage in more of a depth first order instead. So I've just interchanged the order of the two loops here, conceptually. So in the case of that 3D graphics pipeline, maybe we'd rasterize and immediately shade each triangle one at a time before moving on to the next. Now, if we eagerly feed values down the pipeline as soon as they're computed, then we can hope to keep them in small nearby memory like caches or registers where they're much cheaper to access. But importantly, to understand how we might do that, we need to break open the computations within each stage and look at the dependencies between them. The dependencies among different computations can overlap or be irregular. In 3D graphics, each piece of geometry might cover 0, 1, or 1,000,000 pixels, and it might collide with any other piece of geometry in a simulation. And the pattern of these dependencies, which you can think of in some sense as the sparsity structure of the whole computation, determines both the set of possible organizations. For example, we can't compute values before we've computed their inputs. And it also determines the impact that each organization has on parallelism and locality. So if we know the fine-grained dependencies, then we can choose to interleave smaller chunks of each stage instead of the whole thing or each individual item one at a time. So for each stage, we can only produce a small chunk of values before passing them down to compute the corresponding chunk of the next stage. And we can get better locality by making the chunks small, or more data parallelism by making them bigger. We can also change or break dependencies by recomputing values that are used in multiple places instead of storing them longer and reloading them from memory. So here we might split the computation of chunks across multiple CPU cores. This might mean, for example, splitting up rasterization based on what part of the screen a triangle covers to keep that example going. And then we have each core compute its own copy of any shared values, avoiding any communication or synchronization. So given a computation, these are some of the kinds of ways that we can reorganize it to be more efficient. But understanding all the dependencies and all of the possible organizations gets really non-trivial when we zoom out and consider the whole graph of millions of operations across every stage. If we want to do this systematically or automatically, how can we even begin to enumerate all the possible organizations? How can we know what organizations are going to be safe when it turns out, we know from compilers and programming language theory that precise dependence analysis on arbitrary programs is undecidable. Even if we know something's safe, how do we know whether it's going to be a good idea, given that the forces driving performance, like locality and the amount of work we do, are often in tension with each other? So people have tried to build auto-parallelizing compilers for decades, but finding the best choice among an arbitrary set of possible organizations for completely general programs, I think is probably just intractable. So today, it generally still has to be done by hand at huge cost by human experts. So looking back at the Adobe code I mentioned earlier, the optimized implementation does the exact same computation as the reference, it's just been organized differently. It was finding this organization that took 3 months of work. So using a traditional language, in this case C++, each organization globally restructured all the code, mashing together hundreds of loops in different ways. And because of stuff like this, not only is this kind of optimization painful and expensive to do once, it also breaks the modularity of the resulting components. So the unifying theme of my research is figuring out how to make systems that can effectively organize computation for high efficiency. And the key intellectual challenge is figuring out how to structure the dependencies in possible organizations for the specific characteristics of particular applications. So instead of trying to make sense of an arbitrary mess of fine-grained computations that could be potentially run in any order, I focus on using domain knowledge to abstract patterns in the dependency structure of important computations. And that makes it tractable to model, understand, and manipulate critical dependencies. And then defining a structured space of possible organizations is key to being able to describe, transform, and automatically optimize an implementation. Okay, so that's a kind of big picture philosophy. And in my group, we've used this approach in several different areas of visual computing and at several layers of the stack. And I first want to talk for a couple of minutes about how it drove our work over the last 10 years on the Halide language. So Halide's a programming language for dense, regular data parallel computations in things like image processing and deep learning. And it's built around the idea of explicitly decoupling an algorithm from the organization of its computation. So in Halide, one half of our program, what we call the algorithm, defines what values are computed for each pipeline stage and their dependencies, while the other half, which we call a schedule, defines a structured space of choices for where and when they're computed, how we want to organize the computation. And decoupling these things in that way makes it easy for a programmer to write and compose algorithms, since it strips out lots of unnecessary implementation details. It makes it easier for either a programmer or a compiler to specify and explore optimizations without changing the algorithm. And then it leaves the compiler to do the complex but deterministic work of generating code that implements the algorithm given a schedule. So to start out, algorithms are written in a declarative functional style. So once we strip out the concerns of scheduling, the algorithm is a series of simple functions from pixel coordinates to expressions giving the values of those coordinates. These functions have no side effects. They can be evaluated anywhere in an infinite domain, and the required region of each stage just gets inferred by the compiler. So the execution order and storage are unspecified. The points can be evaluated in any order within each stage. The results can be cached, duplicated, thrown away, or recomputed without changing the meaning of the computation. So the code looks like this for a simple two-stage pipeline, where here the first stage F is defined at any point x, y as a nonlinearity applied to the input. And then the function g at any point is a convolution of 3 points in F. And notice that there's no loops, bounds, or mutable memory buffers here. There's just a declarative specification of how to compute any point in any stage, including all the fine-grained dependencies between points in these different stages. All right, so the specific scope of this programming model is what lets us understand dependencies and have lots of flexibility in scheduling. The first, it only models functions over regular arrays or tensors. Second, it focuses on feed-forward pipelines. So this is a good fit for imaging and vision, but not for everything. It can express a limited form of recursion and iteration, but only finite countable loops. And that means that it's actually not Turing complete. Okay, so we have this nice constrained functional model for expressing imaging and array algorithms. Now, how can we organize it? What we did is create a new language as part of Halide that defines a structured space of key choices and can concisely describe most critical optimizations for this kind of code. So in Halide, a schedule breaks down the organization of computation in pipelines like this into two key decisions for each stage. The first, in what order should we compute its values? So remember, we're computing whole arrays for each function. So in what order should we compute the points within each array? Second, when should we compute pieces of its inputs, or what granularity? And this is the more unique piece. It defines the interleaving of evaluation between producers and consumers in the pipeline, which controls locality. So at a high level, this is the core model we use to describe the space of ways a computation can be organized. And different choices about the order within and across stages can describe all the types of organization I showed earlier and more. So composing these choices in different ways for different stages spans the space of trade-offs globally for a whole pipeline. Okay, so the scheduling model within each stage is pretty simple. So you can apply all the classic transformations on simple loop nests like splitting, reordering, tiling, vectorizing, that kind of stuff. But the way that we model global trade-offs, the interaction across stages, is, I think, the most fundamental and unique idea in Halide's design. We do that by controlling the granularity at which the storage and computation of each stage gets interleaved. So the granularity with which we interleave computation determines how soon you use values after you compute them. On this axis, fine-grained interleaving provides high temporal locality, quickly switching back and forth between computing and consuming values. While coarse-grained interleaving provides less locality, computing lots of values before using any of them. The storage granularity determines how long we hold on to values for potential reuse. On this axis, fine-grained storage only keeps values around for a short time before throwing them away. So that can cause redundant computation if they're needed again later. Well, coarse-grained storage keeps values around longer to capture more potential reuse. So using the kinds of organizations I showed at the beginning, breadth-first execution avoids any redundant work by interleaving the computation and storage at the coarsest granularity, but this sacrifices locality between the stages. And in our scheduling language, this interleaving choice is described by the simple code that you can see on the right here. Now, full depth-first fusion interleaves the storage and computation of two stages at very fine granularity and breaks the dependencies between shared values. This maximizes locality, but it potentially introduces lots of redundant work where the dependencies overlap. Then in this last corner, by setting the storage granularity of the coarsest level while interleaving the computation per pixel, we get what I call a sliding window pattern. So this has high locality and does no redundant work, quickly switching back and forth between computing and consuming values in the two stages. But doing it synchronizes the iteration of the two stages, which limits the available parallelism. Now things get interesting when we realize we can trade off along these axes from there. So tile level fusion trades off between locality and redundant computation, depending on the granularity of the tiles that we interleave. Or starting from the sliding window schedule, we can coarsen the compute interleaving to regain fine-grained parallelism within enlarged windows at the expense of some locality. We can regain coarse-grained parallelism by performing sliding windows within multiple parallel tiles, introducing redundant work on the tile boundaries. Or we can combine all these strategies to span the whole interior of the trade-off space. So even for a trivial two-stage pipeline, we can express a nearly infinite range of choices in how to organize the computation. And here's a little cartoon, which hopefully comes through on the screen, of what some of those actually look like running. So different strategies are going to be best depending on the exact algorithms that we're using, the structure of the surrounding pipeline, and how they interact with the underlying hardware. And the difference between them can be more than an order of magnitude in performance and efficiency, computing the same exact results. And that's just for two stages. So a more realistic pipeline looks something like this. The local Laplacian filters has about 100 stages in a complex graph. This gives us lots of choices about the organization and degree of fusion at each of dozens of stages. So each strategy could mean a totally different set of dozens of kernels or loop nests, completely restructuring all our code. And the difference between two plausible strategies can be an order of magnitude in efficiency. Now, to put that in concrete perspective, this is that algorithm we saw earlier in Photoshop. Remember, Adobe's version was written by one of their best engineers in about 1,500 lines of C++ and intrinsics, and it took 3 months to implement and optimize for parallelism and locality. In comparison, he and I took a single day to rewrite it in Halide and integrate it into Photoshop. It took 60 lines of code and ran twice as fast as their version on the same machine. Now, this is the kind of result we've often seen with Halide, but I think anytime anybody claims to beat some amazing expert tune baseline, you should ask questions. So how did we actually beat this expert tune code? It turns out that the win came mostly from interleaving stages differently and breaking some dependencies to trade redundant computation for better locality. But in the end, we didn't just make a few extra optimizations. We had to fuse and schedule each of the 100 stages differently to globally balance parallelism, locality, and the total amount of work over the whole pipeline better than the original code did. So the best organization we found here was just too hard for the original developer to find. He stopped after 3 months of rewriting and optimizing for a specific machine. But with Halide, it was orders of magnitude easier to globally reorganize this computation just by changing a few lines of the schedule. And as a result, we were able to find something more efficient overall in an afternoon of work. Now, at the same time, Adobe's been interested in using GPUs more and more for this kind of code, but couldn't afford to rewrite thousands of lines of code for each accelerator. But in just a few more minutes, again, just by changing the Halide schedule, we could also generate a GPU version that was 10 times faster still. And importantly, this one wasn't just a translation. It turns out that the best schedules on different architectures organize the computation in totally different ways. But today, different versions of this code are also in things like Instagram and Google's HDR+, using different schedules to target a wide range of different accelerators. Okay, so that's a bit on Halide. To recap, the big idea was to explicitly decouple the definition of the algorithm from the organization of its computation, and then to define a structured language of key scheduling choices for these kinds of programs. The end result are simpler programs that often can run faster than traditional hand-tuned code, while giving composable and portable components that scale from embedded DSPs to big GPUs or supercomputers. And it's being used heavily in the real world today. So it's in Photoshop, and Instagram, and all kinds of other things, from pretty much every Android phone to most of the videos processed by YouTube. It's also at the core of some of the new deep learning compilers. Overall, at this point, there's Halide code running in production on billions of devices, including probably most of the phones in your pockets right now. All right, so popping back up, this fundamental idea of using domain-specific structure to master dependencies and reorganize computation, it's been at the core of our work on Halide, but it's also led to contributions in a bunch of other areas. Now I first want to move down the stack and talk a little bit about hardware. So Halide helps us get the most out of a given processor, but for lots of real-time imaging and vision tasks, even that's not enough. And the problem, if you can call it that, is that modern image sensors are amazing. So my iPhone, for example, has 3 12-megapixel cameras, each of which pumps out close to a gigapixel per second of data. Now, for things like real-time tracking and robots in VR, or even just taking better pictures with your smartphone, we'd like to be able to drink from that fire hose and still do some serious computation on every pixel. Now, there's a joke at MIT that we do like to drink from fire hoses, but if we want to do 1,000 ops per pixel, we need teraops per second of compute. And to do it in your phone or headset, it needs to take less than a watt of power. Now, on its face, I think that sounds terrifying. So even at its theoretical peak, a mobile CPU can only deliver about 25 gigaops per watt. And a mobile GPU tops out at best 10 times higher, but it's still an order of magnitude short. But if you remember the fundamental costs of computation, that seems like it might actually be possible. It turns out we can do raw math at teraops per watt in modern hardware. The issue is that we just can't afford to move the data very much. So from this perspective, the only option we have is to take a really radical approach, to implement the whole computation in a single streaming pass over the data. If we can avoid going back and forth to memory and keep the on-chip data flow local from one operation to the next, we can spend most of our energy on compute instead of data movement. But doing that requires really heavily restricting the structure of possible dependencies and using a specific structure to organize the computational logic in space and time. Now, your cell phone includes a dedicated image signal processor, or ISP, that uses an approach like this to deliver teraops of computation in a fraction of a watt. So let's look quickly at how these architectures work. We can start with a really simple operation we might want to do on raw image data, like a black level. So it just takes one pixel in, adjusts its black level, and produces one pixel out. We can build this in hardware. We have wires for the input and output pixels, and all of the math packed together is just pipeline of logic in between. We can connect it to a camera sensor, excuse me, and connect its output to DRAM. And at this point, we have an extremely simple camera ISP. It processes 1 pixel per clock cycle. Now, we can easily add any number of additional blocks that process 1 pixel at a time to build a pipeline of operations. So if we compose 1,000 trivial ops this way and run it at a gigahertz, we have our teraop circuit. But importantly, dependencies are going to rear their head again. So we need to be able to do more than just point-wise operations. So if you think about functions like demosaicing or stereo matching, these kinds of computations have to read a whole neighborhood of pixels for each output. Now, ISPs deal with stencil functions like this by buffering intermediate values and delaying computation until the whole input window is available. If we have some function f feeding into a stencil function g, we have to think about where each of them is in its logical progression through the image. So if we want to compute g here, for example, it needs to be able to consume this window of f. And since data flows through the pipeline in scanline order, it means we need to wait until enough lines of the prior stage have been computed to cover the stencil. But then as soon as they have, they can be consumed to compute the corresponding pixel of the next stage. So ISPs hold these intermediates in small local circular buffers, often called line buffers, that are just big enough to hold the required values. Now, stepping back to the chip we were building, we can add line buffers to our pipeline anywhere we need to support stencil operators. And that's the basic architecture of lots of current hardware image processors. They're able to be so efficient because they keep all intermediate values local and they never have to touch external memory. Now, the problem is that designing advanced algorithms directly into hardware like this is really difficult and expensive. So Apple's camera team, for example, has on the order of 1,000 engineers just to turn out one major design per year. So I think this is another case where current tools conflate the core algorithms with how they're organized in hardware. In this case, all the way down to physical implementation and circuits. So we have to take, if we want to actually implement something like this, we have to take our nice high-level imaging algorithms and manually translate them into a register transfer level specification in Verilog or something of every detail of the hardware logic. And of course, again, automatically synthesizing efficient hardware like this directly from high-level languages has been a holy grail of the hardware community for decades. But just like automatically optimizing software code, it's proven intractable for several reasons for general programs. But applying the philosophy that I've been trying to tell you about today, using this understanding of the domain to define a structured space of computations and organizations, at Stanford, some colleagues and I defined a new domain-specific language for hardware synthesis called Darkroom. So it abstracts and generalizes the architecture of ISPs into what we call line buffered pipelines. A line buffered pipeline is a specialized class of synchronous data flow. It's a directed acyclic graph of stages where each stage is a pure function of a fixed size window of inputs. And again, the key issue here is the structure of the dependencies. So these highly efficient hardware implementations are only possible given tightly bounded dependencies between the stages. So we built the language around that constraint. But it's flexible and expressive enough to implement lots of imaging and vision pipelines in just a few dozen lines of code. Now, along with the structured dependence patterns, we showed that line buffered pipelines like this have a highly structured space of possible organizations or schedules. And even better, we showed how, because of how they're constrained, it's possible to directly solve for the optimal buffer minimizing design, the design that uses the least amount of buffering memory, as a polynomial time integer linear program. So in just a few seconds, our compiler can spit out an optimized structural Verilog implementation of a given high-level algorithm that uses the minimum possible amount of interstage buffering. And the end results in hardware are competitive with traditional hand-optimized designs. So after place and route in an admittedly now vintage 45 nanometer process, a couple dozen lines of code gives gigapixel per second throughput in a few hundred milliwatts and a fraction of a square millimeter of chip area for a range of different algorithms that we tried. Now, in another line of work, we looked at legacy code. So I've shown so far how you can do a lot, both in software and hardware with the right domain-specific abstractions. But so far, we've been asking people to rewrite code in a new programming language to get that. But an obvious question you might ask is, what about all the legacy code out there in the world already? Could we maybe extract structured dependencies and reorganize their computation to be more efficient? Or if we want to get even more crazy, could we even do it from the binary alone? So in the general case, this is obviously impossible, but several years ago, we found kind of amazingly that it was possible to reconstruct some image processing algorithms directly from optimized binaries by dynamically tracing their execution and analyzing thousands of iterations to infer the dependent structure. Once we'd done that, we were literally able to infer the algorithms underlying real Photoshop code in a shipping commercial binary, lift it all the way to halide code. And then by recompiling that with a new organization, we showed it was possible to replace the original code right inside a running copy of Photoshop and get better performance on new machines. Now, a couple of years ago, we released a newer sound static version of this approach in collaboration with Alvin Chung's group at Berkeley and researchers at Adobe. And this new version is based on program synthesis. So we're now automatically translating most of Photoshop's core blending and low-level filter libraries. So this is code with a history going back more than 30 years at this point. And its port to halides at the core of Adobe's effort to bring full Photoshop to iPad and ARM computers over the last few years. Okay. So the core approach I've argued for applies at many levels in image processing. And now I want to give a taste for how it's also really powerful in 3D graphics. So in rendering, I found that the biggest key is often to reorganize computation for reuse. So for example, at the start of my own career, I applied this idea to build an interactive preview system for special effects and animation. Now the problem here is that it takes hours to render a preview each time an artist makes an edit. But if they're only changing a few parameters, most of the work is obviously redundant. So when you're only changing the lighting parameters, for instance, a lot of the rendering computation is going to stay the same. So we built a compiler to analyze the dependence of the rendering on what the artist is actually changing. It automatically reorganizes the computation to do most of it in a pre-process and maps just the dynamic parts to a GPU. The end result runs about 10,000 times faster, so it's interactive instead of taking hours per frame. And this system wound up being used in production at ILM for about 6 years, where it was used on more than a dozen movies. Now, in real-time graphics pipelines, shading is often the dominant cost. So effects like motion blur require lots of visibility samples, but shading on a given surface element doesn't change much. So we rethought the architecture of the real-time graphics pipeline to more efficiently render effects like these. The key idea was tracking complex dependencies in hardware to reduce redundant shading. In the end, our reorganization reduced total rendering costs by an order of magnitude on real games. And since then, NVIDIA's adapted it for their latest GPUs, and these ideas have influenced lots of real-time game engines at this point. Now, another application that raises systems challenges is 3D printing. So a big challenge in multi-material 3D printing is the data size. You need up to gigavoxels per cubic inch of fabricated material. So to address this, together with the computational fabrication group at MIT, we helped build a system that represents the input to a 3D printer, not as a static model like you might be used to thinking, but instead as a procedural program. So we designed it to be able to express any volumetric output while structuring the computation for efficient organization, so it can be streamed for locality and parallelized for scalability. Now, lots of applications in areas like physical simulation, optimization, and inverse problems also use sparse and irregular data structures. So in these areas, the dependencies literally correspond to mathematical sparsity. And here we've worked on a series of domain-specific languages where we've shown how to capture structured sparsity in programs, perform high-level mathematical transformations, and then compile simple code directly to efficient matrix-free organizations. All right, so that's a little bit of how these ideas apply to 3D graphics. And now I want to wrap up talking about how I think they're critical to making the most of machine learning too. And I specifically want to address two contexts from our most recent work. So first, how can we use machine learning to optimize the performance of our systems? Can we automate the kinds of performance engineering that traditionally needs human experts? And second, how can we broaden the applicability of machine learning techniques? Specifically, how can we use gradient-based optimization to make more general programs in some sense learnable? And then how can we use learning systems in contexts where large deep neural networks are just too expensive? And the structure of computation and its organization has given us a powerful lens for both of these problems. So first, there's obviously lots of interest in applying machine learning to everything, including systems. But the sorts of performance engineering usually done by human experts requires precisely navigating really complex spaces of possible choices. And it turns out there's highly nonlinear behavior in how these choices impact performance. So the kind of structure I've been talking about, I think, is critical for leveraging learning in this context. And that's because it enables the combination of learning with powerful program analysis and search techniques, where each one is insufficient on its own. So using this idea, we've been working on learning to automatically schedule arbitrary halide programs better than the best human experts. And we're also working on systems that broaden the scope of deep learning techniques to make it easier to achieve high performance. So by creating a programming language that's both automatically differentiable and efficient, we can, on the one hand, use learning techniques to better optimize the internal parameters of traditional programs. And on the other, build new neural network layer architectures or even entire networks with a more general computational model. So we're both bringing a more general computational model to deep learning and bringing more deep learning to more general programs. Okay, so first, a little bit on optimizing programs. Even though I've talked about doing it in lots of different contexts, I think performance engineering is still really hard. So traditional heuristic-based compiler optimizations are great, but they aren't nearly as good as humans at the sort of large-scale reorganization that gives order of magnitude wins. So lots of people are hoping that learning will help compilers do better than they have in the past. But a big question remains, how can we learn to optimize programs? Well, with Halide, we defined a structured language of schedules that describes most important optimizations. We also have a growing mass of real expert-tuned code. So the first thing you might imagine doing is training a system to directly predict fast schedules for a given algorithm. But I actually think that's kind of throwing the baby out with the bathwater. So the space of schedules and their performance is incredibly complex, but it's also highly structured. So instead, I think the right approach here is to combine the strengths of structured search algorithms from classical AI program analysis from compilers, and machine learning. So then we can focus learning on, for example, predicting the best policy to guide the search, given everything that we know how to infer about the program from classical analyses. You can think of this approach as kind of like AlphaGo, but for optimizing programs. And this is exactly what we've done building a system to automatically schedule halide programs over the last few years. So we train a small deep model to predict the performance of thousands of random programs and schedules on a target machine. And then we use that model to guide a beam search over a structured enumeration of possible schedules. So we can either find a schedule in a few seconds directly from the search, just sort of like, just the -03 flag to your C compiler. Or alternatively, we can import and sample the space of schedules favored by the model and benchmark the top results to add a final layer of auto-tuning. And that's useful if we have a few minutes to a few hours to wait for better results. And the punchline is that this works really well. So this is the first automatic algorithm that consistently outperforms human experts on a wide range of real image processing, graphics, and learning workloads targeted by halide. Across a diverse benchmark suite, it essentially matches human experts in that instant -03 mode and outperforms them by 40% on average, given about an hour of auto-tuning time. And sometimes it's an order of magnitude faster. Now, on the other side, starting from halide, we've been building a fully differentiable programming language. So modern ML frameworks like PyTorch and TensorFlow are great for deep learning, using traditional models. So as long as what you want to do is well described by the standard layers they provide, they automatically give you both efficient GPU implementations and derivatives for gradient-based optimization. But the frontier of deep learning often involves extending traditional architectures with new differentiable operators. And this can be key to capture the problem-specific structure and make learning practical and efficient for new problems. Now, the fixed library of coarse-grained operators makes it difficult or impossible to express many new operators in traditional frameworks. The result's also fundamentally inefficient since it can't reorganize computation across operator kernels. Now, often the only alternative is to hand-derive gradients and manually implement it all in CUDA. But by balancing generality and structure, our differentiable programming language is faster and more general than PyTorch or TensorFlow for defining novel architectures. And at the same time, it's orders of magnitude easier than handwriting and differentiating CUDA. Now, this makes it much easier to define novel architectures for deep learning. But more surprisingly, I think, we've also shown how you can use it to take traditional programs, learn more optimal parameters, and often get deep learning level results. So for example, AHD is a state-of-the-art classical demosaicing algorithm, like the one probably still used in your camera today. But it's been surpassed dramatically by deep methods in the last few years. We found that just by taking the same loss function and training data and using them to resolve for the optimal parameters of the classical algorithm, we were able to dramatically improve its performance, approaching the best deep methods. But this learned classical program uses literally 1,000 times less compute and data than the conv nets. And importantly, once the parameters of the algorithm are automatically learned, it's also easy to explore a whole space of variance. So we can throw in things like larger or smaller filters in different places to trade off performance and quality. And doing this all is relatively effortless with a differentiable programming language. So we're blurring the boundary between deep learning and more general programming. And looking forward, I think this points toward a whole new way to approach learning for efficient inference, especially for performance-critical tasks like real-time imaging and video. And we've been starting to investigate learning to solve these tasks by combining program synthesis over this broader space of differentiable programs with gradient-based optimization of those programs' parameters. So here I'm showing some of our latest results applying this to demosaicing. So the y-axis here is reconstruction quality and the x-axis is performance. So the top right is where you want to get. And I should point out that this is a log-log scale. And our automatically synthesized new algorithms are orders of magnitude faster, higher quality, or both than either traditional or deep learning methods. Instead of relying only on the massive overparameterization of traditional deep neural networks, The resulting programs combine algorithmic structure with gradient-based parameter tuning to solve tasks with potentially orders of magnitude less compute and weight data than traditional deep learning. Okay, so popping back up, these same themes, the power of directly addressing the organization of computation, modeling and analyzing dependencies, and the trade-off between parallelism, locality, and the amount of work have come up throughout my group's research. And specifically, we use domain knowledge in graphics and visual computing to model and analyze the dependencies between data structures and computations in different applications. We use this to build compilers, systems, and architectures that organize the computations and data to balance competing pressures for parallelism, locality, and the total amount of work performed. And the end results are simpler programs, faster systems, and more efficient hardware. And ultimately, I think the systems of the future need the rich expertise of the graphics and vision communities, so I hope you'll join me. And finally, I just want to say that all this work I talked about has only been possible because I've been lucky to have such a wealth of amazing students and collaborators. Thanks.
Thank you, Jonathan. We'll have some time for questions. Let me begin with one.
Mm-hmm.
You talked quite a bit about the optimization part, so this is related to that. I'd love to hear your thoughts a little bit more about, so you talked about this amazing, in fact, all of it was amazing, but specifically taking binary code and raising it up to halide and then optimizing. You also talked about generating the space of optimization schedules. But you didn't talk much about kind of having the traditional programming language style optimization where the user has provided you certain things and you optimize that better, right? So instead of figuring out the most optimized schedule, if you took user schedule because you know that they know something, and then have tricks to optimize that better. Is that admittable here or no?
Yeah, so that's a good question. So because a bunch of our research has been on automatically inferring good schedules, one thing that I may not have made clear enough is that in the original design of Halide, and actually a lot of how it's used still in production today, both the algorithm and the schedule are often written by humans. So our original motivation actually was wanting to be able to have control over kind of steering the compiler optimization in the directions that we thought would be most fruitful. And that's how the scheduling language originally came about. It was a way for an expert performance engineer to be able to concisely and productively describe how a given program should be optimized without having to actually drive all the details of the generated code. Obviously, there's a lot of context where people also want to just be able to push a button and make things go fast. It turns out that having this structured space of things to consider that the scheduling language gives you is also useful as a target for a search system or machine learning system like I talked about. But one thing that I think is really interesting and still largely unsolved, but something that I'm interested in going forward is how we can make that not a binary choice where either you write a schedule entirely by hand, it's more productive than writing, low-level C or CUDA by hand, but you're still controlling everything in some sense, or we fully automate the search for you and figure out how you can combine human and human input and automation more effectively. So could I write down sketch of a schedule or a skeleton of what I think maybe parts of the loop code should roughly look like, and use that to steer the compiler optimization while still letting it, automate more things. It'd be really nice if we had a complete continuum where you could invest arbitrarily little or arbitrarily much effort, communicating with the computer to take more or less control over different parts where you think it's most useful. But that's still very much open research.
Okay, thank you. The floor is open for more questions.
I have a question. So I just so all the work that you showed. So great presentation and
Thank you.
And so you are so you have you're targeting it to a machine architecture and then optimizing it so that it runs better on that. Now, where do you sort of or is it sort of like at some so there are also I'm guessing hardware engineers who are optimizing or designing newer hardware architectures to do certain things, you know. So where do you reach a point and say that, you know, on this architecture, no matter what I do to my program, it's not going to bring more bang for the buck, and it is perhaps better to optimize the hardware instead. So
yeah, so there's two really fundamental issues that I think you're bringing up that are interrelated in an interesting way. So on the one hand, there's, you know, with performance results in general, and the ones I showed are no different. You usually see, you know, numbers that seem good or go up. Like, you know, I showed you things were kind of fast and made them faster, but I told you nothing about whether they're like approaching some theoretical optimal on a given machine. And I think the reason for that is that for some very specialized programs like dense matrix multiply, it turns out that you know, the problem is so perfectly structured that you can actually, the kind of mapping between theory and practice is really strong, and you can reason really clearly about you know, how close you're getting to the theoretical peak performance of your machine. But for most programs that are kind of bigger and hairier and more heterogeneous than that, it's just really hard to calibrate exactly what the, you know, how fast you theoretically could go. So, you know, for all these results I showed, is there, you know, 50% left, 10% left? Could it go 10 times faster even than the best results I showed? We can calibrate that a little bit by knowing what the, you know, theoretical peak math rate, you know, like the peak flops on my processor are, and I'm obviously not going to do more than that. But other than that, it's tough to know how close you are to optimal. But related to that, or you know, the other half of what you were asking about, you know, you have this choice of changing the code or changing the hardware. And I definitely think a really interesting question. You know, I mentioned a little bit of work on generating hardware to implement these things, as well as a lot of work on compiling software to do these sorts of programs. But I think a really interesting, another really interesting direction going forward is thinking about, you know, the co-design of hardware and software. You know, if I have a suite of programs in a structured representation like these domain-specific languages give you, could I maybe say something about, you know, where the biggest opportunity for adding new specialized instructions would be and how much of a win that might give me? So if I wanted to, you know, specialize a processor to be able to run a particular program or family of programs, you know, evolve the hardware to be able to better run the software that I have as a gift, that I have given. That's something that we're also interested in and starting to look at going forward.
thank you.
I have a question too. This was more on the machine learning side of things. So everything you presented was fabulous, but in machine learning, you also have this additional trade-off that the functions you're trying to compute could be approximated in many ways. So neural architecture searches. And then related to that, during learning, you have this additional like statistical trade-offs you can make. So it could be really bad at computing gradients or break dependencies in ways which are wrong, but you know, in expectation to do the right thing, and everything just works. So this is like superpower in machine learning, which somewhat different from these image processing and graphics pipelines.
It's funny, actually, a decade ago, you know, coming out of being a systems person coming out of the graphics world, I was mostly working on 3D stuff back then. People elsewhere would always tell me, oh, graphics is different than everything else because you can cheat and hack and you can use weird approximations everywhere. So that same spirit has been true, I think, in a lot of visual computing settings, not just in machine learning. But yeah, it's definitely the case that with any one of these efforts, we're focused on, you know, biting off kind of a piece of the stack and fixing, you know, what's outside of that a little bit, and focusing on just a certain, you know, certain class of optimizations, like, you know, with these with languages like Halide, we're very focused on computing the same result modulo machine precision, computing the same result, but just changing the order of computations and stuff like that to make it more efficient. That's complementary with also changing your algorithm, right? In halide terms, you might not want to just change the schedule to make things faster. You might want to change the algorithm. So the result that I teased at the very end actually is the most closely related thing to this that we've done. So that literally is, you can think of it as basically neural architecture search, but over a somewhat richer space of differentiable halide programs. So not just slapping together convolution layers, but also little structures that look more like things you'd see in traditional image processing pipeline, and then doing end-to-end learning through that and keeping a Pareto frontier of the trade-off between the efficiency of the resulting things and how accurately they can be trained to solve the task. So there we're basically searching over algorithms and then screening those algorithms based on both the trained accuracy they're able to achieve on the task and the performance they're able to get with the best schedule that we can give them. But yeah, it absolutely is the case that you can go even farther up or down the stack, and opportunities abound. So, in the far future, like we theoretically like to be able to have kind of ways of searching and productively making choices and reasoning at all of these levels all at once. The one thing I would say is I think it's useful to have tools that let you make these sorts of structured choices more productively by kind of by thinking more systematically about structuring the choices you have at a given layer of that stack. So rather than just saying, I have an arbitrary machine learning algorithm that's becoming arbitrary CUDA code, like breaking the problem apart into things like, the ideas of schedules and halide, or maybe there are structured ways you could describe your hyperparameter space for some of the machine, higher level machine learning algorithm choices that let you kind of decouple the separate concerns so that you can more productively think about the space of what you might actually try.
Okay. At the risk of bleeding into the next session, I can't resist asking one question, hopefully which has a short answer.
Sure, I can be quick.
you made it a point, and you do make it a point to call it a domain-specific language. But the concerns are the same in general computing, right? Suppose you're talking about data parallel computation or even task graphs given to you, and you basically have to figure out the right schedule. So what are your thoughts about just generalizing it into general purpose language?
Yeah, so I think that the term domain-specific language is the accepted terminology for these sorts of specialized languages. But I think very often the right way of thinking about them is that they're less domain-specific, especially something like halide. They're a bit less domain-specific and more data structure and computation pattern specific. So halide's not super specific to image processing. It's more specific to this infinite grid of sort of like virtual functional image that's the core data structure that it has. And the computational pattern where the dependencies between stages are often these stencil-like things. So think of like a convolution where the dependencies are a similar window that shifts with the output. And those bits of structure that are what the language is somewhat specialized to, we are working a lot on bringing these ideas to more different and more general contexts. But I think there's always going to be somewhat of a trade-off between how much your compiler or your language understands and knows about the specific data structures that you're working with and things like that, which is where a lot of the power of the scheduling language comes from, versus how general the system can be.
Okay, great. Thanks. I think we're going to close this session.
Great.
Because we need to start the next one. Thank you, everyone.
Thank you all.
On behalf of organizing committee, I feel delighted to express my thanks to Dr. Jonathan for this great talk. It was really indeed very informative and insightful. I also express my thanks to session chair Professor Subodh Kumar, other panelist members, the attendees who are present online or WebEx, and offline here at IIT Jodhpur auditorium. With this, we shall break for tea and rejoin sharp at 10:45. Thank you.
We could have taken over tea and asked more questions. Okay, see you in 10 minutes.
Dr. Parag, shall we begin?
Yes, so I guess it's already 10:45, and I
Yes.
assume that yes, we need to start. Is there someone from ICVGIP 2021 team who can suggest if we can start?
I guess we can start. Yeah, I'm from ICVGIP team here.
Yes, okay.
Anand, hello. Dr.
Hello,
Aditya.
sir. Hello.
Yeah. So, yeah, so let me introduce Dr. Aditya Nigam, who will be faculty member at who is faculty member at IIT Mandi, and he will be the chairing this session. This is an oral session. Over to Dr. Aditya.
Thank you, sir. Thank you very much. Okay, so first of all, let me welcome all of the participants as well as faculty members and students who have joined this. Also, I would like to congratulate our authors for getting their paper selected as an oral paper in ICVGIP, one of the top premier Indian conference. So let's begin our session. And so today, so that's going to be, 3A, session 3A. And in this oral session 3A, our first paper, which is going to be the paper ID 1515, MIRA-NET, facial microexpression recognition using 3D residual attention network. And authors are from IIIT Sri City, University of Chicago, Shivnadar. So the presenting author is going to be one of my old friend, Dr. Snehashish Mukherjee. Yes, sir. Snehashish Mukherjee. Yes, sir.
Yes, yes.
Yes.
Hello,
Okay. Thank you.
hello, Aditya.
Hello, sir. How are you?
Yeah, I'm fine.
Fine. So you can share your screen, and so I assume that it's going to be all. You are going to speak, or the recorded
Yes, yes.
presentation is going. Okay.
I'm going to speak.
Okay. Fine.
So, okay, share the screen. Is my screen visible?
Right now you are visible, but your screen is
Okay.
right now not visible. Yeah, it's about to come up. Yes, it's
Yes.
now
Okay.
we can see. Make it full screen and you can start, sir.
Yes,
Fine.
yes. Okay. So, good morning to all the attendees. I am Snehashish Mukherjee from Shivnadar University, Delhi NCR. So I'll be presenting the paper on facial microexpression recognition. So first of all, what is microexpression? So microexpression is different from facial expressions, general expressions, in the way that it appears on the face for very less duration of time. So maybe a very small fraction of a second it will last on the face, and also the intensity of the expression is very less. So it's very difficult to identify such expressions, first of all, and second is that because of the intensity, the low intensity of the expression, and at the same time it is very difficult to temporarily locate the portion of the video where the micro expression happens, because it happens for a very small fraction of time. So, but why are we interested in recognizing micro expression? Actually, several studies suggest that micro expressions actually depicts the true emotion of a person. So you can hide your actual emotion. For example, suppose the person is smiling, but actually his or her emotion is something else. Okay, so you can hide your emotion and you can depict a fake expression, but your true expression can be captured through this micro expression. So people are interested in recognizing micro expressions, but the challenges are like this. So it is very difficult to recognize the expression for the low intensity, as I said. And second is that the duration of the expression is very short. It's a very short span of time. So these are some literatures, some related works in this for micro expression recognition. So if we can categorize the related works in this area, so first of all, we can say that the little bit older techniques, they actually used to apply some CNN-based techniques. Okay, so CNNs are applied to extract the two-dimensional features from each frame, and somehow they used to coordinate among the frames to extract the temporal cues, and based on that they used to identify the action or say emotion. But it actually lacks the minute details of the texture information, because as I said, the intensity of the expression is very less. So it's very difficult, very important to capture the minute texture information. Okay, so that was somehow lacking in these kind of methods. Then some efforts we found where CNN features are clubbed with some handcrafted features based upon facial landmarks. So using the facial landmarks, you can locate the actual area of the face where the expression is actually happening. Okay, so so it's a combination of CNN features as well as handcrafted features. But the problem is the temporal localization. So you can localize on the face. So spatial localization is there, but you are lacking the temporal localization, which is very important as the span of the execution is very less. Third category we can say is CNN with optical flow information. So optical flow gives us the temporal cue, and CNN, two-dimensional CNN, gives us the spatial features. But the problem remains the same. You cannot locate the actual portion where the where the expression happened, micro expression happened. So there are some unnecessary motion information due to the optical flow information, but the actual information is still less. Another way of thought is that CNN along with LSTM. So two-dimensional features or spatial features are extracted by two-dimensional CNN, and the temporal features are extracted from LSTMs. So the frame by frame, the spatial features are extracted and fed into the LSTM layers for the temporal cues. So that is one school of thought. Another school of thought is applying 3D CNN. So both of them are useful, but the problem remains the same. The temporal localization of the actual area of the video where the micro expression happened. So one solution is that attention mechanism, just as it is done in this particular reference. So they applied facial attention mechanism at the portion of the face to locate the most reliable portion where the expression happened. But still the temporal localization is lacking. So our proposed idea is that applying spatiotemporal attention. So these are the contributions of our approach. So we applied a 3D residual attention network. So it recognizes the subtle features related to the micro expressions, and it is attention guided. So this 3D residual attention network consists of two attention blocks. One is channel attention, another is spatiotemporal attention blocks. So the spatiotemporal attention block actually deals with the spatiotemporal localization of the actual features. Okay, so in this work for the experimentation, we shown the saliency maps to show that how this proposed spatiotemporal attention mechanism can extract the important areas on the face to recognize the microexpression. Okay, so this is the overall model that we used, the proposed mirror net model. So it uses the residual attention network. So RA means residual attention module. So these residual attention modules are stacked one after another, and this residual attention module consists of two parts. One is not two parts. So there is a convolutional. So there are some convolutional layers, followed by a channel attention network, a channel attention block, and another STA block, means spatiotemporal attention block. So this is the spatiotemporal attention block that we proposed in our method. So input frames are fed into some CNNs, and we applied max pooling and average pooling, and then concatenated. The max.
Sir, the last 2 minutes are left. I'm sorry.
Okay.
Just 2 minutes.
Yes.
Okay.
Yes. So these are concatenated, and we applied 3D convolutional attention network, convolutional network, and we fed into some sigmoid function. Then this is the channel attention block that we have proposed. Here, the number of channels we have restricted to greater than 1. So this is the residual attention mechanism, or residual attention block, containing the CA and STA. Here plus stands for element-wise addition, and cross stands for point-wise multiplication. So these are the results. The first two are corresponding to the special the handcrafted features, and the rest of the things are from CNN based and deep learned features. The last one is our proposed method, and just before the last one, this one is actually without applying the attention mechanism. So this is to show how the proposed channel attention and spatiotemporal attention mechanism can extract the exact area in the face. So the third row is actually without using the attention mechanism, and the second row is with the, so after applying the attention mechanism. So after applying the attention mechanism, we can localize on the actual area of the face where actually the emotion is taking place. So these are the conclusion. I am not reading out the whole thing. So so one future research direction may be to reduce the number of parameters by applying some neural architecture search algorithms. So that may be a future goal.
Yeah, so thank you, sir. Thank you very much, Snehasi, sir. And is there anyone who is having any questions? Quick one question, if there is someone. We are already out of time. In fact, I was also, listening to a presentation. I was writing that with or without attention, but you have shown that in 2019 there was a paper in which they have used 3D, I guess, residual network, but without attention. So now you have added the attention, so your performance got better. The other anyways, you have also answered that I have written that number of parameters, but I assume that with this channel attention and spatial temporal, whatever the attentions that you have added, you are going to have much more number of parameters.
Yes. That is the problem in the current system. So we can try to reduce the number of parameters using some other mechanism, some NAS applications that we have.
Understood. Yes. Okay, sir. Thank you very much. Thank you.
Thank you.
Yeah. Thank you. So with this, let's move on to the next presentation. And next paper, the paper ID is 22. That is CT DAN, which is a domain adaptation neural network, I guess. And that's with co-teaching. So co-teaching means DANN for wild unsupervised domain adaptation. And the authors are Rahul Bansal from Flipkart and Soma Biswas madam from IISc Bangalore. So presenting author is also Soma Biswas madam. Yes, so I know him. I don't know whether she knows me or not. Yeah, madam, are you there, or who is going to present?
Hello everyone, I'm the speaker for this presentation, CTDANN. Co-teaching meets DANN for wild unsupervised domain adaptation. So there are three keywords here: co-teaching, DANN, unsupervised domain adaptation, and wild unsupervised domain adaptation. Unsupervised domain adaptation, no target label. So unsupervised domain adaptation aims at leveraging supervision from a source domain data for performing tasks on unlabeled target domain data. So there are two domains, one is labeled and another is unlabeled, and these two domains follows different distribution. So if we simply train a model using labeled data, it will not generalize well on the target domain data because of the distribution shift between the two domains. So how to adapt a deep network? So most existing work resolve unsupervised domain adaptation problem by minimizing domain discrepancy between source and target domain data by learning some common domain invariant feature. As we can see in this picture, this is a shared network which aligns the distribution of these two data by projecting the data set into some common domain. Adversarial domain adaptation. It is another standard technique to align the distribution of two data set which uses adversarial loss technique. So the network which we are seeing in green is a feature extractor. Network which we are seeing in orange is a domain classifier. So domain classifier classifies the samples, whether it belongs to a source domain data or a target domain data. Source domain data 1, target domain data 0. And feature extractor tries to confuse it, and in the process it tries to project features, it tries to project source domain data and target domain data in a latent space where the source domain data and target domain data are indistinguishable to each other by domain classifier. The network which we are seeing in blue is a classifier which takes up source features and which only takes up the source feature data, and it trains a classifier. The network in green will generalize well on the target domain data as well, because source feature and target feature in the latent space are following the same distribution. Wild unsupervised domain adaptation. So in wild unsupervised domain adaptation, we have two challenges. One is noisy source domain data and another is a distribution shift between source and target. Why did we include noisy source domain data as well? Because labeled source domain data is generally crowdsourced from the internet, making their labels unreliable, and sometimes there is a noise in the image also. So now we have two challenges. One is noisy data and another is a distribution shift. Co-teaching. So training of a deep neural network with noisy labels. Co-teaching is another state-of-the-art technique for image classification under noisy label data. There is no domain adaptation here. Co-teaching is just for an image classification task with noisy label data. Co-teaching is based on a small loss concept that deep model can memorize easy samples first and gradually adapt to hard samples. What do I mean by easy and hard? Easy samples are those which are correctly labeled and hard are those which are wrongly labeled. So what happens is that it's difficult for deep learning model to learn hard instances. It overfits to it as the training progresses. So what co-teaching does is in every mini batch, it selects a subset of the sample based on the small loss concept and trains the model using only those samples. And it maintains two identical network in parallel. So subset of the sample selected through network 1 used to update the network 2, and subset of the sample selected via network 2 is used to update the network 1. We can take a peer review as a supporting example for this architecture. Propose CTDN approach. So as I've told you that we have two challenges here. One is a noisy source domain data and another is a distribution shift. To tackle noisy source domain data, we have maintained two network 1, network 2, network 1 feature extractor 1, classifier 1, network 2 feature extractor 2, classifier 2. So network 1 gets both the data labeled source domain data as well as unlabeled target domain data, and network 2 only get labeled source data. So network 2 only participates in selecting the clean samples based on the small loss concept. But network 1 participates in both, that is in domain distribution shift problem as well as selecting the clean sample based on the small loss concept as well. So feature extractor 1 and domain discriminator works in adversarial to each other, so that feature extractor learns to project labeled source domain data and unlabeled target domain data into some latent space where they both are indistinguishable by each other. So in co-teaching, we were selecting the sample based on a small loss concept. Here, we are weighing them. We are not selecting. We are not selecting a subset of the sample. We are weighing them based on some weighting factor. Lambda 1 and lambda 2 are weights, and these weights are calculated based on the loss. So weight is inversely proportional to the loss. That is how it is being calculated. It simply means that if the loss is more, then weight is low. It's meaning that loss being high, it simply means that it is more likely to be noisy, and if loss is low, then it is less likely to be noisy, so weight will be higher. And these weights are cross propagated to peer network to update the parameters of the network. So weighted classification loss. So corresponding to each network, we have weighted classification loss LY1 and LY2. As we can see that LY1 is weighed using the weights calculated through network 2, and LY2 is calculated using the weights calculated via network 1. So, and these two losses are nothing but a cross entropy loss weighed using the weights of the peer network. Domain discriminator loss. So domain discriminator is a binary cross entropy loss, as I have explained earlier, that it simply so domain discriminator is simply used to detect whether it belongs to a target domain or source domain, and it works in adversarial to the feature extractor. Weight factor. So weight, as I've earlier explained, so weight is inversely proportional to the loss. The function which we are using is weight is equal to e raised to power minus loss. So in loss, we have two factors. One is how clean or noisy the sample is, and another is that how effective the sample is for the domain adaptation task. Entropy loss. We are also using the entropy minimization principle for unlabeled target domain data. Final loss and optimization. So corresponding to the two networks, we have two losses, loss 1 and loss 2. Loss 1 is Ly1 minus beta 1 LD plus beta 2 LT. Beta 1 and beta 2 are hyperparameters. So feature extractor 1 and classifier 1 tries to minimize loss 1. Simply means that it is minimizing the classification loss but maximizing domain discriminator loss. And domain discriminator tries to maximize loss 1 simply means that it is minimizing LD, which is a domain discriminator loss. And feature extractor 2 and classifier 2 tries to minimize loss 2. So important features of DNN. So DNN incorporates co-teaching into DNN framework very seamlessly. It's an end-to-end model. Unlike co-teaching, we are not rejecting out any samples. We are weighing them, so we need not know the noise level. In co-teaching, there is an assumption that we need to know the noise level, but in CTDNN, we need not know the noise level. So we have experimented with 3 datasets, Office Home, Office 31 and Bing Caltech. Office Home and Office 31 are clean dataset. We used pair flip, we generated pair flip and symmetric noise to make these 2 dataset noisy. Bing Caltech data is inherently noisy. So baseline and variants. So our baseline is DNN and TCL. TCL is a transferable curriculum, another state-of-the-art method for wild unsupervised domain adaptation. CTDNN1 and CTDNN2 are our variants. CTDNN1 is nothing but a sequential 2-stage approach. So it simply means that we are passing the samples firstly through a co-teaching and then through a DNN. CTDNN2 is same as CTDNN, is just that we are not using weighting scheme in CTDNN2. So this is the result on Office 31 with 40% symmetric label noise. As we can see that we are outperforming all the state-of-the-art method. TCL is state-of-the-art method for WUDA, and others are the state-of-the-art method for UDA method for UDA problem. We have experimented with different levels of noise as well, 10, 30, 40. So at low levels of noise, all the 3 approaches performs well because deep learning networks inherently are robust to some levels of noise. But as we keep on increasing the noise, our approach CTDNN is more robust than the other 2. We have also, so table 3 is a comparison with our variants only. As we can see that CTDNN performs better than CTDNN2, and difference between CTDNN and CTDNN2 is just the weighting scheme. In CTDNN we have the weighting scheme, and in CTDNN2 we don't have the weighting scheme. And CTDNN1 is a two-stage approach, which is also performing inferior to TCL as well as CTDNN, but performing better than DNN because there will be no negative transfer in CTDNN1. Table 4 is the analysis which we have done with label noise as well as with the image corruption. So in this, like we have done 20% of the samples were corrupted with label noise and 20% with image corruption. How we have done the image corruption? By Gaussian noise and followed by salt and pepper noise. So conclusion is that CTDNN seamlessly integrates the co-teaching approach in DNN backbone, and we could have used some other backbone as well, like CDN or some other backbone for standard UDA, for another standard backbone for UDA problem. So that could be experimented. And so extensive experiment on 3 different datasets with different types of levels of noise shows the effectiveness of our proposed approach. Thank you.
So it's done. I assume that it was an automated presentation and no one is there to answer any question. So,
Aditya, Dr. Aditya.
Yes, sir. Yes, sir.
The author is there as attendee.
Oh.
I request IT team to unmute him if he is available.
Oh, Rahul Bansal is there. Rahul,
Yes.
Please add him. Yeah. He has raised his hand.
Yes.
Can we have Rahul? Yeah. IT Jodhpur team, can you add him and give him rights to speak?
Unmute him.
Unmute. Yes, I can't do that. Is there
No,
someone from IT?
Yeah, I'm asking. Just give me a minute.
Okay. Okay, sir. Okay. In the meanwhile, if there is anyone who wanted to ask any question, please get yourself ready. Is there anyone who wanted to ask a question? Please raise your hand. Yeah.
Rahul, can you hear us?
Yeah, I can hear you. Can you hear
Okay.
me?
Yes, Rahul. Yes, Rahul, we can hear you and we have listened to your presentation. It was a nice presentation, although it was very fast because you have to cover several things, but well presented. If there is anyone who is having any question about this work, although what I observed was that a huge amount of experimentation is being done, and I assume that's almost a matured work in which all the type of comparative analysis and other things that are being required for a complete paper, it's being shown and done. My question is that you have used multiple loss functions. Out of that, the entropy loss was also there. You have said that it is to manage the noisy label. So can you elaborate that how? Yeah.
No, so actually there are three losses. One is a cross
Yeah.
entropy loss, which is generally a classification loss. Another is a domain loss, which is used to do the domain shift, which handles the domain shift between the two domains. And third one is a entropy loss, just an entropy loss that is only for target data, because for target data we don't have any labels. So we just want that the entropy of the labels of the target data should be very low. It's just an entropy minimization principle.
Okay, so you see, so my question was that have you observed its convergence independently, or you added all of them and then later you have seen that what's the effect of entropy loss?
No, we have not seen the. So actually, so we have added all these losses with some multiplier, which are our hyperparameters, and then we tuned on the basis of, and then we tuned those hyperparameters like classification loss plus k domain loss plus k2 entropy loss.
Yes, I understand. So I just suggest that you can check that independently. So entropy loss may start with some value. So is it actually getting saturated or even getting low? Because you must have given some weight to the entropy loss, and I assume it's not going to be too much. So is it that
Yes,
the
yes. Yeah, weight for the entropy loss is very low compared to the other. Yes.
yeah? So it's convergence. Several times we have seen that these losses keep on there. They don't much converge. So is it really going to be helpful in your solution? So that it may actually be justified from there. Otherwise, we are okay. Yeah, we are done,
Makes
Rahul.
sense.
Thank you very much. Yeah,
Thank
we
you,
are done.
Aditya.
Thank you,
Yeah.
Rahul. Thank you. Yeah.
Yeah.
Okay.
Okay.
So with yes, somebody is having another question. Please ask.
So yeah, I'm Divya, and like I would like to please explain once again that the relationship between the loss and the weights. Can you please
Okay.
elaborate that
So
again?
yes, definitely. Yeah. So the losses are weighed using the weights actually. Loss is same, it's just that they are weighed. So how, and the weights are calculated based on the loss itself. The more the loss, less the weight. There is an inversely proportional relationship between loss and weight. Because if the loss is more, then we assume that the sample is more likely to be noisy, so we give them a lower weight. And if the loss is less, we assume that the assumption is that that sample is likely to be less noisy, so weight is more. That's a small loss concept.
Okay,
And
okay. And
for
one
that
more,
actually,
yeah, please.
and we at the start, actually in the start, like for the first few epochs, we don't do any waiting, because at that time like system needs to warm up. For first 3 4 epochs we don't do any waiting, because at that time system knows nothing. So yeah, as the system starts progressing, then the waiting scheme comes into play.
Okay, so like I just want to clarify, is this that what we say lambda L1 plus lambda 2 L2? So is this the weight that you want to that you are denoting?
Yes, exactly. Yes.
Okay, yes. And
Yeah.
one more thing, please explain that domain distribution loss
Yeah.
just a bit. detail of that.
Yeah, so domain distribution loss is nothing but it's a binary cross entropy loss. And so what happens is that feature extractor and domain discriminator works in adversarial to each other. Domain discriminator tries to discriminate between source domain and target domain, and feature extractor tries to confuse it.
Yeah.
So feature extractor tries to maximize the domain discriminator loss, and domain discriminator tries to minimize that loss. So
Yes.
it is just a binary cross entropy loss. The goal is for feature extractor to learn generate features which are not distinguished by domain discriminator. The idea is to project these two distribution into some common domain.
Okay, so I'm sorry to interrupt. We have lost 6 more minutes. So thank you. So I'm also happy that Divya has asked. If you have more questions, please contact offline and have a fruitful discussion. So thank you, Rahul, again for your good presentation and work. Let us move on to the third paper, which is paper ID 49. NTUX, an enhanced large-scale dataset for improving pose-based recognition of subtle human actions. Authors are from Triple IT Hyderabad. Neil Trivedi is going to be the presenter. I welcome Neil Trivedi, and I also request that now we need to more carefully look into the time. So Neil, you have your 15 minutes. We are anyways lost 6 minutes.
Yeah.
Yes.
Am I
And
audible?
those who have question, yes, you are audible. And those who have question, please get yourself ready. And as soon as we finish, please ask your questions. We need to keep our time well. Yes, Neil, you can start.
Yep. Is my screen visible?
Yes, you can start, Neil.
Yeah. Hello everyone. I'm Neil Trivedi, and I'll be presenting NTUX, an enhanced large-scale dataset for improving pose-based recognition of subtle human actions. So firstly, I'll briefly describe the problem statement of skeleton action recognition and how it works. So essentially, we'll have a person performing an action. Those actions are captured and we pass it through some kind of skeleton extraction method, which gives us a 3D skeleton sequence as shown in the GIF. And once we have this skeleton sequence, we pass it through the classifier, which are trained to identify what action is being performed. So this is the overview of the problem of skeleton action recognition. Now I'll introduce the existing widely used datasets, which are called NTU-RGB plus D and NTU-RGB plus D120. So these are some of the salient features in this dataset. So NTU-RGB plus D dataset contains 56,880 samples spanning over 60 different classes, and NTU-RGB plus D120 dataset contains 114,480 samples spanning across 120 different action categories. Note that both of these dataset gives the skeleton in 25 joints topology. So how these data sets are captured? So there is a performer performing an action, and there are 3 cameras situated at 0, -45, and 45 degree with respect to the performer, and then performer replicates this action 2 times, which gives us 6 different combinations of action, single action, and the cameras that are used in this capture dataset creation are Microsoft Kinect version 2. So this is the topology of the skeleton that is provided in this dataset. As you can see, there are total 25 joints provided in the skeleton, and the name of these joints are given in the slide. And these are some of the samples from this existing dataset. We can see the actions are like hand waving, kicking something, and put on hat. So these are the RGB frames overlaid by the skeleton that has been provided by this datasets. So even though these data sets are widely used and a lot of research has been done to get good accuracies for this data set, they suffer from some inherent issues, and that is what we try to address in our work. So if we can see that the skeleton that has been provided in this data set contains only 3 joints per fingers in each hand, which are not sufficient to address to distinguish between lots of actions, as we'll see in the further slides. So these are some of the actions from given in this data set. And if we take some time and try to identify these actions, it will be really difficult for us because they are not at all comprehensive from just by looking at the skeleton data set. Even after I show you the labels of these action categories, it is not very easy to identify what action is being performed since there are only 3 joints in hands. So it is impossible to distinguish these actions without fine finger level joints. So we can also observe these issues when we see the per class performance of the state-of-the-art methods. We can see that the most worst performing classes include lots of action labels which involve hand level movements like writing, eat meal, and type on keyboard, etc. Similar can be seen for the NTU 120 dataset. So what can be the solution? The solution is adding finger level joints to the dataset. So that's why we are introducing the NTU-X, an enhanced large-scale dataset for improving pose-based recognition of subtle human actions. NTU-X has a dense skeleton representation, including a total of 118 joints as compared to the 25 joints of the earlier dataset. This dataset contains, along with 25 body joints, 51 facial joints, and 21 finger joints for both of the hands. And all of these features are provided for all the samples of original NTU-RGB plus D and NTU-RGB plus D 120 dataset. So I'll next give you the overview of the pipeline that was used to create this NTU-X dataset. So there, the pipeline is divided into 2 stages. In first stage, given the RGB frame sequence, we try to extract the 2D skeleton from this RGB frames. And once we have this 2D skeleton, we use 3D skeleton extraction methods to get the final output skeleton sequence. So in this slide, I'll explain the stage 1, which in which we are trying to extract the 2D skeleton sequence given the RGB frame. So as you can see that we use the CMU OpenPose as our 2D extractor, and we pass the RGB sequence through the this extractor, and we get the 2D skeleton sequence as shown in the overlaid sample. In the stage 2, where we try to extract the 3D skeleton, we use the RGB frame sequence along with the 2D skeleton sequence that we had extracted earlier in the stage 1 and pass it through 3D skeleton extractor, which will output the 3D skeleton sequence as our final data. And for the 3D skeleton extractor, we have used SMPLX and Expose as a 3D extractor. So we had to choose between SMPLX and Expose, and the way we made this decision was by semi-automatic method and looking at some of the samples of some of the output of this both method. As we can see that SMPLX is slow, but it is more reliable for the samples which are from side view and contain multiple people. However, Expose is a lot fast as compared to SMPLX. And based on this observation, we divided some of the classes to be extracted by SMPLX and others by Expose. So to show the superiority of the NTU-X dataset, we'll go back to those samples we saw a few slides back, where we were not able to identify the actions that were being performed using the original dataset. But now with our proposed dataset, it is very easy to identify these actions even without looking at the labels of these actions. So this clearly shows the importance of including hand joints and by those means importance of the NTU-X dataset. So we benchmark few of the existing approaches of original NTU dataset on our NTU-X dataset, and we can clearly see by the green column that just by improvising the data, the existing approaches perform significantly well as compared to the original dataset. So as we saw that the worst performing classes included finger level movements, and hence by observing the improvement in those classes, we can also see the importance of NTU-X dataset that we have proposed. Similar is the case with the 120 class dataset, where the classes involving finger level movements have improved a lot. So, so essentially, to summarize our work, we point out some of the major issues with the existing widely used skeleton action dataset, which is that they lack finger level joints and which bottlenecks existing approaches to identify actions which involve significant finger movements like thumbs up or make OK sign. And hence, to overcome these drawbacks, we introduce NTU-X dataset, which contains a dense 118 joint skeleton. And we by experimental evidence, we show that our dataset helps the existing approaches by a significant margin to classify the actions involving finger level movements. Thank you. Further details about our dataset and pre-trained models can be found at our GitHub repo and also on our project page on the links that are given in the slides. Thank you.
Yes, so thank you, Neil. Thank you very much for your crisp and short presentation. We are back in time. If you have any questions, is there anyone who is having any question, please ask. Divya, do you have any question? Anyone else? 1, 2, 3. No one. So, Neil, I have a question that, so as you have said that all the existing benchmarks, you just have improvised the data and started to work. And we understand that if it's a hand-based thing and finger joints being given, old things is also started to grab the useful information. But
Right.
do you think that your data set started to, so if we take all the previous data sets in which your I guess 21 finger points that you have introduced in your data set, if we don't utilize that,
right,
and use the previous algorithm, so is it the case that they started to perform with a similar type of performance, or your data is also better in body, that 25 points or that the facial or other points?
Yes, sir. So those, so essentially we have provided in our paper those ablations where we only use the 25 joints of body from our data sets, and we can see in qualitative measures that our data is much more cleaner and capture much better way as compared to the original Kinect based data set. So even when we use only the 25 joints of our data set, the performance is as comparable with the original 25 joints Kinect based data set.
Okay, so I understand it's cleaner data, so it's slightly better than the existing data sets. Understood. So this is now publicly available. What's the process to download this data?
So sir, we since this dataset is extension of the original NTU dataset, we are awaiting the permission from the NTU labs to allow us to publicly release this dataset. However, if someone wants, the entire process of creating this dataset is available on our GitHub repository. Once we gain the permission from the original labs, we'll be publishing the data.
What is the expected timeline of the publication of such data?
I'm not sure.
You're not sure.
Yeah.
Okay, fine. So we are done. If there is no other question, thanks, Neil, once again. Thank you. Okay, so now going on to our next paper, and the next paper is 51, paper ID 51, towards interpretable facial emotion recognition, and the authors are from IIT Roorkee, Sarthak Malik, Puneet Kumar, and Bala Subramania Raman. Presenting author is Puneet Kumar. Welcome, Puneet Kumar. Are you there?
It will be a recorded presentation.
Oh, it's a recorded presentation. Please start that.
Yeah, okay.
A very good morning to all the respected chair members, professors, and my fellow authors. Today, as Sarthak Malik, a BTech student from IIT Roorkee, is going to give a brief talk about a work on interpretable AI. The topic of our paper is towards interpretable facial emotion recognition. Before starting, I would like to give an outline of what this talk will be all about. Firstly, I would be introducing about the topics that we have addressed in our paper, then our contribution made towards this direction, and the literature survey, that is all the works that have already been done. Then we will dive deep into the problem formulation, the architecture, and the new DNC shape algorithm that we have proposed. At last, I will be showing few results related to the confusion matrix and the feature maps that are outputted by the DNC shape algorithm, and then we will analyze them. Beginning with the introduction, as we have seen with time, the deep learning models have shown a great potential, and their accuracy is increasing day by day, made the field of medical field, emotion analysis, or speech analysis. They are performing better and better in each field. But what is stopping them is their black box nature. Interpreting a DNN model is a tough task. We can't tell what are the features that the deep learning model is concentrating or how it's concentrating. Why he have given the importance to that particular feature. It may be possible that there is high accuracy because of some noise or the model seeing features that are not even relevant. So this led to development of a new field in AI, the interpretable AI. This contains few algorithms like SHAP, LINE, and GradCam. Many of these are computationally very expensive, while others don't have any mathematical proof. While some, like GradCam, are good and even faster. The problem with them is they are prone to shift in the image. Like a little shift in a GradCam can lead to a huge change in the feature map. Again, this caused them stress. So this motivated us to explore the field of interpretable AI, and we developed a new method, divide and conquer based Shapley additive explanation, DNC SHAP, and applied the same on the FER system that we have proposed. Speaking of our contribution, we have proposed a deep learning based facial emotion recognition system that can classify the features into 7 discrete classes. Then we applied our novel DNC SHAP algorithm on this system to analyze the feature maps we get and the highly relevant features or pixels we get from this. At last, the main contribution of this paper is the DNC SHAP algorithm. We have incorporated the divide and conquer algorithm with the Shapley values to get the highly relevant pixels or features in linear time, which requires a quadratic time earlier. Now, let's do a brief literature survey. The field of emotion AI is well known and booming in research. There are various research papers done in this field, as we can see here. These models can be classified basically in 2 ways. First is the traditional based ML models. These require techniques of handcrafted feature extraction. The techniques like oriented gradients, local binary pattern, and Gabor wavelets are used. While the other are the end-to-end based deep learning models. These models don't require any handcrafted features and can work their own. Also, people have added some attention layers in these models. All these models work on 7 basic features of happy, sad, fear, disgust, surprise, anger, neutral. These are the binding work of Paul Ekman. We have used the same features in this model. Speaking of interpretable AI has gained importance in the last few years. It is because of the black box nature of DNN and the mistrust that it creates. Interpretable AI is basically of 3 types. We can speak of attribution method, perturbation-based method, or backpropagation-based method. Attribution-based method means assigning some relevance or importance score to each feature, in this case of images, each pixel, to get a feature map. The main work in this field is the SHAP by Lundberg and its team. It is based on Shapley value and it's a quadratic in computation. Next is the perturbation-based method. In this method, we change each feature by slide and see what is the impact on the prediction. This helps us in giving importance to each and every feature. The main work in this field is line. Line is not mathematically proved yet, and so we can't trust this completely. It collides, it is same as SHAP in case of linear model, but in non-linear model, it disagrees with SHAP. Last is the backpropagation based method. In this method, we backpropagate the net from the top to bottom to get the relevance score of each and every pixels. This includes saliency map and GradCam. This category is great, but they are very prone to slight change in the image. Now, let's see what we want to achieve in this paper mathematically. Let us consider a neural net F that maps n-dimensional feature X to label M. Y1, Y2, Y3, Ym, and the features are X1, X2, X3, and Xn. The goal of this proposed approach is to find the Shapley value for the importance of each pixel Xi in getting the label Yj. Looking at the methodology of our FER model, we can see in figure 1 that our model is built on top of VG16. We have added 4 residual layers to it and concatenated them at the end. The idea to this came from the fact that each block in VG16 give us some features. It may be possible that these features dilute as we propagate through the net. So we thought of adding these features at the end, and this worked out to be great. Next comes our DNC-SHAP algorithm. As I have already discussed, DNC-SHAP here means divide and conquer based Shapley additive acceleration. Here we have incorporated divide and conquer with SHAP algorithm to reduce its time complexity. Shapley values basically are from game theory and are permutation combination based. They are NP hard and require exponential time. But this is not possible in computation. So what we did was we incorporated divide and conquer. That is, we divide the whole image in the half and we calculate the importance of each half. Again, we divided these halves into halves and calculated their importance. Combining them, we get a feature map here. The red part here shows the high relevance area while the blue shows the low relevance area. Now, let us discuss the ablation study which has led to the architecture that we have proposed. Firstly, we just used a pre-trained VG16 as net. We were not able to get a great result. Then we built a baseline model based on our idea of residual layer. We just included 2 residual layers and a dense layer of size 4096. What we observed was that the output accuracy was fluctuating too much while training. So we concluded that the neurons are too many in the dense layer. We reduced the size of dense layer 2048. Also, we incorporated 4 residual layers as we have seen in the final net. This gave us the accuracy. This gave us state-of-the-art result in 3 of the 4 datasets that we will be discussing later. The experimental setup used for this is NVIDIA Tesla T4 GPU with 2560 CUDA cores and 2320 tensor cores with 16 GB of virtual RAM. The dataset used by us are FER13, FERG, GEFI, and CK+. All the experimentations are performed using 5-fold cross-validation, item optimization, categorical cross-entropy loss, and test size of 32 for FER13 and 16 for rest of the dataset. The model is trained up to 100 epoch for each of the dataset with a learning rate of 8 into 10 to the minus 4. Now, let us summarize the results that we got from this paper. Firstly, our FER system, the facial emotion recognition system, is able to get state-of-the-art result in 3 out of the 4 datasets we have used. The results here are 62.62%, 99.68%, 99.97%, and 99.67% for the 4 datasets. This can be seen in the confirmed matrix here. We can also see the table to result comparison that FERG, GFE, and CK+ got the state-of-the-art result. Next comes the feature maps given over by the DNC-SHAP algorithm for various classes of anger, disgust, fear, happy, and sad, surprise, neutral. Here we can see the feature maps. The anger part, the face of the nose and the lips of the woman are most highlighted. For the disgust, the eyes and the nose that is formed in this way that show disgust is highlighted. For the fear part, we can see the facial is distorted and also the chin is lower. So the algorithm is focusing that area. Happy, it's clear that smile will be seen in the teeth. Surprise, it's clearly visible that the open mouth can be seen. So this is how we have outputted the feature map using DNC-SHAP algorithm. Table 3, we can see here the table 3 compare the theoretical post, the execution time of various interpretable algorithm. DNC-SHAP is just after GradCam, but I have already discussed the problem with GradCam. They are not trustable. They changes the feature map a lot. Even if we change, even if we propagate an image a little bit in axis on the y-axis direction, so they are not trustable. Also can't be proved. While DNC-SHAP algorithm is mathematically proved, algorithm from Shapley values is faster than both SHAP and line. Table 4 here shows the feature overlap that I was talking about. The DNC-SHAP algorithm overlaps the most with the SHAP algorithm that is currently used in the industry. It is a quadratic, while our DNC-SHAP is a linear algorithm. Now, I would like to conclude our paper with these points. This paper proposes an interpretable deep learning-based FER system, which we can analyze our result. We have analyzed the result of FER model using our newly proposed DNC-SHAP algorithm. Our DNC-SHAP algorithm gives the highly relevant feature for each class, and it is consistent for all the images in a class. Also, the features that come out for different data set is consistent for each class. With this, I would like to conclude my talk, and thank you very much.
Yeah, so thank you very much, Sarthak. Sarthak is here. If you have any questions, please ask. Sarthak is a BTech student at IIT Roorkee. And if you have any questions, please carry on. If you have any questions, anyone, last 10 seconds. If you have any questions, please ask. Okay. So Sarthak, I have one or two maybe very short answered question. First one is that you have used this Zafe and CK4. So they are, I understand they are very old. In fact, in 10 years
sir.
back, I was also using them. This FER13.
Yes, sir.
So it's a new database. Your performance was also around 60 plus there just. So what is the reason and what are the
Actually,
challenges?
this is a
Yes.
very random data set. Jeffrey and other one is very organized one.
Yeah.
This one is a very random data set. Like these can also consist images of cars, shoes, etc. I mean, they are just taken randomly from the internet. They
So
are not
this
well
is
organized.
so it's a public database
Yes,
because
sir.
yeah, it's and that's right now the standard benchmark database for FER.
Yes, sir.
Okay. My other question is that you have done this facial emotion recognition using so applied it on individual images. Suppose that if I have videos,
Yes, sir.
so is it that I have to apply it frame by frame and it will perform?
Yes, sir. Yes, sir. We have to apply it frame by frame.
But emotions several times are lasting for some microseconds or maybe half a second or so. But you are looking only seeing individual images.
Yes, sir. The main purpose for this paper is to interpret each emotions, like the features, in a lower number of time.
So you want to say
The
only
Yes, sir.
interpretation was something
Yes,
that
sir.
whether you want to see that what you are looking and is it really relevant?
Yes, sir. Yes, sir. Whether the model is trustable or not. It may be possible it's looking at some features which are not in that image. Like in the
Okay.
presentation, we can see the smiling face. It is concentrating on the teeth itself.
Okay, understood. So Snehashish, do you have any related questions, or we can carry on?
No. Okay.
Yes, okay. Okay, fine. Okay, fine. Thank you, Sarthak, very much, and keeping the time. Yeah. So our next paper is going to be paper ID 118, and that is handling ambiguous annotations for facial expression recognition in wild again. It's going to be a FER paper in wild again. And the authors are Darshan Gera, SSIH, Vikas GN, and Bala Subramaniam. And here it shows that Vikas GN is going to present. Let us see. Is it?
So
Yeah.
this will be also a recorded talk.
Recorded talk.
Let me
Okay,
say
sir,
this.
please start. It's again a recorded talk. Thank
Everyone,
you.
my name is Vikas, and we are here to present our work titled Handling Ambiguous Annotations for Facial Expression Recognition in the Wild. Before we begin, I would like to thank the organizers of the conference, collaborators Dr. Darshan Gera and Dr. Balasubramanian, and the Department of Mathematics and Computer Science of Sri Sathya Sai Institute of Higher Learning. I would also like to thank Bhagwan Sri Sathya Sai Baba, the founder chancellor of the institute. Facial expressions play an important role in social interaction and communication. Recognizing them can improve science with applications like driver fatigue monitoring, mental health analysis, and e-learning, just to name a few. Deep learning, with availability of medium to large-scale datasets, has really pushed the boundaries in this field over the last few years. In our work, we have considered datasets such as RAFDB, FER+, AffectNet, and FEC. The FEC is a large-scale in-the-wild dataset released by Google. While rich in size and diversity, it does not provide annotations for basic expressions. A noisy training set and a clean test set were curated and released by the authors previously. These datasets captured from uncontrolled environment, also known as in the wild datasets, come with their own challenges, such as variations in pose and illumination, occlusion, and noisy annotations. Ambiguity in annotations causes overfitting or noisy labels, and it seriously hampers training. We plot here the test accuracies of a ResNet 18 model trained on 0% synthetic noise, represented by the blue curve, and another trained on 30% synthetic noise, shown here as the orange curve. As training progresses, the orange curve falls sharply as a consequence of overfitting on the noisy samples. Recent works on this problem use peer training or joint training to handle the noisy label problem. Work such as co-teaching, co-teaching plus, JOCOR employ multiple networks driven based only on clean samples. However, they require the noise rate in advance, which is infeasible in real-world scenarios. Another work titled Noise Concurrent Training does not need to know the noise rate in advance. However, using multiple networks is still a computational burden. Further, these methods are not specific to FER. While there are single network architectures, such as self-cure network, that do not need to know the noise rate in advance, they suffer from self-confirmation bias. Our proposed method neither suffers from self-confirmation bias, nor does it require to know the noise rate. It is a simple framework leveraging data augmentations to handle ambiguous annotations using just a single network. A combination of supervision and consistency loss encourages learning from easy samples as well as hard samples. The effectiveness of the proposed framework is demonstrated through evaluations on synthetic as well as real benchmark datasets. Our work is motivated based on the following observation. Wrongly annotated samples have inconsistent predictions when transformed using different augmentations. This is in stark contrast to clean samples. Clean samples have predictions which are relatively consistent when transformed using different augmentations. We consider two types of augmentations, weak and strong. The selection of clean samples is critical to avoid the influence of noisy labels. Based on our motivation, the Jensen-Shannon divergence between the ground truth distribution and the predicted distribution of the weak augmented image gives an estimate of the purity of the image. But using a lone network to arrive at this conclusion could lead to self-confirmation bias. To overcome this, we incorporate self-ensembling by considering an exponential moving average model for clean sample selection. Prior studies established the tendency of deep neural networks to learn easy samples in the initial part of training and memorize noisy samples in the later stage. With this in mind, we dynamically tune the threshold for selecting clean samples as training progresses. This we achieve by using a Gaussian ramp-up function as shown here mathematically. To classify a sample as clean or not, we use the exponential moving average model theta tilde on the weak augmented image xw to calculate 1 minus Jensen-Shannon divergence of y hat and pw tilde. pw tilde here is the prediction probability of the EMA model on weak augmented images. This gives us a probability. If this probability is higher than a threshold tau, then we qualify the sample as clean. Additionally, to encourage hard sample learning, we introduce consistency loss between predictions of weak and strong augmented images. Let us have an end-to-end look at the model. For each sample X from the training set with label Y, we perform weak and strong augmentations. The augmented images are passed through the single network model to give us prediction probabilities PW and PS for weak and strong respectively. The single network, represented by theta, is updated by backpropagation on the combined loss consisting of supervised loss and consistency loss. This supervision loss is the cross-entropy loss calculated with label smooth ground truth y hat and predicted probabilities. We restrict the supervision loss to samples that are qualified as clean thus avoiding the direct influence of noisy labels. We also use a consistency loss between the strong and weak prediction distributions to encourage hard sample learning. Restricting supervision to just the clean samples and encouraging consistency between PW and PS for all samples protects the model from the influence of noisy annotations. Clean samples are selected as mentioned in the previous slide. The consistency loss here is a symmetric KL divergence to bring consensus among predictions of weak and strong augmented images. Let us have a quick look at the algorithm. We initialize theta. In our work, we use a ResNet 18 pre-trained on MSLab. For each epoch, we sample a mini batch and obtain soft labels y hat for each sample in the batch. We then compute PW and PS. Clean samples are selected based on equations 1 and 2. We then compute the loss as shown here in the equations. If we are still in the warm-up phase, we use only the supervision loss. Else, we use a combination of the supervision and consistency losses. We then update theta and theta tilde. Here are a few implementation details. Phase images are detected and aligned using empty CNN and further resized to 224 by 224. The base network used is a ResNet 18 pre-trained on MSLab. This is appended with a standard dense classification layer. Weak augmentations are based on standard crop and flip augmentation strategy, while for strong augmentations, rand augment based on auto augment is used. Warm-up epochs vary slightly across datasets and Adam optimizer is used. To evaluate on synthetic noise, we polluted the training datasets of RAFDB, FER Plus, and AffectNet with 10, 20, and 30% noise by switching the labels randomly. We then test the model on the clean test set of the datasets. Here, SCM and RR use a single network, and the other models employ joint networks for training. Clearly, other single network models fail to perform as well as the joint network-based methods. Our method, using only a single network, is superior or comparable to NCT, and it outperforms all the other methods. Across all datasets, we observe that as noise level increases, the difference between our method and the second best performing method becomes prominent. To further evaluate the effectiveness of our proposed method, we performed experiments on real-world noisy datasets. Our method outperforms all other methods on AffectNet server. However, our performance is slightly lower compared to NCT on the FEC dataset, which is heavily imbalanced. Methods such as co-teaching plus, NCT, and GeoCR use multiple networks. Impressive results from our single network model demonstrates that our framework endures robustness to real noise of unknown kinds and types. We also test our model on in-the-wild FER datasets. Results here in table 3 shows our model outperforming other single and multi-network models, demonstrating its utility as a general-purpose FER learning framework. Naturally, we were curious as to which expressions were easy to recognize and which were difficult. Confusion plots reveal a lot in this context. Disgust seems to be a very difficult expression across all datasets. It is heavily confused with anger on FEC, AffectNet 7, and FER+. It is quite unsurprising that happiness is the easiest expression to recognize across all datasets. To study the importance of the different components proposed, we plot here the test accuracy on FER+ and RAFDB when trained with synthetic noise of 10, 20, and 30%. The plots have 3 curves. The blue one depicts the baseline, where the network was trained on all samples using only the cross-entropy loss. We observe that as the noise level increases, the performance falls sharply due to memorizing noisy labels. The orange curve here was obtained by using only supervision loss based on clean samples. This curve, while better than the blue curve, has still not used the entire dataset. When trained using the proposed method based on the joint loss combining supervision loss and consistency loss, the performance is much higher. This is depicted by the gray curve. It is quite impressive that the performance using the proposed method on 30% noise outstrips the other curves with 20% noise. This clearly establishes the importance of the different components proposed. Here are some of the referred works.
Yeah, so thank you very much. Let's have any
Opportunity.
few
Be happy
questions.
to answer any questions.
Yes, he is here. Is there anyone who is having any question? Yes, Vikas GN is here. If you have any question, please ask. Okay, so Vikas, one very simple question. You have said that happiness surprisingly is the most easiest expression.
Yeah.
So any insights why?
So okay, to give you a example, I could say that sometimes between disgust and anger, even humans cannot really recognize one from the other. So it is natural that algorithm that we develop is also struggling because the data set that we use inherently could be biased between those two expressions. But happiness, I think universally we could see that somebody is happy if we see a smile on the face. So I guess it's much easier for an algorithm to recognize that.
So is it in general true with the results quoted by others on different data sets, or it is with respect to one data set and with your algorithm?
Most of the algorithms, I believe that they do really well on happiness. And I think this is something general that I've observed over these three data sets that I've seen, not purely with respect to our algorithm, but a lot of algorithms do have issues when trying to distinguish between a few expressions, but the easiest of them seems to be happiness.
And last is that you have used for consistency or the symmetric KLD. So whatever, so have you tried other, measures, or just have utilized KLD?
No, we have not experimented with other types of consistency losses. So we have used symmetric KL divergence for this.
Okay, done. Anyone else? If you have any questions, that's the right time. Else, no one. Then let's thank Vikas for good presentation. Thank you, Vikas. Thank you.
Thank you.
Okay, so now going on to our next presentation, next paper, that is paper number 169. Selective mixing and voting network for semi-supervised domain generalization. Again, it's coming from IISc Bangalore, Ahmad Afurin, along with Soma Biswas madam. Presenting author is Ahmad Afurin. I assume it's again going to be a recorded talk. Let us see.
Yes. It's recorded talk.
It's a recorded talk. Please, sir, start.
Welcome everyone. My name is Ahmad Arfin and I am a student from ISC Bangalore. In this presentation, we will discuss about selective mixing and voting network for semi-supervised domain generalization. Let's start with the content of this presentation. We will have brief introduction about domain generalization and semi-supervised domain generalization, then the literature review, then SMVNet, the dataset that we have used for our experimental setup, results, conclusions, and finally the reference section. Let's start with the introduction. In domain generalization, during training, we don't have any prior information about test data distributions. In many real-world scenarios, we found that annotating the dataset is an expensive and very difficult task. Hence, we have explored semi-supervised domain generalization problem in this paper. In the right top figure, it shows the domain generalization setup where the training set comes from multiple domains and the test set comes from different domain than the training data. The below figure shows the semi-supervised domain generalization setup where the label data comes from multiple domains which are very few in numbers and the rest of the data from those domains are considered as unlabeled data. The test data again comes from the distribution which are different from the training data. Literature review. Domain generalization by solving jigsaw puzzles. Here, domain invariant feature representation of the data is extracted during training using cross-entropy loss. They propose a self-supervision learning of input features by means of solving a jigsaw puzzles created using random pitches on the input image. Meta learning for domain generalization. In this paper, the algorithm simulates the training test domain shift during training by synthesizing virtual testing domains within each mini batch. Domain generalization with adversarial feature learning. This model is based on adversarial autoencoders to learn a generalized latent feature representation across domains. Maximum mean discrepancy measure is used to align the distribution among multiple domains. In this slide, we will discuss about the base model, which is mixture of multiple latent domains. This model consists of feature extractor, classifier, and domain discriminator, as shown in the figure. It performs iterative clustering on the sync style feature of data to effectively divide the samples into the latent domain present in the dataset. It is shown as pseudo-domain level in the figure. The training is performed in an adversarial fashion to learn the domain invariant representation to the combined loss, which are adversarial loss, entropy loss, and classification loss. Despite being extremely effective under fully supervised domain generalization protocol, we observe significant drop in the performance under semi-supervised domain generalization. Hence, it motivates us to build upon this base model to improve the performance in a semi-supervised data regime. In this slide, we will discuss the proposed modification on the base model to make it effective for semi-supervised domain generalization. Basically, it is our SMVNet model. The main challenge for semi-supervised domain generalization protocol compared to the standard domain generalization is the unavailability of large number of label samples. In practice, the size of label sample is very small. Thus, the effective learning of any model under such protocol is majorly driven by the information present in the unlabeled samples. However, our experiment with base model shows a significant performance drop under semi-supervised domain generalization protocol. Hence, we propose two modifications on the base model. One is selective mixing module, another one is voting module. In the next few slides, we will explain in details about these two modules. In this slide, we will discuss about the selective mixing module. We select the easy samples from unlabeled data and use them to further improve the domain invariant feature representation using a mix-up technique. We define the easy samples as the ones for which the base classifier has the high confidence in its class level prediction. From the figure of selective mixing module, we can see that we perform weak augmentation on the unlabeled data and select those samples for which the corresponding confidence is greater than the threshold. For these samples, we perform strong augmentation also. The strong augmentation from these samples and the strong augmentation samples from labeled data are mixed to generate a new augmented data. The mathematical expression for the same is shown in the equation 1, where A is the strong augmentation, alpha is the coefficient of mixing coefficient generated using beta down distribution. We modify the training of the classifier by using a mix-up based cross entropy loss as shown in the figure, where LCE is the standard cross entropy loss. In this slide, we will discuss about the voting module. It has two main functions. It helps in improving the performance of the classifier in recognizing objects from unseen domains by retaining only the class information. Second, during test time, it helps in boosting the correct class confidence for data which are misclassified by classifier. While training the classifier, we additionally construct a binary module which gives the similarity score of the two samples provided as joint input to the module. The output of this module is the similarity score SV, which is given in equation 3. To learn this module, binary cross entropy loss is used, so as shown in the equation 4. Here, YV equal to 1 in case of n and xk belongs to the same class, otherwise it is 0. Thus, for a mixed samples with a different component class, the score SV is low, and for same mixing class, the score SV is high. In this slide, we'll discuss about the training. In addition to the mixed classification loss and voting module loss, we also use entropy loss as we use in the base model. In comparison to base model, we have introduced two other losses, which are mixed classification loss and voting loss. Both of these losses uses unlabeled data, making sure that SMVNet extract as much useful information as possible from the unlabeled data in the training set. We train the SMVNet in an end-to-end manner using combined loss function, which includes mixed classification loss, domain discriminator loss, entropy loss, and voting loss. It can be shown in equation 6. In this slide, we will discuss the inference or test. During testing, we first find the top M class based on the confidence score from the classifier as shown in figure 1. For each of these top M class, we select few samples from labeled training set. P shows the set of randomly selected labeled training samples for all of these top M class. We generate a number of synthetic data by mixing the test sample X test with few randomly selected samples ZI from labeled training set of these top M classes as shown in figure 2. Mathematically, it is shown in equation 7. Next, we pass these mixed synthetic data to the voting module, which gives the similarity score theta V as shown in the figure. We further generate voting score SPC and a voting uncertainty SUC for each class C in CM as per equation 9. Finally, the test time fused score, which will be used for final class prediction, is shown in equation 8, where theta class is the score coming from the classifier. 1 is an identity function or indicator function, which is 1 if the subscript A is less than B, otherwise it is 0. Finally, the class is predicted using argmax of SC, where C belongs to CM, as shown in equation 10. In this slide, we'll discuss about the datasets that we have used. We have used two datasets, PAX and VLCS. PAX datasets has 4 domains and 7 classes. These domains are art, painting, cartoon, sketch, and photo. And these classes are horse, person, house, guitar, giraffe, elephant, and dog. VLCS also has 4 domains: Pascal VOC, Label Me, Caltech 101, Sun 09. The classes in VLCS are bird, chair, dog, person, and car. Experimental setup. All the experiments were performed on AlexNet backbone. PAX and VLCS datasets are used. And for both of these datasets, the unlabeled data presents 95% and 80% that we use for 2 different settings in our experiments. Results. Table 1 shows the semi-supervised domain generalization results on PAX for 2 different setup of unlabeled dataset, which is 95% and 80%. For both of these 2 setups, we can see that our model performs better than the other models by a significant margin. Table 2 shows the semi-supervised domain generalization results on VLCS for the same 2 setup of unlabeled dataset. Here also our model performs better than the other models by a significant margin. Table 3 shows the ablation studies on PAX for photo target domain. Here we can see that our SMVNet, final SMVNet boosts the performance by around 2%. Conclusion. Applying mix-up algorithm on top of base model boosts the performance significantly compared to using base model only. Our novelty module further helps in boosting the performance. It can be seen from table 3 that our Novelty further increases the performance by 2%. Our SMVNet model beats the state-of-the-art model by a significant margin. Reference. This slide shows the references that we have used for our work. Thank you, everyone. We can now move to the question and answer session.
Yeah, anyone is having any question? If you have any question, please ask. In fact, we have several authors. They have done very similar type of work and have utilized almost similar type of losses. So if you have any question, you can ask. Meanwhile, so if you, I guess, is it Ahmad Afrin. So one question is that 2% gain, as you have said that, so how much statistical relevance does this improvement hold?
So it depends from the from the data set, that if we have high number of classes, then and high number of samples in each classes, this 2% can represents a lot of improvement, basically.
Yeah, so but this 2% is with respect to certain data set over which you was working. So is it that the case that 2% there was a significant improvement?
Yes. 2% was actually we have done on 2 data sets. So if we take the on an average, it was 2%. But for some data set, it was we gained around for some settings we gained around 4%, and for some different settings of labeled unlabeled samples we gained around 3%. So on an average, we are saying it is 2, but generally it is for some data set it is better. So it varies from data set to data set.
Okay, the last question is that you have said that the voting modules. So have you checked with there can be so many different voting schemes possible. So have you utilized or have seen that other voting schemes and some voting scheme is preferred, or you just have chosen one and seen that okay, any random scheme is okay?
So for voting, we basically try to check that for which class, for which samples the classifier is not predicting correctly. For those samples only, what we are doing is we are mixing the samples from the training sets, and if both the samples belong to the same class, obviously it should predict, it should give higher confidence. So using that technique, we have used simply.
Okay. Yes, that's pretty much okay from my side. If there is anyone who is having any question, please ask, because anyways we are out of time. Yeah, then let us thank Ahmad Arfin. Thank you, Ahmad.
Thank you, sir.
Okay. Yes, so now going on to our next presentation, paper presentation, which is paper ID 185, a realistic talking face animation with a speech-induced head motion, and authors are from TCS, and Sandik Biswas is the one who is going to present. Yes, Sandik. So it's again going to be a recorded presentation, I assume. Yes.
Yes, it is a recorded presentation. Let me see it.
Everyone, myself Sandika Biswas from TCS Research. I'm working with the Cognitive Robotics group of TCS Research, and my research interests are in computer vision and AI. I am going to present our paper, Realistic Talking Face Animation with Speech-Induced Head Motion. This paper is co-authored with Sanjana Sinha, Dipanjan Das, and Dr. Brojeshwar Bhomik. So what is a speech-driven animation? It is a talking face generation system that mainly takes a speech and a single or few images of a target person as input and generates an animation of the face with lips synchronized with the given speech input. There are many use cases of talking faces or digital avatars. It can be used with chatbots. Speech can easily be generated from text, which can be used to animate a virtual avatar of a person. It can be used in dubbing. If one needs to dub a movie in a different language, then only the mouth region can be animated for the new speech while keeping the facial expressions as it is. It can also be used in a telepresence scenario. In case of limited bandwidth, the face of the person on the other side can be generated only from speech, and it does not need to transmit the whole video. For all these scenarios, it is necessary that the digital avatar looks realistic so that it can be more engaging with the end user. For a realistic face animation, there are certain attributes that a talking face should have. The lip synchronization should be accurate, lip motion should be realistic and plausible, identity should not be distorted or get altered throughout the video. Not only lip motion, but for realistic animation, some natural motion like eye blinks, eyebrow motion should be there. Texture quality should be good, and there should be realistic and speech-related head motions. In this paper, we present a pipeline for talking face generation, which aims to include all these attributes and focus on generating speech coherent head motions. There is a large number of research on talking face generation, but only few of these methods include head motions. The methods which focus on head motion generation can be broadly classified as image-based methods and video-based methods. In image-based method, the system takes a single or few images of the target person and generates animation. Sometimes these methods also require ground truth head poses for an initial small portion of the audio or speech, and using that predicts head motion for rest of the speech. Whereas video-based methods either take sample video of the target person to learn a person's specific talking style, or take a head pose source video to copy the head poses in the animation. As you can see here, the animation video follows the head poses present in the source video. So in this case, the head motion does not correlate with the speech. Our method falls in the first category. So our method is an image-based animation method. So the limitations in the existing methods for talking face generation with head motions are: one is video-based methods require post-source video or sample video of the target person, which is not feasible always at the inference time. Similarly, getting ground truth head poses of a person, which can be used for predicting the head poses for the rest of the speech, is difficult. Also, when a simple sample video of the target identity is used for learning a person's specific talking style, it becomes difficult to generalize for different speeches. For long speech or for different speeches, it shows similar and repetitive head motions. So to overcome these problems, we propose a method for generating head motions that are solely dependent on the audio or speech and do not require any sample video of the target person. We propose a complete speech-driven face animation pipeline with accurate lip sync, natural eye blinks, and realistic head motions. We take a hierarchical approach for disentangled learning of speech-driven motion and motion-induced texture. We first learn all kinds of motions on facial landmarks, and then the landmark motion is used to animate the facial texture. And for head motion, we propose a self-attention based GAN network architecture for generating head motion correlated with the content and prosodic information of the audio. So this is the complete pipeline for our talking face generation method. Speech is taken as input and deep speech feature is calculated from the speech MFCC. First, we predict the lip motion related to the speech on face landmarks using a GAN network. Then we predict eye movements like blinks from noise input using an LSTM network. As blinks are random and not related to speech, we predict it from random noise instead of predicting it from input speech. Next, we predict head motion using a self-attention based LSTM network. Head motion is predicted in terms of R and T, which is applied on 2D facial landmarks after lifting the 2D landmarks into 3D. So after rotating the 3D landmarks using predicted R and T values, it is reprojected back to 2D for texture generation. The texture generation module takes a sequence of predicted landmarks and an image of the target person and generates animation for those sequence of frames. Following are the losses used for training each of the submodules. For lip motion, we use distance loss, which is supervision between ground truth and predicted landmarks. Along with that, we also use a direction loss, which captures the direction of lip movements, and also we use a temporal loss. For blink generation, we use MMD loss to learn the eye motion in unsupervised way. This loss matches the distribution of eye landmark displacements in ground truth and prediction. For head motion, we use supervision on R and T values. The self-attention layer predicts an attention value for each of the frames in a window, and it gives weightage to the predicted RT values. For the frames with low attention, it takes a neutral position of RT, which is basically a frontal face. For head motion, we also use a temporal loss on the attention between consecutive frames. For texture generation, we use pixel loss and perceptual losses and along with the GAN loss. Texture generation network is trained using MAML and requires fine-tuning for new subject using a few sample images of the person. For more training details and network architecture, please refer to the paper. These are some qualitative results.
Well, the way that Nick works was very different from how I had worked before. It was extremely close, and we were going off instincts the whole time. We would change things along the way, and he allowed me. I never felt this much freedom on a.
It was great. I went to film school at USC, so I had directed some, but not episodic. So I was really excited to get to do it before we finished. It was hard for both Angie and I because we are in the show so much that it's hard to get us out to actually direct and not write us in. So, but they did it.
You know, big job, and it was a big job, was a Toronto production of Godspell, and a lot of really great people ended up being in that show as a first job ever. Myself.
Hi everyone, and welcome back to Pronunciation with Emma. In this video, I'm going to take you through the British phonemic chart and how to pronounce the vowels. Now, undoubtedly, the one thing that people struggle with when they're learning English is the pronunciation, in particular, the vowels. They are tough, and a lot of them sound very, very similar to some speakers of certain languages. Now, there are 12 monothons to go through, so make sure you stay until the end of the video. Don't rush through this. Take your time. It's going to be a short video. Just focus on your pronunciation just for a couple of minutes. I've also created a British phonemic chart just for you, completely for free. The link is down in the description. Download that and then watch this video, and it will help you remember the symbols and the sounds, and you can start practicing at home completely for free. So let's begin with that first sound.
A kingdom of isolation, and it looks like I'm the queen. The wind is howling like this swirling storm inside. Couldn't keep it in, heaven knows I tried. Don't let them in, don't let them see. Be the good girl you always have to be. Conceal, don't feel, don't let them know.
Quantitative results, we evaluate our generated videos from different aspects like head motion quality, for which we use canonical correlation analysis and histogram similarity to compare the predicted with ground truth head pose distribution. To evaluate texture quality, we use structural similarity. For blurriness, we use CPVD, and for fidelity, we use FID and DISTs. To assess identity preservation, we use FaceNet network, which is basically a face recognition network, and compare the features of FaceNet for ground truth and predicted faces. Also, we use a cosine distance between ground truth and predicted face images. For lip synchronization, we use landmark distance and audiovisual synchronization metrics. And for blink, we compare the statistics of blink, like frequency, duration of blinks in ground truth and predicted sequences. We have evaluated 3 different data sets like VoxelLab 1, 2, and LRS TED, which mostly contain videos from talk shows or interviews. In all the metrics, our method gives comparable or better results than the existing methods. For head motion, our method shows better performance than that of the other existing methods. We also perform an ablation for different loss or architecture choices. Using self-attention improves head motion patterns and gives better quantitative results on all the datasets. We also show ablation for texture generation. We compare the animation results for different values of K, where K is the number of images of target subject used for fine-tuning the texture generation meta-thread network. For K equals to 30, we get the best texture quality. We have also performed an user study. 26 participants have been asked to rate 20 videos generated from different methods, including ours and also the state-of-the-art methods. For realism, our videos get much higher rating than the state-of-the-art methods because the state-of-the-art methods texture quality is not good and identity also gets distorted in most of the methods.
Thank you very much, Sandika. Is there anyone who is having any question? So I may be having one or two quick questions. Sandika, are you there?
Yes. Okay. Hi.
Okay. So good work. In fact, I have seen your demos as well, and most of them you are comparing with 2020 and 2021 multimedia as well as CVPR papers, ECCV papers, and your performance seems to be good. One question is that when you add head motions, so have you also must have seen the type of artifacts which are going to be introduced? So are they also going to be affecting the realism or hamper sometimes?
Yeah, what I feel that still there is a kind of a lack of temporal smoothness in the head motion, which may affect the realism thing. So here in this case, we have not considered a temporal architecture or something like that in the texture generation network. We have only considered that in the landmark part. So I believe that if we can include that part in the texture generation as well, that will improve the temporal smoothness thing and also the realism. That's it.
And so right now it is in English. So I assume that suppose that you want to change the language to Hindi, what where we need to tweak and change the things.
Actually, the thing is that is why we are using deep speech features instead of using the MFCC, which generally in the state-of-the-art methods have been used. So in deep speech feature, it can work well on the other languages also and on other accents as well. Yeah, it can work on different languages along with English.
It does. Is it mean that directly we can use your proposed complete end-to-end pipeline to generate things in which avatars are speaking Hindi?
I won't say that it will perfectly work on different languages because I believe that the deep speech network also uh, uh, does not include much data from other languages. So maybe a fine tuning of that deep speech and as well as our network will be required for the other languages, but it can work on other languages as well.
Yes, and the last question is that how much amount of time does it take? Is it that it can be done in real time?
The inference, the prediction thing.
Yes.
Yes,
So
it has a lag of 3 seconds because the model loading and also some pre-processing is required, and also in DeepSpeak there is some constraint that it requires a minimum number of frames to process. So uh, uh, in terms of seconds, it has a lag of 3 seconds approximately.
thank you. Yeah, thank you, Sadika. And I like your final future challenge, which is that including the emotion and emotion-based speech as well as rendering of face motion, lip
Yes.
sync, and eye blinks. They are very important.
Yes.
So that's going to be your next phase. This is good. So I am done. If there is anyone still wanted to ask any question, it's open. Else we are going to our final presentation. Anyone?
Yes, sir. Actually, I'm from
Sonia. Yes,
so
Sonia Das.
Priyanka Saxena. Hello.
Okay. Yes, yes, we can listen, Priyanka. Please carry on.
So I'm PhD student at IIT Jodhpur. I had one question in your work. So as you showed the results in that, there was a slight observation that the lip movement was not synchronizing with the speech. So
Yeah.
so
Yeah,
what?
so I believe that is because of the internet. I think, yeah, I also feel that there was a lag and some mismatch the lip sync and the picture.
Okay, so
But
what methods, maybe in future work that might be improved? So,
yeah, so method wise, I'm not saying that the lip synchronization fully accurate, but what I felt in this video, it is not like that. I believe because of the internet lagging thing, maybe that mismatch is coming.
okay, thank you.
Okay, thank you, Priyanka, and thank you, Sandika. Yes, so we are done with this. Thank you, Sandika. Next, so finally, we are going towards our final last presentation of this session 3A. That is paper ID 193, discriminative multi-scale CNN network for smartphone-based robust gate recognition. It's going to be Sonia Das, NIT Rourkela, and she has published along with Sukhdev, Upendra, and Kumar Sahu. Yes, again, it's going to be an online presentation. Is going to start. Yes.
Is it visible, sir?
Yes, Sonia, your voice is we can listen, but you cannot see your screen. Are you going to present?
Yeah, but has
Yes.
it been shared? I'll just
Yes, right now I cannot see.
just a minute, sir.
Yeah, it's coming. It's coming. Yes, now it is visible, and you can make it full screen and it starts. Sonia.
Okay,
Yeah.
okay, sir. Okay, sir. So, okay. Hello, everyone. This is Sonia Das. This is scholar at National Institute of Technology, Rourkela. I'm presenting on discriminating multi-scale CNN network for smartphone-based robust gate recognition. The outlines are the problem statement, related work, proposed approach, experimental results, and summary. So comes to problem statement, different covariate factors affect the gate sequences of data. So before that, a VIP lightning on gate-based recognition. So what is gate? Gate is a way of walking of an individual which is dynamic in nature. So why is gate useful biometrics as compared to other biometrics? Due to its non-intrusive nature, which makes it suitable for security and surveillance. Also, user consent is not required. At the time of monitoring in surveillance, it does not require user cooperation. So, but our paper is smartphone-based gate recognition, because currently smartphones feature with many advanced inertia sensors at an affordable prices. So these sensors are accelerometer and gyroscope. It captures accurate motion patterns of a moving object along X, Y, and Z directions. So basically accelerometer tells speed and gyroscope tells motion pattern. So here capture accelerometer data and gyroscope data along X, Y, and Z directions. So it is very both devices are very convenient. So it is useful to track the person in surveillance with fewer concern. So conditions that affect the walking patterns are mainly carrying the objects when walking, different clothing conditions, shoes, speed. Apart from the main covariates, there are also some covariates which are changing the load from one hand to other hand when walking, or placing the mobile at different positions, like from back pocket to the front pocket when a subject is in a surveillance, then falling at the time of walking. So these leads to an erroneous patterns in the gas sequence of data. So few walks are also there, has been done. So mostly walks are done based on single sensor based and multi-sensor based data. At the nickel used single sensor data, that is accelerometer. On 2011, he adopted a machine learning approach taking acceleration data and classified using XBM technology using multiple voting scheme. In 2012, Jufei and other others employ discriminative Veblen transform for featureize the acceleration data and adopted SBM for classification. And there are also several multi-modal sensor-based works have been done. In 2018, the CNN feature extraction methods are used for local features, for getting local features, and SBM for classifications. In 2016, Fing and others employ RNN technique for getting global features. As GET is a sequential in nature, therefore it is suitable for the capturing GET patterns for identification. However, this method fails at the presence of different covariance factors. In 2020, the authors used both CNN and RNN technique to get features for better accuracy. Even though those methods show good recognition rate, their average recognition rate is not at all that promising. That means both are using in 2020. This is 2020. Yes, the deep learning approach, it achieves good result on the presence of different covariate factors. But to give more efficiency, so we are proposed the discriminative method, which indicate to handle the covariates factors. So the proposed approach is an multi-scale CNN network is designed to extract discriminative local features. Yeah. In particular, CNN operates on multi-scale signal to handle covariance-based variation effects and highlights the significance of local features with respect to class-specific GET patterns by incorporating the class-specific weight update subnetworks, which is nothing but the virtual networks. Further, these localized features are passed through a fusion network to access. Then last, the feature vectors are flattened to 1D feature and then again fed to a fully connected layer and subnets layer for classifications. Here the accelerometer data, that is along X, Y, and Z direction, and gyroscope data are simultaneously considered as inputs. After combining all the sensor data for every walking cycle of a subject can be represented as X. And the total, where N is the number of time steps in each segmented GAT cycle. So here, each input data is downsampled by multiple different scales, that is tau. That is, we are taking 3 different scales with respect to original input dimension N. Then each multi-scale sample is obtained by averaging the conjugative data points as given in the equation, where st of tau is the downsample signal of the input signal x of I at time index I with a scaling factor tau, and t is the number of data points. Then the 1D, here we are using 1D convolutional operator, means 1D CNN, and each set of data is some sample at time step t to capture features and form a set of feature maps that is denoted as f of tau. And we are taking here 4 feature maps. Then our proposed is to localize the feature maps so that we can detect the covariance effect, and according to that covariance effect we give the weights. So discriminative feature analysis is obtained through that. So the class specific weight update network is inserted between the last convolution layer and the classifier.
So Sonia, last 5 minutes.
Okay, sir. In each scale of CNN, that is the f of tau is the feature map of the last convolution layer is processed through the pooling layer consisting of local feature vectors, and here W is the weight vectors, that is W1, W2, Wk, each column corresponding to a class. A localized classification is performed using dot product between the feature vector and the classifier weights. The information of each feature vector is computed in terms of prediction scores of the K classes. And here the class probability is obtained through the entropy based pooling mechanism. A small entropy indicates that features are highly correlated to the training sample, and a large entropy specifies misleading feature vectors that are affected by the covariate factors. Then the training we are using through several epochs and using cross entropy loss function to estimate the model parameters. And on the results, we are through the multiscale CNN. First, we are using several challenges data sets, and one is OUSIR dataset, which is captured at Osaka University, Japan. It is the large population data set capturing inertial sensor-based GAT data. Then GAT MOBO-SCC data set. It incorporates 8 types of covariates along with the speed variations. And others are WHO and IDNet data set. IDNet is having different SUGS type of covariates, and WHO GAT is the normal GAT data, the normal walking. So the multiscale or the first I am comparing with the multiscale. We are comparing with the multiscale CNN, which achieves better results than other, and moreover, giving weights to the each multiscale signal enhance the recognition accuracy. Here also CNN also gives better results because it captures the local features through the data set, and our method also achieves best. And the LSTM is not capturing well because it captures the global feature vectors. About the summary, the novelty lies in the feature extraction process, and a discriminative approach explores the classification ability in terms of feature weighting mechanism. That's all. Thank you for listening.
Thank you, Sonia. Thank you very much. Is there anyone who is having any question? Yes. From IT Jodhpur side, is there is someone who wanted to ask any question? Any research scholar? No. Okay. So Sonia, I have maybe my first question is that as you have also said, and we have also seen that such type of networks also got overfitted over pocket-based scenarios, that if you place it in the front pocket or the back pocket and so on. So is it the case with you also that you have seen that such type of overfitting happening?
Yeah, absolutely. Means actually the smartphone captures the rotation pattern of a mobile, and as the mobile is just in the pocket, so it just tracks the persons of a on one side only, means the right hand side and the left hand side. But pardon, sir, what actually the question?
The question
Hello?
is that, as you understand, yeah. So the question is that that if your assumption is that mobile movement is equivalent or going to somehow render the human gait, but several times that mobile motion is going to be coupled with the pocket in which you are placing, or the way. Suppose that you are holding it on your hand. If you are holding it in your front pocket or the back pocket, so depending upon that, gate is also going to be artifacted. The point is that several times it has been seen that depending upon the pocket or the way you are holding, things got overfitted into that.
Yes,
Have you also seen such type of scenarios in your data? Yes.
yes, absolutely, sir. Actually, we are taking a right side pocket only, and all the data set, and actually, I have also taking some data set by own that are also taking a particular constraint that holding the mobile at the right hand side pocket. If it has been changed, then the scenario has been changed. So.
Okay, so it is that right now you'll have to place it in some fixed pocket, which is
It's his pocket.
fixed pocket. So it may happen that got overfitted into that, and if somebody is holding it into some other location, it may not work. Fine.
Yes, sir. But in our case, if one is has to usually put the mobile in its right hand side, but for some call, it will be take uh, it will take for the holding the call, and again comes to put in the pocket in the same side, then it will be taken as it as a covariate based signals. Then it makes it a low weight to this signal. You just make it a means just discard these factors at the time of continuous tracking of a person at that time.
Okay. Okay, so thank you very much, Sonia. We are done with all the this 3A sessions presentation. Thank you. Thank you very much to ICVGIP team for
you, sir.
conducting this online thing in the best possible way. Thank you.
Thank you, sir.
Right. So, on behalf of organizing committee, I thank Dr. Aditya Nigam for chairing this session. We will break for lunch now, and we will reconvene at 1:45. So we have a lot of interesting things happening in the next half. There is oral session at 1:45. Sorry, 1:30 actually, right? So it's not 1:45. 1:30 oral session, and then Vision India, a lot of exciting papers there at 2:30, and then contest, and followed by Best Dissertation Award talk. And then we will be closing. So a lot of exciting things. Please join post lunch. Thank you.
Hello, Dr. Venkat.
Hi, Anand. How are you?
Hi. So, yes, I think few speakers are already there, but we will wait for 2-3 minutes.
Sure, Anand.
Okay, welcome back after lunch. We are now going to start a post-lunch session. And in this first, we are going to have an oral session with 4 papers. Dr. Venkat Ramna from Samsung, he will be chairing this session. Over to you, Dr. Venkat.
Oh, thank you, Anand. Welcome to all the presenters and the attendees. And I think in this, majorly we are looking into the papers which are exploring the GANs with respect to video generation, reconstruction, and how feature engineering can also help in various applications. So we look forward to presentations from the presenters. And shall we start, Anand, then, with the first presentation?
Yes, sure. So, yeah, maybe you can read out the first paper. Yeah.
Okay, so the first paper by Varshniya and team, teaching GANs to sketch in vector format. So let's start and request you to abide by the timing.
Yes.
So 12 minutes plus 3 minutes per question.
Yes, so this will be a recorded talk. Let me share the screen.
Okay, sure.
Greetings to one and all present here. Generation in vector format. Greetings to one and all present here. I am Vashneya and currently working as an R&D scientist at Honeywell Technology Solutions. Today, I will be presenting our work, Teaching GANs to Sketch in Vector Format. This is done jointly by Dr. S. Balasubramanian, Dr. Vineet N. Balasubramanian, and myself, when I was a student at my alma mater, Sri Sathya Sai Institute of Higher Learning. I would like to first present the motivation for our work. Since time immemorial, sketching has played an important role in human communication much before languages were developed. Even to this day, sketches are used to represent abstract concepts like circuit diagrams, path trees, and architectural designs. Today, deep neural networks perform state-of-the-art in many vision tasks such as image generation. But this generative ability of deep neural networks is limited to raster images. There are only a handful of work that discuss sketch generation in vector format, and most of them are based on VAEs. Currently, there are no GAN-based architecture for sketch generation in vector format. In this work, we focus on developing GAN architectures that can generate sketches in vector format. I would now like to present the related works on GANs for generating sketches in raster format. The work towards realistic face photo sketch synthesis via composition-aided GANs propose a novel CA GAN for generating sketches of human faces given their digital portraits. Recent work such as Doodler GAN also considers sketches in raster format. Doodler GAN models the process of sketching as generation of parts or portions which make up the whole sketch. Since these parts are predetermined, it would be mandatory to specify them for generating sketches of other categories. This requires manual intervention, thus making it hard to generalize across different categories. I would now like to present the existing works of generating sketches in vector format. The first attempt in this area was by a blog titled Recurrent Net Dreams of Fake Chinese Characters in Vector Format. This generated kanji characters in stroke-based format using a two-layered LSTM. Following this was the SketchRNN, which was proposed in 2017 by Google Brain. SketchRNN is a VAE architecture with a BiRNN as encoder and RNN as decoder. This was trained on PicTraw dataset. This is the state of art in generating visually appealing sketches for unconditional generation, conditional reconstruction, and completion of incomplete sketches. The sketches were not visually appealing when a mix of categories was used for training. In order to overcome this difficulty, Sketch Pick2Sec replaced the BiRNN encoder with a CNN and eliminated the KL divergence loss. Since the convolution is spatial, the input to this model is rasterized format of sketches from the PicTraw dataset. Based on the Turing test, the authors of this paper concluded that Sketch Pick2Sec outperforms SketchRNN. All the architectures mentioned for sketch generation in vector format are majorly based on VAEs. A well-known disadvantage of VAEs is that they tend to produce blurry raster images. Since there is no concept of blurring in vector images, stroke-based sketches produced by VAEs like SketchRNN tend to draw smoother and more circular line segments that resemble an averaging of many sketches in the training set. This phenomenon has also been discussed under the model limitation sections in the supplementary material of the SketchRNN paper. We would like to call this as the scribble effect. The figures shown here are scribble effect observed in yoga poses and mosquito sketches generated by SketchRNN. It is well known that GANs produce sharper raster images. Hence, this motivated us to come up with a GAN architecture which would be described in the upcoming slides. Our contributions are as follows. We have proposed a standalone GAN architecture called the SkiGAN for generating sketches in the vector format. To the best of our knowledge, this is the first GAN architecture to do so. SkiGAN also models the natural sketching process. We also propose a hybrid VAE GAN architecture called the VASCI GAN for fair comparison with SkiGAN. We also compare our models with SketchRNN on visual quality, training complexity, scribble effect, and other ablation studies. The problem setup and assumptions are as follows. The sketches are represented in the vector format as a phi tuple, delta x, delta y, q1, q2, q3. Delta x, delta y are the offsets in x and y axis respectively, and the drawing is assumed to start from the origin. Delta x, delta y are modeled as GMM for SkiGAN and as IIDs for VASCI GAN. Q1, Q2, Q3 are the pen states and are modeled as categorical random variables. Tau is a real number between 0 and 1 and controls the randomness of the variety in sketch generation. It's also called as the temperature. We propose a novel coupled generator G tilde, G hat, trained with a combination of standard adversarial and policy gradient losses. This generator is modeled to mimic the natural sketching process of humans, wherein the current pen state is dependent on the current offset and the previous pen state, and the current offset depends only on the previous offsets. G tilde generates offsets which are continuous random variables and is trained using the adversarial loss. G hat, on the other hand, generates pen states which are discrete random variables. These discrete outputs pose a difficulty for the gradient updates to be passed from discriminator to the generator. Hence, G hat is trained using the policy gradient loss. Both G tilde and G hat are LSTMs. Coming to the discriminator, D is a bi-LSTM which takes in a batch of fake 50% fake sequences and 50% real sequences to predict whether each of them is real or fake. D is considered to be the ideal reward function as it improves every iteration due to training. Hence, the action value function of G hat is defined as follows. Since D can give a reward only for a complete sequence, we perform Monte Carlo rollout to determine its reward for an intermediate sequence. Since there is no intermediate reward for an incomplete sequence, the objective of G hat is to generate a sequence from start state that can maximize the expected reward given by J of theta. The gradient of J of theta with respect to theta is defined by this equation. Using likelihood ratios, the above equation can be approximated as follows. The parameters of G theta are updated by gradient ascent, and those of G tilde and T are updated by gradient descent. Pen state outputs, mixing weights, and variance parameters of the Gaussian mixture model are scaled by tau to control the level of randomness in the generation. Since VAEs are good at representing data in latent space and GANs at generating data, we propose a VAE GAN-based architecture called the VASCI GAN. It has been observed in raster image datasets like CELIB A and labeled phases in the wild datasets that VAE GAN architecture alleviates blurring of generated images. Hence, we hypothesize that VASCI GAN will alleviate scribble effect in vector sketches as well. This also becomes a GAN architecture for fair comparison with SCI-GAN. Encoder is a bi-LSTM and it is trained with KL divergence and reconstruction loss. Decoder, which is also a generator, is an LSTM and is trained with a combination of KL divergence, reconstruction, and adversarial losses. The discriminator can be a GRU or a LSTM, and it is trained with the adversarial loss. We present sketches generated by SCI-GAN and VASCI-GAN in the following slides. For our experiments, we took 4 categories of sketches: cats, mosquitoes, yoga poses, and fireworks from the quick draw dataset. Let us now look at the sketches generated by the SCI-GAN. For unconditional generation, all the sketches are generated with a single start tuple. Sketches are generated until the pin state Q3 equals 1 or until the number of tuples generated becomes n max. If one notices the figure to the left, the sketches to the left of the line separating it are those generated after the pre-training, whereas those on the right of the separating line are those generated after training. Their visual appeal favors the combination of adversarial and policy gradient losses. The figure to the right shows the extrapolative abilities of SCI-GAN. We feed in a partially drawn sketch to observe how trained model can figure out various endings for the incomplete sketches. The complete sketches are indeed meaningful and visually appealing, thereby highlighting the creative aspect of SCI-GAN. We now present the results of VASCI-GAN with GRU and LSTM discriminators. The trained VASCI-GAN model is allowed to generate sketches after being conditioned by a sketch from a particular category. The sketches are indeed meaningful and visually appealing for both the discriminators. The 2 figures at the bottom show results on transfer learning. The weights of the model trained on cat sketches are transferred to train 2 different categories, namely big and aeroplane sketches. This shows that VASCI-GAN is able to transfer the sketching knowledge across different categories. Please do note that the transfer learning on SCI-GAN leads to mode collapse, which is a direction of future investigation. Here are the average scores of visual appeal given by human subjects. The scores of ski-GAN are closer to those of SketchRNN but outperforms VASCI-GAN, thereby emphasizing the importance of the combination of adversarial and policy gradient losses. I will now present the ablation studies performed on the proposed architectures. First, we study the effect of temperature tau on the sketches generated. For this, we set the tau to the values of 0.2, 0.4, 0.6, 0.8 and 1.0 and study its impact on the sketches. One would notice that for both unconditional generation of ski-GAN and conditional generation of VASCI-GAN, as the temperature increases, the randomness or the variety increases. This is due to the fact that the higher value of tau leads to a greater influence of variance on the generation of offsets and pen states. Based on visual appeal, we find that tau equal to 0.4 is ideal for sketch generation as there is a good balance between creativity and generating meaningful sketches. In order to understand the effect of policy gradient loss on training, we weight the policy gradient loss and analyze its effect on the sketches generated. One can observe that both policy gradient loss and adversarial loss must be weighted equally to get visually appealing sketches. To understand the effect of weighting KL divergence loss, we assign the weights 0.25, 0.5 and 1.0 and analyze the quality of sketches generated. Visually inspecting these sketches, we conclude that 0.5 is the ideal weight for KL divergence loss irrespective of the type of discriminator. In conclusion, we propose two GAN-based architectures for sketch generation in vector format, namely the ski-GAN and the VASCI-GAN. We also effectively model sketching process and propose a combination of policy gradient and adversarial loss for training. Ski-GAN generated sketches better than VASCI-GAN and has a faster convergence in terms of training. Both ski-GAN and VASCI-GAN minimize the scribble effect and converge faster than SketchRNN. Thank you.
Thank you, Varshiniya. Okay. So with respect to your losses, so is there any other losses you tried other than this, what you mentioned?
No, so we did not experiment with any other types. So for the ski-GAN, we experimented with the policy gradient and adversarial, and for VASCI-GAN, the KL divergence and the adversarial loss.
Okay. No, like, did you try for VASCI-GAN the other loss, what you tried in ski-GAN, policy gradient? Okay, L divergence.
We haven't done that. I think that also would be a good extension.
Okay.
But just that the VASCI-GAN needs to be modeled as a coupled generator like a ski-GAN. So in ski-GAN,
Okay.
we had two small generators inside the bigger one, and
Mhm.
we trained the ones that generate the discrete random variables using policy gradient and the one with continuous random variables using the adversarial. So similar way, I think we could also do it for the VASCI-GAN as well.
Okay. And in terms of computation complexity, how does it fare?
So what we have observed is ski-GAN converges faster than VASCI-GAN, and both of them are converging much faster than SketchRNN.
Mhm.
That has been our empirical experience.
Okay. How fast did you quantify?
I think I have the number. It's in the paper.
Okay. Okay. Fine. And how about like in terms of when you're deploying it after the trained model, in terms of computational complexity, how it fares with respect to SketchRNN?
I think the forward pass after the training would be comparable. I mean, I don't see much speed up in that case, but the training wise, the convergence is quite faster.
Oh, okay, got it. I think Shanmuga, you have any query?
No, I don't have.
Okay, okay, fine. Any other queries, Anand? Other attendees? Do we have? Otherwise, we can move to the next paper.
Sure.
Okay, thank you, Varsniya and team.
Thank you very much
For
for the
nice work.
opportunity.
Right. Okay, so let's move to the next paper, HDR video GAN, deep generative HDR video reconstruction by Mrinal Anand and team. I request Mrinal present their work.
And this will be a recorded talk. So
Okay.
let me share the screen.
Okay, sure.
Hi, I'm Nathan. I'm currently a PhD student in the Computer Science Department at the University of Colorado Boulder. I'll be presenting HDR Video GAN for deep generative HDR video reconstruction. This is a work that was done during my undergrad at IIT Gandhinagar with my colleagues Mrinal Anand, Chandan Kumar, and Dr. Shanmuganathan Raman. The dynamic range that we as humans can experience is vast in the real world, but unfortunately, most off-the-shelf digital cameras can only capture a limited range of the illumination in the scene. Now, for a fixed setting, you either get an overexposed image, like in the middle column, or an underexposed image, like on the right side. Now, an HDR image on the other side is a much better representation of the natural scene, as it preserves the details both in the brighter areas and the darker areas. Now, there's a lot of work that is going on in HDR imaging. One of the main ideas is where you try to fuse overexposed and the underexposed image and reconstruct the HDR image. Now, reconstructing HDR video, on the other hand, is much more challenging task. And due to the underlying complexity, it has received a very less attention. And that is our motivation behind developing HDR video GAN. So starting off with the data set, we utilize publicly available data sets. They were curated back in 2014, consisting of numerous HDR videos. We synthetically generate LDR frames from the HDR2 frames. And in an alternating exposure strategy, where the neighboring frames have different exposures, one being low and other being high. And the goal is to, using the alternating exposure LDR frames, to generate the corresponding HDR frames. Now, starting off with the first component of our HDR video GAN, that is LDR denoising. Now, the real world off-the-shelf cameras are prone to capturing noise while recording the LDR frames, and they'll end up generating artifacts if you try to reconstruct and corresponding HDR frame from the noisy LDR frame. So this is a very crucial component to remove the noise from the LDR frames. For this, we use a unit architecture and which is trained in a self-supervised manner. And it from the given noisy LDR, it generates cleaner LDR frames. The second component of HDR video GAN is optical flow correction. So in video-to-video synthetic synthesis tasks, there is a lot of objects that moves across frames, right? And for generative models, these object movements are prone to generating temporal artifacts during the reconstruction. So maintaining a temporal coherency between frames is important. So we address this using light flow net, which is fine-tuned to compute the optical flow maps between the consecutive LDR frames. Using the computed optical flow maps, we try to align the neighboring cleaned version of LDR frames. Now, the third component is the actual reconstruction. Using the cleaned, optically aligned LDR frames, the generator reconstructs the corresponding HDR frame. And the generator consists of encoder-decoder kind of architecture, incorporating many residual blocks in between. And the final part is the actual adversarial training. Whereas in which the discriminator tries to discriminate between the fake example that's what's been reconstructed from the real ground to HDR frame. Moving on to the objective functions, HDR video GAN is trained on multiple objectives. First of which is tone mapping. So it is being observed that the loss function in the linear SDR domain underestimates the error in the darker regions due to the relatively lower values of the pixels. Now, maintaining the consistency with the baselines, we compute our losses on tone mapped HDR frames by converting our HDR from the linear domain to the log domain. The second objective of the overall objective function is the actual adversarial objective. Now, rather than using the conventional adversarial laws, we rather discriminate the ith reconstructed SDR frame from the previous, that is I-1 with ground true frame. Now, this slight modification is observed to generate frames with much lesser flickering artifacts and generally much better frames with improved visual quality. Third is since generative models like GANs are prone to generating visual artifacts like blurriness and color mismatch, we incorporate content and style loss off of the pre-trained VGG90. And finally, also by including the L1 as the reconstruction loss, we get the overall objective, a weighted version where each of the objective are weighted. And this overall objective is what the HDR video GAN is being trained on. Moving on to results, we perform our approach with Kalantari et al. 2019, which was state of the art at the time, and a previous work by Kalantari in 2013. And we measure on metrics such as PSNR and SSIM, which are common photometric visual metrics. And we also evaluate on SDR-VDP2, which is a visual metric specifically focused on computing the visibility score between the HDR frames. HDR video GAN is observed to outperform the state of the art in both in terms of empirically in over all the metrics, and also in terms of visual comparison. On the right side, we have the ground true HDR frame from one of the test scenes. And on the bottom left, we have the state of the art at the time, the Kalantari et al. 2019. And we can see, and since this is a frame which has a lot of motion that is going on between the scene, Kalantari et al.'s work, the reconstructed HDR frame has a lot of tearing artifacts in between them. And HDR video GAN, on the other hand, produces much more smoother and crisper frames with improved temporal coherency. More results. This is one more frame from a video scene in the test set. Improvements is observed in terms of details, both in the darker areas, brighter areas, while also improvements are observed in the actual object boundaries. Last but not least, ablation study on the denoising network. Removing the denoising network, it is observed that the model ends up generating frames with much more graininess in between them, with a loss in the actual object boundaries. Incorporating the denoising net is, we observed improvements both in terms of visual quality, of course, and also over all the metrics. For a better understanding, deeper understanding of HDR video GAN, please check out our paper. Thank you.
Thanks a lot, Nidin. Is that Nidin who presented? Nidin and Shanmuga?
Yeah, there is another person called Mridal Anand, who is the first author.
Okay.
He's available for any
Hello.
Q&A.
Oh, okay. Cool. Thanks a lot, Mrinal and team, for presenting the paper. So I have a few queries. So did you check with respect to the different losses? You have different weightages. under your ablation study, which loss was playing a very critical role in enhancing this metric?
Um, uh, Unable to unmute.
Please unmute, technical team.
Anand?
Yes, I'm asking IT team to unmute. You can speak, right? Hello?
Hello.
Yes, we can hear you.
Yeah. Hi. So, answering to your question, the main loss function was the adversarial loss function. That was the crux of this work. So initially, we experimented with discriminating with the current frame only, but what we found was that there was a work which proposes discriminating with the previous frame. So this idea of previous frame definitely increased the temporal coherency and reduce some of the artifacts. So I would say the backbone of our work would be the adversarial losses that we used, and in addition to that, the ELDR block is this two-stage process of using this adversarial blocks are also very crucial in our work.
Okay. And I saw that you prepared the data set by doing the downsampling of the HDR video frame, right, to generate the LDR frame.
Yeah.
And maybe you have some augmentations also as part of that. What
No,
are
so
the, do you
we
have
didn't
any?
use the augmentation for the proper comparison with the baselines. There was some predefined techniques that was mentioned in the baseline paper by Kalandari ETL. We just verbatim followed that technique for the dataset generation.
Okay. My question is more on the lines of how scalable is it for real world? Like,
Yeah, so
does it
coming
have
to
any
that point,
dependency on the data set generation, which you
yeah,
have
so
described?
coming to your point, the model proposed is very scalable. So why I'm saying is this, the motivation behind using LDR blocks was to just uh, reduce uh, the natural noises that gets added to an image while capturing the photo. So depending upon a scenario, if I am able to compute what could be a standardized, if I can basically get what kind of a noises there are present in a particular frame or in a scene, I could use that to fine tune my self-supervised network, and uh, based on that you can get a clean HDR frame. So this particular technique is inspired by a paper called a self-supervised approach for adversarial robustness. So they showed that using this two-stage processes, they are getting a high adversarial robustness. So we also thought that in our case also, when you click images in the real world, there must be some noises present in the external environment, and we can fine-tune this ELDR block at the starting to get very clear LDR frames. So yeah, in case of adaptability, I think our model is very adaptable.
Okay. Any others have any questions for Mrilan, Anand, and team? Okay. So thanks a lot, Mrilan and team.
Yeah,
Thank you.
thanks.
For
Thank
good
you.
work. Move to the next paper presentation. Exploring wide GANs with complementary feature learning for video generation by Sonam Gupta and others. Request Aarti will be presenting, I think,
Yeah.
for this. Okay, please go ahead, Aarti.
Is my screen visible?
Yes, you can
Okay,
see.
thanks. So, hello everyone. I'm Aarti Keshri, presenting on behalf of two other co-authors from VP Lab, Department of CSE, IT Madras, India. So, we will present G3N++ exploring wide GANs with complementary feature learning for video generation. So, here the task is unconditional video generation, in which the input is a noise vector which is sampled from standard Gaussian distribution. And this input is then fed to a generator. This generator performs a series of transformation on the input noise vector and gives a video which is coming from the underlying training data distribution. So existing methods tries to solve this task. Like VGAN tries to decompose the video into foreground and background. VGAN uses 3D transpose convolution to solve this task. And another work, TGAN uses two generator networks, and one temporal generator network generates the noise vector corresponds to each frame of the video, and these noise vectors are then fed to image generator, and these image generator generates each frame which is corresponds to the input noise vector which is generated from the temporal generator. So to reduce the complexity of the task, some other methods like MocoGAN and G3N tries to disentangle the video into content and motion. So MocoGAN is architecturally similar to the TGAN. Like TGAN, it replaces the temporal generator of TGAN by GRU and also disentangle the video into content and motion. And G3N proposed a three-branch architecture in order to disentangle the motion and appearance. These architectures are responsible for temporal, spatiotemporal, and spatial aspect of the video. So existing method fails to generate a realistic video, as we can see here. So what we can do to solve this problem is, the first thought we will have, like, we can make the network deeper or wider. So how we will make the network deeper? We can add more layers to the network, and by in order to make the network wider, we can add parallel branches to the network. So one underlying issue with the deeper network is that as we go in deeper in the network, the network loses the information learned by the initial layers. So here we propose to use the wider network instead of deeper network. So wider network are we hypothesize that wider network are better in order to generate a realistic video, because it has more capacity to retain the signal content of the video. So our key contributions are, we proposed a wider GAN in order to get a realistic video. And second is a feature level adaptive masking layer. This helps to learn the complementary features based on motion of the video. And third is, we also generalized our model to conditional video generation. For example, text to video generation and class conditional video generation. So here is the overall architecture of our model. So generator contains 5 hierarchical G3 module. Each G3 module consists of 3 streams: spatiotemporal, temporal, and appearance. And our main contribution lies in making this appearance wider. So we will discuss in detail about these streams in later slides. So the generator is trained by the two discriminator, image and video discriminator. Image discriminator is made up of 2D convolution network, and which classifies the input image as real or fake. And video discriminator in similar way classifies the input videos as real or fake. So this is the detailed architecture of G3 module. The first stream is a spatiotemporal stream. It is made up of 1D transpose convolution followed by batch norm and 2D transpose convolution. And second stream is a temporal stream. It is made up of 1D transpose convolution followed by batch norm. It is responsible for temporal aspects of the video. And the third stream is appearance stream. It is made up of two sibling branches. These are identical branches, and one adaptive masking layer. This adaptive masking layer helps to learn the sibling branches, the complementary features. The input to the adaptive masking layer is temporal features. These sibling layers learns one sibling layer learn the feature related to the moving object in the video, and other sibling branch learn feature related to the stationary part of the video. So we used standard adversarial laws in our model. So first two terms are represent the loss with respect to the video, and the second two terms represent loss for image in the frames law. So we have used three data sets: UVA NEMO dataset, Wiseman action dataset, and UCF 101. UVA NEMO dataset contains 1240 videos of 400 smiling individuals. Wiseman action dataset contains 93 videos of nine people performing 10 actions, for example, jumping jack and hand waving. So UCF 101 contains 13,220 videos of 101 different action categories. All the videos are all the frames are resized to 64 by 64 resolution. So here we compare quantitatively with the previous methods on three benchmark data set. So we can see the our method outperform all the previous method in terms of FID metric. And table 2 shows the ablation study on architecture. So we ablate the architecture by removing the adaptive masking layer first, and then the one of the sibling branch. So it shows the importance of each branch we have added in the paper. So one number cannot be associated with the diversity as well as the quality of the video. So we have used this newly proposed PR net curve for generative models. So here the blue curve represent the curve for PR curve for our method. So you can see here it is very good in case of UCF 101, which is a very complex data set. And also table 3 shows F-score value for F-score value for all data set and compared with the G3N. So here also there is a much more improvement even for the complex sets. So these are the qualitative results on Wiseman action dataset compared with Mokogan and G3N. You can see here Mokogan gives the ghost-like videos like these and these, and also G3N has some temporal inconsistency in some of the videos, or as compared to these our videos are very sharp and quality is very good. Here this slide shows the qualitative results on UVA NEMO dataset, and here we can see similar artifacts here, temporally inconsistent videos in previous method, and our method gives a very nice result. So here are qualitative results on UCF 101 dataset. Even for the as we have seen quantitatively, here also we can see our result give our method give more realistic videos than previous methods. So we have also extended our model to conditional video generation. First, we will discuss text to video generation. Here we have added one encoder, which is the pretend encoder, which is used to encode the input text caption to text embedding, and then one Gaussian noise is concatenated with this text embedding, and this final noise vector is then fed to the generator. Then we will get a video. For example, we can see here the caption is Daria is running from right to left. It will give the following output. So also here are some more examples. So we can see here our method gives the correct direction as well as action of the action for the video. Now this slide shows the class conditional video generation, and here are some results from our model, like running, parallel jumping, walking, etc. So for future work, we can explore more different type of wider networks, and higher resolution and longer video generation is another interesting area to research to work on. And here are some prominent references used in our paper. Thank you.
Thank you, Aarti. Anyone has any questions? Aarti? So can you go back to this precision recall curve which you were defining? So can you explain in more detail how do you read this?
Like this, yeah. So precision recall curve. Okay. So precision recall curve basically takes equal number of real videos and fake videos, and these real videos and fake videos are then passed to a pre-trained 3D CNN model, and it will give the feature of the real and fake videos, and those features are then fed to those features are then being uh, clustered into different beans, and these beans are used to calculate this precision and recall curve.
Okay.
So we have added a reference.
So why in the Weisman action data set we are not having lower precision and recall as opposed to the other two data sets?
Okay. So so Weisman action dataset contains very like very easy dataset it is. So I think that's the reason.
Okay.
Like it is not a complex dataset, so
Okay, fine. That's all I have. Thank you.
thank you.
Okay, so we can move to the next paper then. Thanks, Aarti and your team for the presentation, your work.
Yeah,
Okay, now I will request the next presenter of paper feature generation for long tail classification, Rahul and team.
Okay, so this will be again a recorded talk. Rahul is there for live QA.
Sure.
We present a practical way to generate meaningful features by calibrating the tail categories distribution in a long tail classification setting. This is a joint work with Mark from NVIDIA Toronto, Vineet from IIT Hyderabad, and Makran from IIIT Hyderabad. Let's begin by understanding the long tail setting in detail first. A data set is said to be long tail when majority of the samples are from a few head classes and there are very few samples from the tail class. In the hypothetical scenario shown, the data points available for dog class are extremely low compared to that of the cat class. Irrespective of the fact that both are extremely cute, when trained with any state-of-the-art method, the dogs would stand no chance against the cat on the prediction front. It is noteworthy that real world is inherently long-tailed and not an artificial construct. As a result, almost all the time the data sets collected from the real world are long-tailed. These kinds of data sets are generally denoted by their imbalance, which is a ratio of class with the maximum number of data points to the class with the least number of data points. This naturally brings up several questions like, how will it affect the accuracy of the prediction? what kind of real world consequence would such a data set have? Ultimately, why studying long tail is important. Let's take the same example of cats versus dogs. Say there are equal number of data points for both the classes. When we train an MLP using it, the decision boundary looks something like this. And the test accuracy is 100%. Know that this is a toy data set, which is the reason for the perfect score. Let's randomly remove data points from the dog class now and make the imbalance ratio equal to 100. Then retrain the model based on it. When we look at the decision boundary, it is clear that network is struggling to recognize dogs correctly. Despite this being a toy data set, the test accuracy plummets to 50%. When talking in terms of dogs and cats, this issue might not be very pressing. But if we replace the dogs versus cat scenario with male versus female, suddenly the gravity of the situation is much more evident. Remember, this is when we restrict ourselves to just two genders. When we take into account the other genders, this issue worsens rapidly. This problem gets even more dire when we talk in terms of deciding which vaccine to prescribe based on a long-tail data. Suddenly, it's more of an ethical issue rather than just a cuteness competition. This is why it's important to study and address the long tail in the data sets. While there exist several ways to approach such a scenario, we explore a direction that attempts to generate meaningful features by calibrating the tail characters distribution and making it balanced. Let's dive deeper into the proposed method now. Consider a dataset with three different classes which have a long tail distribution. Say class 1 is the head and class 3 is the tail. As shown in the figure, if you train based on the so-called dataset as it is, we have already a decision boundary that classifies class 3's validation samples as class 1. The samples of this dataset have a distribution that is not Gaussian, and this makes it difficult to understand and calibrate. So we need to make it resemble a Gaussian distribution in order for us to generate samples using them. But before we proceed further, first we compute the class characteristics, namely mean and variance for each class separately. These will come in handy later. Now we use a 2K transformation mapping in order to make the distribution of the classes closer to Gaussian distribution. Now using the features that resemble a Gaussian distribution, we do nearest neighbor search in order to find the classes based on which we can generate the new. More precisely, we first decide how many samples are we going to generate for each training data point so as to balance the data set. Then we take one such training data point and find nearest neighbor categories by comparing distances to the centroids of all classes. The intuition behind choosing the nearest classes is that classes that are close to each other in feature space would share similar features. The number of nearest classes to taken into account is a hyperparameter we play with in our paper. Then we take the corresponding statistics of the selected classes that we calculated earlier and average them. We call this the calibration step. Note that there is an alpha added to the averaged value. This basically controls the spread of the generated sample. Alpha is also a hyperparameter that is dataset dependent. For simplicity of sampling, we construct a Gaussian distribution based on the calibrated mean and variance from the previous step. Then we draw a sample from this distribution. Recall that until now, we have generated new samples based on just one training data point. This may not be sufficient to balance the data set. Therefore, we repeat the steps of picking a training data point, finding the nearest neighbors, getting calibrated statistics, and sampling from the calibrated distribution until the data set is completely balanced. We use this new balanced data to train a final classifier. Ideally, this should provide a better decision boundary that encapsulates and generalizes to unseen data points from the validation or test sets. We tried out two different variations of the training data generation protocol. Typically, when we generate once and new start to train, we call it train tail calib. But when we generate new samples at every epoch and train using them, we call it tail calib X. The X here indicates the multiple generation steps instead of one used in tail calib. Let's talk numbers now and see how our method performs in comparison to the existing literature. First, let's revisit the toy example which we studied at the beginning. When the imbalance ratio is 100, the test accuracy becomes 50%. How does our method perform in this scenario? The newly generated samples based on a method are pushed a decision boundary back, effectively increasing the test accuracy of the dogs to 99%. This is a proof of concept that our method works. Now let's benchmark on more complex long-tail datasets. On C500 LT dataset, firstly, note that cosine CE training paradigm is superior to CE, which is cross entropy, and in fact, outperforms several Ross leaveting-based methods. Cosine CE plus tail caliber expo outperforms all previous works, ignoring distillation. In fact, it achieves performance close to CBD, especially on imbalance factors 150. That trains two networks, a teacher and students, and benefits from the advantage of ensemble. Finally, applying tail calibex on top of trained CBD model results in further performance improvements of 1 to 2%, notably for imbalance factor 150. Apart from becoming a soda on CIPA 100 LT, we also demonstrate that tail calibration is orthogonal to and can be combined with other works to yield additional improvement. On mini ImageNet LT dataset, tail calibex outperforms all previous work. Compared to the cosine CE baseline, not only does it improve the accuracy for tail classes by over 20%, we also see performance improvements for both the middle classes and head classes. Surprisingly, CBD performs worse than the classifier retraining, that is CRT. Hence, we omit evaluation of tail calibration as applied to a backbone trained with CBD. If you have a long tail or imbalanced dataset and need a quick fix that boosts performance, then try out a pip package. Just use the command pip install tail calib. It supports both CPU and GPU acceleration for convenience. Using it is extremely simple. All you have to do is install and import it like in line 3, then initialize it with either NumPy or PyTorch depending on your use case, like in line 6, then input the imbalanced data along with its labels like in line 4. For much more advanced use cases, take a look at the pip package documentation page. Here are some useful links. Don't forget to check out our collab notebook to play with our method. If you are interested in deep learning research which involves long-tailed or imbalanced dataset, we recommend you to take a look at long-tail bus to learn about the recent training papers in the field. Thank you.
Thank you, Rahul and team. Thanks for the presentation. Okay.
So, can you hear me now?
Yes, we can hear you, but it
Yeah,
is a little lower. Your voice is a little low. Maybe
Yeah.
speak closer to the mic.
Yeah. Is it okay now?
It is better now.
Yeah. So I do see a couple of questions in the chat from Chetan Arora. How does the method relate to batch norm that is done batch-wise? Is it similar thing over whole data? Like, can you please elaborate on the questions? I don't understand it clearly. What do you mean by batch norm that is done batch-wise? Do you mean the actual batch normalization step, or do you mean are you talking about the L2 normalization step here?
I'm talking about the batch norm layers that when we add that. So after every feature map, we try to normalize the feature map with zero mean and unit,
Yeah.
for example.
Mm-hmm. Yeah. So the thing here is that we do batch normalization as usual. So because our method works on extracted features, we don't worry about the batch norm here at all. So basically, you have if we take a look at our results, right? So we have CBD plus tail calib and CE plus tail calib or cosine CE plus tail calib. So what happens here is that the CBD, CE, and cosine CE are used to train the features. So we are basically using the extracted features. So we don't worry about the batch norm here at all.
No, so you're talking. So when you say that you're calibrating the feature, you're talking about perhaps the last layer.
Yeah, exactly. Exactly.
So if on that last layer I would have applied a batch norm layer,
okay,
then I would have been doing something very similar, but for a batch.
Yeah, true. So it's a different normalization step, right?
Okay, but now what if I understood your method correctly? You are doing this normalization over the whole data set. The statistics are being normalized over the whole data set. Is that understanding correct?
Yeah.
Okay, so is there any experiment that you might have done if in the last layer you would have added actually a batch norm layer versus when you apply yours, how does the thing behave differently or similarly?
So we have not tried it. Yeah. So, but I think it's something worthwhile to try. Yeah. But we have not did the ablation yet.
Okay. And I have a very similar question, the second question also. So I have seen the instance whitening methods also. So if I have a feature map, or let's say if I have 100 feature maps in the last layer or whichever layer, I'm trying to decollate the feature map so that I am able to make best use of the bandwidth or the network that I have, the parameters that I have. So just like what you are doing in the last layer, let's say you are doing the data set wide normalization. Could I have tried to do data set wide decorrelation as well, just to learn the transformation which decorrelates this feature so that I have best use of all the elements?
Yeah, actually, there are multiple takes on how to solve long tail, right? So what you're proposing is one of the things. So what they try to do is take a feature from the head class and then decorrelate it and then use it to create a new tail class, right? So that is one of the way to do it. But like since ours is not very close to it, we didn't compare anything to it. So they do kind of a transfer learning from head to tail. So they take a feature from head, decorrelate it, and then use it to tail. I mean, then correlate it with the tail, and then make it look like a tail sample. So that is one direction that long tail community is taking. But we think ours is not very close to that. So yeah, so we didn't compare any methods that related to. So one method I think we did do is there is a method called M2M. So we did compare with that, and we perform better than them.
Thank you.
Thanks, Chetan. Thank you, Rahul. I think I also had on similar lines, query. So head to tail, how? So you're saying your work is not on the lines of taking the
Yeah.
head and trying to
Yeah, exactly.
decorrelate it to the tail. Okay.
Exactly. So ours is more like taking some statistics of the head and matching the tail class statistics to that, right? So, but there is indeed a direction in the long tail community where you take because since we have, so I mean, you can take an image and then decorrelate it into a class dependent set of features and class independent set of features. Okay, so you take the class independent set of features from the head class and then combine it with the class dependent features from the tail class, and then you create a create a new sample for the tail class. So it's just an extreme way of augmentation, right? So that's what. So there is a direction that indeed is there in the community. So there is a method called M2M that kind of does that. So it's not very visible to the naked eye. So it's kind of an adversarial example that's being created, but does help. But our method like outperforms them.
Okay.
Yeah.
Okay. Thanks a lot, Rahul and team.
Thank you.
For good work. So I think we come to the conclusion, and it was really good presentations by all the authors. And I will hand it over to Anand.
Sure. Okay, thank you, Dr. Venkat. Thank you for chairing this session. So now we will be moving to the next session of this, which is on Vision India.
Yes.
So, Dr. Anil?
Yeah. So hello, I am Anil Tiwari, a faculty member in the Department of Electrical Engineering here at IIT Jodhpur. I really feel very happy in welcoming all the panelists and the attendees to the Vision India session. The session will be chaired by Dr. Vineet S. Subramanian, and I welcome him. Over to Dr. Vineet. The session will be, of course, from 2:30 to I think 3:45 or something like that. Thank you.
Thank you. Thank you very much. And yeah, nice to be part of the event today. And good afternoon and welcome to all the attendees today to the Vision India session. So over the last few ICVGIPs, I think maybe this is the third one, I think, we have been trying to have a session called Vision India. The purpose of this session is one for different student researchers from whose affiliation is an Indian institution to present their published works at different top-tier conferences and journals across the world related to topics in vision and graphics. That's one of the objectives of this session. The second objective, which is perhaps even more important, is to hopefully inspire and inspire other students to also aim and hopefully increase the publication count of Indian researchers at top-tier venues around the world. So keeping this spirit, despite it would have been wonderful to have this session in person, so there can be attendees who could interact with these student speakers and maybe get to know their experiences. But keeping in line with the spirit, so what we've planned this year for the Vision India session is to have 7 presentations, which were selected out of, we had somewhere between 20 to 25 submissions, nominations, of which 7 were picked primarily due to the time constraints. And these 7 publications that are being presented in this session have been published at CVPR 2021, ICCV 2021, IJCV, PAMI, and IGDAR 2021. So all of these are top tier venues by their own right. And what we've asked the speakers to do in this session is each of them have shared a pre-recorded video of their research, but they've also added 1 to 2 minutes of research tips that they've benefited from in being successful at achieving top-tier publications. So what we'll see now are the presentations from 7 different speakers. We'll probably play them to keep the time limit in check. The plan is to play the recorded videos one by one, and we should have about 15 minutes or so at the end to take questions jointly to all the speakers from anybody, because we thought it would be useful for, especially related to research tips and questions related to that, it may be useful to address all the speakers at once. So without further ado, we can probably get started. I'll probably read out quickly the presentation titles so the videos can be played one by one. The first one is by Pranay Gupta from IIT Hyderabad on Quo Vadis skeleton action recognition, was published at IJCV 2021. The second one is from Kranti Kumar Parida. The title of the work is Beyond Image to Depth, Improving Depth Prediction Using Echoes. This was published at CVPR 2021. The third talk is by KJ Joseph on Towards Open World Object Detection, published at CVPR 2021. The fourth one is by Soumya Jahagirdar on the topic Look, Read and Ask, Learning to Ask Questions by Reading Text in Images, published at IGDA 2021. The fifth one is by Praveen Nagar on generating personalized summaries from day-long egocentric videos, published in PAMI in 2021. The sixth talk is by Pawan Prasad on the topic Very Fast, Deep Embedded Single Image Reflection Removal, published at ICCV 2021. And the last talk is by Daksh Thapar on the topic Anonymizing Egocentric Videos, published in ICCV 2021. With this, we can probably get on to the talks, and we'll have a joint Q&A towards the end.
We are from IIT Hyderabad and are presenting our work Quo Vadis Skeleton Action Recognition. Skeleton action recognition is a popular subfield of the more central action recognition problem. It differs from traditional action recognition in terms of the input action representation. Here, the action dynamics are represented via the trajectories of human body joints. Skeleton action recognition remained a challenge until the introduction of large-scale datasets such as NTO-RGBD16, NTO-RGBD120, and PKU-MMD dataset. However, the datasets and the capture methods for the aforementioned works are confined to controlled indoor settings. The videos in these datasets retain either full or partial context supplied by object interactions and background. They consist of choreographed or prompted actions performed for the purpose of creating a dataset which adds a certain bias. They are also confined to a fixed set of action vocabulary. Transcending these constraints, one by one, we introduce 3 novel datasets: Skeletix 152 to study in the wild action, Skeleton Mimetics to study out of context and exaggerated actions, and finally Metaphorics to study metaphor-styled human actions performed in social settings. To begin with, we present Skeletix 152. To source in the wild videos, we use Kinetics 700 as the starting point. It has 700 action categories, including daily routine activities, sports, and other fine-grained actions. We carefully omitted categories incompatible for pose-based action recognition. Next, we obtained the corresponding 3D skeleton sequences using Vibe, a state-of-the-art 3D pose estimator. Within these sequences, we removed classes where Vibe produced erroneous outputs. Finally obtained Skeletix 152, our carefully curated 3D skeleton action dataset, which contains 125,000 sequences spread across 152 classes. Next, we introduce skeleton mimetics. This dataset is derived from Skeletix 152. To curate this new dataset, we shortlisted classes with exaggerated movements and gestures. Instead of considering all the videos, we select specific action videos where action is performed by mimicry experts in out-of-context settings without object interactions. Final dataset consists of 319 skeleton sequences across 23 classes. To study the actions used to convey abstract and metaphorical concepts, we introduce the metaphorics dataset. The dataset contains videos from two scenarios, dumb charades and interpretative dance. We first source dumb charades game episodes from YouTube. In the game episode, one person, the actor, acts out a target phrase word by word while the other player tries to guess the target phrase solely from actions performed by the actor. To annotate each video using the Anvil tool, we mark all the finer details pertaining to the game in the video clip. We finally obtained 716 segments across 28 game sessions. We also source interpretative dance videos from YouTube. As part of the annotation process, we align the lyric subtitle file of the original song and the video. Since the actions are performed in real time, we obtain the action level annotations by aligning the audio file of the video with the original audio file of the song. We obtained a total of 129 video segments across two full-length music videos. In total, our metaphorics dataset contains 845 video clips. We begin our quantitative evaluations by checking how the state-of-the-art approaches fare against the lab-style datasets. For this purpose, we choose NT120. This table shows the average accuracies of the best performing models across the two splits of NT120 dataset. Here we observe that 4S Shift GCN and MSG3D are the most accurate, and hence we use these two approaches for our future experiments. In addition to the average accuracies, we also analyze trends in the best and worst performing classes for the two approaches. If we focus on the best performing classes, we observe that most of these actions involve large movements of the entire body or across multiple joints. On the flip side, the worst performing classes involve small movements localized to the intricate finger joint region. We now describe our experiments using the newly introduced datasets involving the best performing architectures on Intune 120 dataset. We begin with the Skeletix 152 dataset. We train the models in two training regimes. In the first one, we train the models from scratch on Skeletix 152. And in the second one, we first pre-train the models on Intune 120 and then fine-tune it using Skeletix 152. We observe that pre-training the network provides slight benefit as compared to training from scratch. Comparing their performance with NT120, it is evident that skeleton-based action recognition in the wild is significantly more challenging, given the inter- and intra-category diversity and noise-inducing factors. Analyzing the trends across the best and worst performing classes, we observe that the best 5 classes are all exercise-based activities, which tend to have very low intra-class variability. On the other hand, sequences from the worst 5 classes exhibit a lot of diversity and intra-class variability. Next, we explain the benchmarking experiments against the skeleton mimetics dataset. Due to the small number of samples in skeleton mimetics, we only use it for evaluation. We again follow two training regimes. In the first one, we use the models trained on the entire Skeletix 152 dataset.
And in the next one, we train only on the samples from the 23 overlapping classes in Skeletix 152. Results of the table depict that training on the complete Skeletix 152 improves performance as compared to training on the smallest grid containing the 23 skeleton mimetics classes. Finally, we perform evaluation on the metaphorics dataset. We evaluate using the models trained on NT120 and Skeletix 152. Since the label set used to train the models are different from the ones in metaphorics, we propose to compare word-to-word distance between the representations of the predicted label and the ground truth label. The rather poor performance can be attributed to the fundamentally different nature of training and evaluation settings. In this paper, we examined multiple up-and-coming frontiers in skeleton action recognition. To study skeleton action recognition in the wild, we introduced Skeletix 152. We introduced skeleton mimetics to study out-of-context and exaggerated actions. We finally introduced metaphorics to study gesture-like actions in social settings like damsharads and interpretative dance. Our analysis on NT120 dataset motivates the need for skeleton representations which provide finger-level joint information. The poor performance on Skeletix 152 showed that skeleton action recognition in the wild is challenging, largely due to the large inter-class variability. Metaphorics dataset also provides an opportunity to study the generalizability of skeleton action recognition approaches. Being patient is really important when it comes to getting our works accepted at top venues. Our work was also initially rejected at ECCV, and the entire publishing cycle lasted more than 1.5 years. While an acceptance at a top conference comes with its flair, journals are equally prestigious, if not more. Although publishing in a journal takes more time, but it is equally rewarding as well. Finally, an acceptance is not everything. With the current reviewing system in place, it is possible for reviewers to miss the merit in your work. However, if your work truly has merit, it will be taken up by our amazing community. Thank you for listening. You can check out our code and datasets at the given address.
Hi, I'm Kranti Kumar Parida. I'll be presenting our work, Beyond Image to Depth, Improving Depth Prediction Using Echoes. This is a joint work with Siddharth Srivastav and Gaurav Sharma. This work was recently accepted and presented at CVPR 2021. Our goal in this work is to predict the pixel-wise depth of the scene as compared to traditional depth estimation approaches, where depth is predicted directly from RGB image. We go a step further by exploiting echoes as well. We are inspired by echolocation, where animals like bat, dolphin, and even visually impaired people use echoes to get the distance of the objects in the scene. In the proposed approach, we first predict depth separately from echoes, then from image. We then extract material properties of different objects in the scene using material net, perform multimodal fusion to associate information from image, echoes, and material features. Then, using the fact that some regions can be better predicted with echoes, while others using images, we predict per pixel attention map for both echo and image and combine them to get the best of both worlds. Finally, we perform a weighted combination of depth from both modalities with attention to get the final depth of the scene. We use material property as a proxy to encode acoustic reflection and absorption properties of different elements present in the scene. Different materials will produce different echoes for the same sound. Hard materials, such as metals, will reflect sound strongly as compared to soft materials like fabric or cotton. Here is a short demo that shows how material property impacts the sound propagation. We can observe here that there is a significant difference in sound with and without the objects placed in the scene. In the hope of modeling this effect, we extract material features. We extract it using a pre-trained network trained on a large-scale dataset MINC used for material recognition from image patches. These features from this pre-trained network work as a proxy for the material properties. We perform our experiments using simulated data on both replica and Matterport 3D dataset. Both these datasets contain scans of different indoor environments. The image and depth map were obtained using Habitat 3D simulator, and echoes were obtained using Sound Spaces simulator. Both these simulators are open source and publicly available. For the experiments, we first evaluated how much the echo and material property help. We observed that adding all the features gives the best performance. We further compare our results with different baselines and existing approaches. Our method outperforms all of them in both the replica and Matterport 3D dataset. Here we give some qualitative results. We observe that our method captures finer details in the scene as compared to existing approach of visual echoes. The structure of the group of chairs in the first example, table and chair setup in the second, and the plant in the third example are better visible in our approach. In some more qualitative results, we make similar observations and see finer details of the objects along with boundaries well constructed. We give here the attention map as observed from echo and image channels. We observe that echo attends to faraway regions but ignores the finer details in them, whereas the image channels attend to the nearby region. This is probably because the echoes from nearby regions are not distinguishable from the source, and the echoes received from soft matters like sofa are not that strong. We have made our code public and you can find it here. Thank you, and we'll be happy to answer if there are any questions. In this slide, I'll try to provide here some of my insights on what might be some key factors for getting a paper accepted at major computer vision venues. I'll try to mention a few points here other than the technical aspects. Hope it is helpful to some of you. The first important point is formulating the problem by discussing and brainstorming with all the collaborators and then sticking to the same problem. After fixing the problem, it is better to write the initial approach in a paper format. It will be helpful to find out gaps in the approach. The next important thing is to run the baselines quickly and get the results as soon as possible. You should have the results ideally 1 month before the deadline. I would like to point out here that do not hesitate to contact the authors if there is some discrepancy or doubt in the results of the baseline. Then discuss with the rest of the authors and fix the outline of the paper, that is your problem statement, why it is important, what has been done, and how your approach is different. Finally, the most important step is the writing of the paper. While writing the paper, keep in mind the reviewers. Given our field is expanding at a massive pace, there might be reviewers from a wide range of background and some may not be aware of every details of your area. You should also keep them in mind while writing the paper. Also, give special attention to figures and plots. Finally, revise your paper as many times as possible before the final submission. Thank you. I hope some of the tips are useful for you and wish you all the best for your next submission.
Hi everyone, my name is Joseph and I'm a PhD student at IIT Hyderabad advised by Dr. Vineet. I would like to thank the organizers of ICVGIP for providing this opportunity to present our work on open world object detection. This is a joint work with Dr. Salman and Dr. Fahad from MBZ UAI, Abu Dhabi. Our work introduces an extension to object detection problem setting, where the detector is able to identify instances of unknown objects as unknown and incrementally learn them when these identified unknowns are eventually labeled. Open world detection considers the realistic setting where a few set of classes denoted by the blue circles are labeled out of a large pool of unlabeled classes denoted by the gray area. An open world detector should be able to identify instances of unlabeled classes as unknown along with learning labeled instances. As and when these unknown classes are annotated by an oracle, the open world detector should be able to incrementally learn those classes without access to previous class data points. The whole process goes on until the detector learns all classes of interest. Our newly formulated open world object detection problem sits in the nexus of open set learning and incremental learning when applied to object detection. The proposed methodology OR is built on top of fast RCN framework with 3 important changes. We explain them next. Class separability in the latent space can help an object detector to identify unknowns and reduce forgetting. We enforce this through a contrastive clustering loss on this 2048 dimensional feature vector in the ROI head. We ensure FC, a feature vector corresponding to class C, to be close to its corresponding class prototype PI while far away from other class prototype vectors. Each class prototype is a function of the feature vector of the corresponding class, which are stored in a feature store. Continually adapting these class prototypes is a key task, which is explained in this algorithm. Fstore is a feature store which contains fixed length queue per task. After a certain burn-in iteration IB, the class prototype vectors are computed as the mean of the vectors in the corresponding feature store. After each IP iterations, the prototypes are refreshed. The contrastive loss demands even the unknown data to be labeled, which is impractical. As a surrogate, we propose to define an unknown-aware region proposal network which auto-labels unknown. Those proposals with very high objectness score but without an overlapping ground truth label are auto-labeled as an unknown. The third change is to use an energy-based classification head. Energy-based models has its intrinsic capability to assign low energy values to in-distribution data and high energy values to out-of-distribution data. We utilize this to classify whether a region proposal belongs to an unknown class or not. Specifically, we use a modified version of Helmholtz energy formulation where the energy is expressed in terms of classification logics, which directly follows from equation number 3. When we plot the energy values of a kept aside validation data, we see clear separation in the known and the unknown classes. We fit a Weibull distribution on this, and the likelihood of a proposal to belong to either of the learned distribution is used to identify it as an unknown. This completes the description of OR. By learning the next task sequentially, we use a simple exemplar replay strategy to address forgetting. Next, let's review the experimental setting. Task 1 contains instances of all 20 classes of Pascal VOC dataset. Semantically different classes from the remaining 60 classes of MS COCO are grouped to form the next 3 tasks. We explicitly evaluate the quality of unknown detections using wilderness impact and absolute open set error, while quantifying the detection accuracy with MAP metric. This table summarizes our main result. While learning each task sequentially, when compared to the standard fast RCNN, OR has dramatic improvement in characterizing unknown without compromising on the performance of labeled data. Without any methodological change, we are able to achieve state-of-the-art performance on incremental object detection too. Here we have a qualitative result. OR is able to detect fruits and vegetables as unknown on the left, as it has not been introduced yet. After learning about them in task 3, OR can incrementally learn them. An unidentified class still remains, and it is correctly detected as an unknown. To summarize, we introduce a practical extension to object detection problem which tasks the model to identify unknowns and incrementally learn them when the identified unknowns are eventually labeled. We formulate a methodology based on contrastive clustering, unknown-aware RPN, and an energy-based unknown identifier. We further define the experimental setting and evaluation protocols for this newly introduced problem. Please refer to our paper for more detailed results and ablation experiments. Our code and models are available on GitHub. Finally, I would like to share some tips that I've found helpful while doing research. The first one would be to do only what you're truly passionate about and take ownership of what you do. Doing research will not be a straight path, and we need to be prepared for the ups and downs. You'll easily have the energy to maneuver the low phases of your research only if you're truly passionate about it. If it's not the case, you will easily find excuses to move on to something else, and unless and until you stick with something and dedicate wholly to it, we cannot expect any concrete results. The second one would be to organize yourself better. So I believe the caricature of a PhD student has changed a lot. It is not like someone sitting in a lab having uninterrupted long hours pondering over amazing research. So he or she might have some family responsibilities. They might be TAing for some courses. They might have some responsibilities from wherever they are interning. They might be mentoring someone. So I believe the rule of thumb is be prepared to be disturbed. And unless and until you are organized, it will be very hard to kind of cope up with your research. I personally use Google Sheets to organize myself. Maybe I can share a little behind the scenes of the work that I presented today. So whenever I read new papers, I tend to write short notes about the same. And whenever I meet with my collaborators, I tend to summarize the important points of discussion here. Here you can see that I was pretty consistent until May 16th. And then May 16th over here, and then there was a huge gap until September 1st. This write-up did indeed help me to pick up my work from where I left off. Equally important is to organize your code, and I use GitHub for doing so. Here you can see how the methodology indeed matured from a set of ideas over here and progressively got better and better. So one good part about Google Sheets is like it allows you to have these asynchronous discussions with your collaborators. Another practical tip that I found very useful is to start writing a paper from day one. It can even be just outlining the various parts of your paper as a skeleton and progressively improve them as and when you have more points to add. One other tip of organizing yourself is to start talking with yourselves. You can be your best colleague and your best reviewer too. One last step would be to take rejections positively. You never know what's in store. See each submissions as a checkpoint of your work so far. Maybe I can share a personal story. Long back in 2017, my first submission was to WACV and it was rejected. It was turned down at ICVGIP 2, and eventually it got accepted at an ECCV workshop. Attending ECCV 2018 was indeed a game changer for me. It was one of the workshops hosted by Tini Trials and Christopher Lampert that introduced me to continual learning. Since then, I've been working in that space and it was very rewarding. So my WACV 17 rejections did indeed help me in the long run. Many of these tips are manifestations of advices that I received from my advisor and my parents. So if you found anything useful, the credits are to them. Thank you so much for listening so far, and all my contact details are there on my website.
Hello everyone, my name is Soumya Jagatar and I'm going to present our work, Look, Read and Ask, Learning to Ask Questions by Reading Text and Images. Our work was accepted and presented at International Conference on Document Analysis and Recognition. Conversational AI is an exciting and emerging area. Technologies such as Alexa, Google Assistant are getting used in our day-to-day lives. Interactions such as human-robot and even robot-robot are no more just science fiction movie things. Tasks that mimic human conversation are a huge set of responsibilities of conversational AI. Therefore, building a conversational AI system that can make a smooth and meaningful human-like conversation is need of the hour. Document community has also started showing interest in this problem by introducing works such as TextVQA, a text-based visual question answering system that highlights the importance of text in the scenes to answer the questions. On the similar lines, ECDAT 2019 Robust Reading Challenge on Scene Text Visual Question Answering also introduces a new dataset in which questions can only be answered by reading text present in the image. Another work, that is text caps, in which dataset for image captioning with reading comprehension was introduced. Other works such as OCR VQA, Knowledge Aware Text VQA are also few works which have contributed in this interesting domain. Now let us look at an example of possible set of conversation which happens between human and robot with text VQA kind of environment. It could be something like the man might ask, "What is the name of the book?" The robot, after reading the text in the image, answers Harry Potter and Deathly Hallows. And the conversation simply dies. Now the question is, did the robot also generate a follow-up question such as, "Do you want to know who wrote this book?" The answer is yes. As these works result in limited one-way communication, which becomes a very huge hurdle in better visual dialogue systems, we introduce a new problem of generating questions using text and image, which attempts to solve these limitations. That is, given an image and an OCR token with respect to that image, the task is to generate an appropriate question for which the considered OCR token acts as an answer. Here are some possible set of applications for the proposed task, which include visual dialogue system, automatic text VQA dataset creation, a tool for visually impaired, and question generation in educational systems. To solve this task of text-based visual question generation, inspired from baselines in the work generating natural questions about an image, we provide three baseline approaches. The first one is maximum entropy language model. Here, a set of OCR tokens extracted from the image, along with a set of detected objects using faster RCNN, are fed to maximum entropy language model to generate a question. The second approach is sequence to sequence model. Here we first obtain caption of the image using pre-trained CNN, LSTM caption generator. Then the generated caption along with the identified OCR tokens from the image are passed to sequence model to generate an appropriate question for the given input. And the third baseline is gated recurrent neural network, in which we first obtain the visual features using pre-trained image encoder, in this case that is Inception V3, which yields a feature vector which is then passed to a gated recurrent unit to generate question. All these baseline approaches have their own limitations which are as shown in the slides. To tackle the limitations of baseline approaches and solve the new task of text-based visual question generation, we propose a new architecture called as OCR consistent look, read, and ask, that is OLRA, where the model is first supposed to look at the image, then read the content in the image, and later ask an appropriate question. I will be explaining the model in three components. The first one is look and read module. In this module, for the input image, we first extract the visual features using pre-trained CNN, that is ResNet50, which yields the vector phi. We use the OCR detection and extraction technique to obtain the OCR token from an image, which acts as a potential answer. We first obtain the fastest features of the OCR token and pass it to a bidirectional LSTM, which yields the feature vector phi O. Based on experiments, we found that the positions of the OCR token plays an important role in visual question generation. Hence, we use the positional features as phi P. We concatenate the three vectors and pass it to a multimodal fusion model, which is a multi-layered perceptron. The output of multimodal fusion module is a joint representation which serves as an input to both OCR consistency module and the question generation module. Now, let us look at the OCR consistency module. Here, in this module, after learning the joint representation of both image and OCR features, the model should be able to generate question given the specific OCR token. To ensure this consistency, it is important that the joint representation learned after the fusion preserves the OCR token, that is phi O. To preserve this, we reconstruct the phi cap by passing joint feature to multimodal perceptron to obtain the reconstructed answer token. We minimize the L2 loss between the original answer and the reconstructed answer representation. Now let us look at the third module, that is Ask module. In our final module, the relevant question, we generate the relevant question. We use a decoder LSTM to generate the question Q dash from combined space multimodal fusion. The output of the multimodal fusion module, that is joint representation vector, serves as an initial state to an LSTM. We produce the output question word one at a time using the LSTM. This happens until we encounter end of sentence token. Every loss between generated and the true question guides the generator to generate better questions. Basically, the training of ORA happens in a multitask learning paradigm where the two tasks are OCR token reconstruction and the question generation. Coming to the results, we show a model performance on two datasets, which are scene text visual question answering dataset, STVQA, and text visual question answering dataset, that is a text VQA. As we can see from the baseline, that our method outperforms the baseline approaches by a significant margin in all performance metrics considered on both the datasets. Now let us look at some qualitative results. Here we provide the comparison between the questions generated using baseline approaches and the question generated using the proposed method, that is OLRA. As we can see, the OLRA method generates questions which are very much similar to the expected question. Now let us go through a few more examples of qualitative results. Here the OCR token considered, as we can see, is 222003, and the question generated is what is the number on the forefront of the train, and expected question was what 6 numbers are visible. As we can see, the generated question is very much relevant and similar to what the expected question is. Here is another example from different dataset, text VQ dataset, where the generated question is very much similar to as that of the expected question. We also show a fallback case of our model where the model basically misinterprets the content of the computer to the brand of the monitor or computer. So I would like to conclude by stating that we propose a novel task of text-based visual question generation, that is text VQG in short. We propose a model to ask meaningful questions about the text present in the image, that is OLRA. And we believe that this captivating novel task encourages researchers to develop better text VQ systems and thereby promoting research efforts of the document image analysis community towards better conversational AI systems. And here are some tips for to make sure that your time and energy into the work results in sweet fruits. That is, the first one is wisely look for the loopholes which are present in the system. So pick, just like we found that the question generation task with respect to the text present in the image was never tackled. So we found out that that was a loophole. Spend enough time for performing various ablation studies. So due to the time constraint, we haven't shown the ablation studies. Please do look at the paper to find the ablation studies for this task. And also it is very important to address the queries raised by reviewers at the rebuttal. So these points will basically enhance and they'll actually add up to your work, which gives a very positive impact at the end. So with all these points, I would like to conclude. Thank you.
Hello, everyone. So today, on behalf of my team, Anuj Rathore, Professor C.V. Jawahar, and Professor Chetan Arora, I am going to present my work titled Generating Personalized Summaries of Day-Long Egocentric Videos. What are egocentric videos? So egocentric videos, also known as first-person videos, captured by wearable devices, typically worn on head or chest of the camera wearer. Because of that, this video approximates the visual field of camera wearer. Some examples are like GoPro, Pivot Head, and SenseCam. So how egocentric videos are different from third-person videos or traditional videos. So as this video often recorded in hands-free and always-on manner, so that's why these videos are very long and very redundant. And because the camera is placed on the head or the chest, that's why these videos are very shaky. While recording these videos, the subject moves from a variety of scene contexts That's why this video comprises a large variety of scenes. Furthermore, the subject pose information are missing in these kind of videos. So because of these challenges, the third person video analysis techniques cannot be used for egocentric video analysis. So video summarization is defined as selection of key frame or key shots which are representative of the original video. And summarization is a key task for efficient consumption of egocentric life logs generated by a wide range of practical applications. So few of them are like life logging and law enforcement. So in life logging, you're having a day-long recording. So you would like to generate a summary focusing on social interaction patterns, or maybe unique interaction you have met throughout the day. Similarly, in law enforcement, you would be interested to detect important scene, object, or people to identify the scene or the clue, or to better investigate particular crime scene. So that is a very important question. Can we summarize day-long egocentric videos in unsupervised setting? So the precise problem statement is as follows. Generate dynamic length personalized summary from day-long egocentric videos using unsupervised deep neural network. Dynamic length means you would like to generate a summary of different lengths. In personalization, we want to incorporate user feedback. And in customization, we are having a predefined criteria, such as maybe you want to generate a summary focusing on social interaction. So this is the proposed architecture, and for the simplicity of the explanation, we have divided this entire architecture into three parts. The RL framework in the middle part, the sliding window framework in the left, various plugins in the right, and the personalization module in the bottom of the figure. So I will start with this RL framework. So given a video, we divide the video in small chunks. We call it subshots. We pass the subshot to the C3D, and we generate the feature corresponding to each subshots. So given the state space generated by the subshot level features, the RL agent picks the summary frame that maximizes the reward function. The reward in turn defined by various plugins meeting different summary objective. So as training progresses, you update the summary, and if the agent improve the reward, you update the summary. And finally, you are having a summary which is having the best or optimal reward. So what is distinctiveness and indicative rewards? So distinctiveness and indicative reward are the base reward, ensure that the selected subshot are diverse and representative of original video. For diversity, we maximize the pairwise distance between the summary subshots. And for the indicativeness, we ensure that the original video is reconstructed by the linear combination of the summary subshots. So moving to one of the core contribution of the proposed framework, which is sliding window framework. So as we see that the RL agent is bi-LSTM, and it cannot handle a long sequence which ranges up to 60,000 timestamps. So to overcome this limitation, we propose a sliding window framework which move a small continuous window over the day-long video. So instead of giving the entire video in a single go, we give a small segment of the original video in the form of sliding window. We also provide a past summary and the future summary generated by the most recent summary to maintain the global representativeness of the original video. So now coming to the personalization module. So initially we generate a summary without any feedback. So once we have this unbiased summary, we show the summary to the user, and we get the feedback from the user. The feedback could be positive or the negative, defined by the user, and we incorporate this feedback into the reward function using interactive reward. So positive feedback means the subshot which user want to be in the summary, and the negative feedback is the subshots which he doesn't want in the summary. So in interactive reward, we try to maximize the similarity between the summary subshots and the positive subshots. Whereas for the negative subshots, we try to maximize the dissimilarity between the summary subshots and the negative subshots. So that forms an interactive reward, which is integrated in the total reward while training the agent. These are the results. These results are generated by by the basic reward, which is distinctiveness and indicative rewards. So as you can see that the proposed method uh, overperform compared to the SOTA approach with huge margin. So the reason being that if you visualize this summaries generated by various framework, then we observe that the state-of-the-art method pick the summary frame from the particular location of the original video because they cannot handle this day-long video. Whereas the proposed framework, the policy gradient Q-learning and actor critic frameworks, uniformly distribute the summary frames all over the video, and these selection are quite aligned with the ground truth summary. And these are the result of personalization. So we have defined two events, namely preparing food and driving events. So the second bar chart shows the summary generated without any feedback. And the third bar chart shows when the feedback is given as follows. So the user want to include the driving event and the user want to exclude the driving event and include the preparing food event. So you can see that the summary started picking the frame from the preparing food event. Similarly, when you reverse the order, now user want to include the driving event and exclude the preparing food event. So the last bar chart shows that all the frames are picked from the driving event, whereas the frames which are there in the preparing food events are excluded very efficiently. So the proposed framework is a first contribution toward handling these day-long sequences in completely unsupervised setting. So the long sequence modeling is a foundation for building AI that exhibit high-level intelligence like humans. So furthermore, this is the common problem for various domain like NLP, audio, medical imaging, and stock market analysis. Thank you.
The presentation of paper ID 9614 titled We Desire Very Fast, Deep Embedded Single Image Reflection Removal. And my name is Pawan Prasad and I work at Samsung R&D Institute, India, Bangalore. A brief look at the contents of the presentations where we first introduce the problem statement followed by the proposed method, experimental results and the conclusions. Reflective surfaces such as glass often degrade the captured image, causing undesirable reflections. The corrupted image is often modeled as a linear combination of two components, namely reflection and the background. Estimating these two components from a single image is severely ill-posed. Most of the recent methods of single image reflection removal use data-driven approaches that use deep learning to recover the background image given the corrupted image. Let's look at some of the existing limitations in the existing deep learning-based methods. Firstly, most of the existing methods target extremely low resolution images, whereas most of the images captured in real life are very high resolution images. Secondly, the receptive field of almost all the methods do not change between the training and the inference, keeping them static. This limits the range of resolution a given network can operate on. Thirdly, existing methods focus mostly on improving quality of reflection removal by completely neglecting the processing speed and the memory requirements, making them impossible to run on resource-limited devices such as mobile phones. In our work, we address each of these three limitations. To ensure that our network supports higher resolution images, we process the corrupted images into two separate stages, namely the low-scale subnetwork and the progressive inference stage, called as the PI stage. The PI stage iteratively handles higher scales. We propose a novel scale space architecture where the receptive fields can vary according to the input resolution at inference time. We ensure that the complexity is reduced by using a shallower networks at the higher scale and deep network at only the lowest scale. Further, we deploy weight sharing in the PI stage to ensure that the model size is kept small. We can process a very high resolution image such as 12 MP within a couple of seconds on a mobile device. The high-level overview of the proposed scale-space architecture for reflection removal is shown here. Given a high-resolution image corrupted by reflections, we first determine the number of scales in the scale space required to process this image. The lowest scale is given to the LSS net that can efficiently remove reflections using a large receptive field, followed by progressively upscaling the images and removing reflections at higher scales. The final high-resolution images is generated as the output of the highest scale of the PI stage. The LSS net uses a deeper network architecture with double convolution residual blocks that ensures that the receptive field is large enough to have a full view of the input image at lowest scale. The HSS net is much shallower and works along with convolution guided filter to progressively generate the final high resolution output. It will be interesting to note that both LSS net and HSS net generate valid output images, not just features, at each scale level. We use the Pascal VOC dataset to generate synthetic reflections and also use the Berkeley real dataset for transfer learning. The high resolution dataset that is used for testing contains varied resolutions from 12 MP to 64 MP. We train the LSS net and the HSS net separately using different real and synthetic datasets. The LSS net is trained firstly using synthetic dataset generated using Pascal VOC, followed by real images from the Berkeley dataset. The HSS net is, however, trained mostly with a synthetic dataset. We use a typical data augmentation such as flips, props, and rotations. We do use a combination of L1, L2 gradient, L2, and contextual losses with all of these except the L2, but with different weight combinations where L1 and gradient L2 are given slightly higher weights compared to what was used for LSS net. I will now present the results on the public datasets. Which are mostly high resolution. Low resolution, where only LSS net is used as a result of low input resolutions. As it is evident, our method and the most recent RAGNet are able to restore very well in the high texture regions. I will now show some more results on the public datasets. Now, I will show our results on high resolution images 12 MP. It is quite evident that all of the recent methods fail to restore the images corrupted by reflections, in spite of the fact that they work well for low resolutions. Even though some of these methods work well for images that high resolution, which cannot really handle the receptive field of very high resolution images and fail for high resolution images. Some more results are presented here. Now, I will show how our method progressively restores the image with different levels chosen for the scale space during inference for very high resolution images such as 64 MP. I will now show quantitative evaluation of our method against state-of-the-art methods. Our method outperforms most of the recent methods on public datasets. Most of these datasets used for quantitative evaluation are of low resolution, hence only LSS net is used for a majority of the images. We also show comparisons of complexity of different methods. Our method is at least 2 orders of magnitude better than the next fastest method. Our method can be easily deployed on a smartphone to process high resolution images in real time. We now present the conclusions of our work. Our method is the first deep learning based method for single image reflection removal that can handle very high resolution images and at the same time run on resource limited devices such as mobile phone within a few seconds. We use a novel scale space architecture for reflection removal that is designed to be flexible with dynamic receptive field during inference. We achieve state-of-the-art performance, and we also provide a high-resolution dataset for future benchmarking and evaluation. Thank you.
Hello everyone, my name is Daksh Thapar and I am from Indian Institute of Technology, Mandi. I'm here to present my work on anonymizing egocentric videos, which was published in International Conference on Computer Vision in 2021. Because of the availability of egocentric cameras such as GoPro cameras, egocentric videos are becoming more and more popular. And with these popularities, we are actually seeing many large-scale data sets, such as FPSI data sets and Epic Kitchens data set, which are actually being used related to the egocentric research. And this research is not just limited to egocentric videos, but it has also its applications into the robotics and other aspects of computer vision as well. Now, one of the reasons that such data sets are becoming so much popular is that egocentric videos actually provide a false sense of security, since the camera wearer is never visible in those videos. Now, majority of the state-of-the-art systems have actually shown that even though the camera wearer is not visible, they can still recognize the camera wearer in egocentric videos. So they can utilize the hand gestures that are the behavioral patterns of how the hands are moving inside the videos to recognize the person, such as shown in the left video, or via the gait or the moving pattern of a person. That is again a behavioral feature, such as in the right side of the video. And such features can actually be utilized to recognize the camera wearer, despite the wearer is not visible at all. Now, one of the such works actually shows that given any two videos, they can actually tell whether those two videos they belong to the same camera wearer or they actually belong to a different camera wearer. Even when the videos do not have any walking motion in them, just by using hand gestures also, these works have been able to show that whether given two videos which are actually performing completely different daily tasks, but because of the behaviorality of the way your hand moves and the way your head is moving, they can actually tell whether the two videos are coming from a same wearer or they are coming from a different wearer, even if they are performing two very different tasks such as cutting or washing. Now, such systems are actually posing a really great privacy threat, because if we are to heed to their warning, then we must actually stop using these egocentric videos because they are not preserving the privacy of the camera wearer. So to solve these threats and so that the research for the egocentric videos is not stop, we need an anonymization system which can also act for egocentric videos. Now, such an anonymization system should be able to remove the identity of the camera wearer, and it should be able to maintain the utility of the egocentric videos, because we utilize egocentric videos for a wide variety of tasks such as summarization, temporal segmentation, and action and activity recognition. Moreover, those videos' visual integrity should be maintained. So the anonymization of the video should be in such a way that whenever we are viewing the video, the visual change in the video should be imperceptible. So hence, we actually propose an anonymizing egocentric videos framework, which actually does all of these three tasks. It is able to remove the wearer's identity by fooling an identity recognition system. It maintains the utility by preserving the performance of activity recognition systems. And since our system actually adds very subtle perturbations in the videos, it actually maintains the visual integrity of the videos as well. Now how we anonymize the videos? We actually anonymize the videos over the video homography. Since one of the salient features to recognize a camera wearer is through the head movement, the behavioral head movement. And that head movement is actually recorded by the camera pose that is in the rotation of the camera. So hence, if we can perceive the rotation of the camera in such a way that it actually hinders with the behavioral features of that person, we can anonymize the egocentric videos, and those perturbations in the rotation can be very small that the videos are imperceptible. And since rotations in the camera domain can easily map to homographies in the video domain, we actually add perturbations in the case of homography. So our system actually, what it does is it extracts the camera pose from the given video. Based on the camera pose, it actually creates a wearer classifier system. Now to extract the relevant camera pose features, those can be used to anonymize the wearer. We utilize guided backpropagation on the wearer classifier. And by this guided back propagation, providing us with the camera pose. Now this camera pose can be turned into homography, and by apply this homography to the target egocentric video, which actually provides us by anonymized egocentric videos. So one of the ways which we can actually compare our anonymization is to compare it with noise. So here we have shown that what is the effect of noise when we are working with egocentric videos. So we can see that we actually need to add a lot of noise so as to achieve the anonymization. And we can see that adding such a noise can actually make the video really jittery. And moreover, by adding such a noise, even the activity recognition systems are also fooled. So the original video, which was of cut activity, by adding such a high noise, the activity recognition systems actually say that the activity of this video is turned off rather than cut, despite the identity is changed. But the visual integrity and the utility of the video is completely removed. In other case, our proposed system actually does a very subtle perturbation. Now, these subtle targeted perturbations preserve the integrity of the video and visual perceptions of the video. But as we can see, that the actual video was of the subject one identity, but after perturbing, the state-of-the-art Vieira classification systems were actually saying that the video actually belongs to subject 5. Moreover, the perturbations are so small that we can add them and stop them at any time we want over the FPSI dataset. And we can see that just a slight blackish area is coming over the top and left. But when we are seeing the center part of the video or other part of the videos, our proposed perturbation for anonymization is completely imperceptible. So this is about our paper, Anonymizing Egocentric Videos, where we actually add very small, very subtle perturbations based on the homography, and we are able to anonymize egocentric videos. This will allow the videos to be anonymized, and we can actually utilize these videos to the egocentric research field. Now comes to the point what it actually takes to publish research papers. So one of the very basic fundamentals of publishing research papers is learning how to read the research papers. You need to actually learn how to read research papers. And reading the research papers does not mean that understanding what's happening inside the paper, but analyzing what's happening. That is, when you read a research paper and you get to a proposed system that the authors have proposed, you need to come up with a thinking that how from scratch the authors were actually able to reach to that thinking. That is, if you were given this problem and now you have the solution, how would you approach to that solution? So that actually creates a critical thinking in you that will actually allow you to utilize this critical thinking, the problem that you are able to solve, and hence be able to publish papers which are actually of good quality. Thank you, everyone.
Okay. Thank you, Dr. Anand, for coordinating and playing the videos. And thank you to all the student speakers for the great work and the presentations. Congratulations again to each of them for the publication, and hope each of you keep up the good work. So we can move on to the Q&A session for these few talks now. So we have about 10 minutes or so for questions to any of the speakers. So just to remind all of you, there were a total of 7 talks. If any of you would like to unmute and ask a question, all the speakers of this session have been kind enough to be available here. So they are on this call. So if any of you had a question for any of these speakers from these presentations, please do unmute and ask. Maybe if any of you have a question on even just publishing, since that was the intention of the session, please do feel free to ask to any questions.
Hello, I am having one question for Daksh. So Daksh, you have told us that the anonymity is not prevented by the egocentric videos, but how you will identify the subject? like you can match that these two subjects are the same, but how the identity is compromised.
Okay, yeah. So for the identity, one of the works is an ECCB work that actually showed that you can match an egocentric video of the wearer with the corresponding third person surveillance video. So because in both egocentric and third person videos, the gate features are available, and so you can match them. So yes, by matching egocentric to egocentric videos, yes, the privacy is not violated. But however, if we can match the egocentric video to the corresponding third person video, we can visually see who that person is, and hence we can tell exactly who the camera wearer was. So that aspect actually made the privacy violation in egocentric videos.
Okay, thank you.
Any other questions for any of the speakers? Okay, if maybe I'll start off with a couple, and then maybe there'll be more questions coming. Maybe I had questions for different people. I'll just start with anyone. Maybe.
Dr. Vinit, there is some question on chat as well.
Oh, okay, sure. Just one minute. Let me read out the questions. If
or maybe they are to host and presenter. Okay, maybe I can read out if you.
Please, yeah, if you don't mind, if you can read out. I'm not able to see the question.
So my question is to BH Pawan Prasad. I guess you work at Samsung Research. How is the research in academia different from research in industry? Maybe it's slightly question, but yeah. Is Pawan there? I don't think he's. Okay.
Looks like Pawan is not here, unfortunately. Yeah, maybe the person asking the question could perhaps write to him offline.
Dr. Vinit, please go ahead. Yeah.
Okay, all right, okay. We start off with a question, and maybe there may be more questions in the next few minutes. Let me just start from the beginning. Pranay, maybe one question. I hope Pranay is here. I had a couple of questions. One is considering, I mean, one of your main contributions, firstly, nice work on the dataset for skeleton action recognition. Maybe a couple of questions. One is, what difficulties did you face while creating a dataset? I mean, if you had to create a dataset again, what would you keep in mind? Because generally dataset creation can be a tough task. I wanted to get your thoughts on what you think about that. And the second question I had was, considering you benchmark different methods for skeleton action recognition, what are your thoughts on appearance-based methods versus graph convolutional networks on such problems, especially on skeleton kind of data? Any thoughts on these questions? Is Pranay Gupta here? Yes, I do see him. Pranay, could you?
There, yes. Can you hear us?
You may have to unmute if you're talking. Pranay, can you hear us? Okay, maybe we'll move on to the next question, and hopefully once he comes back online, we can ask the same question. By the way, once again, any other questions from the audience for the speakers? Okay, if not, let me, maybe one question for Kranti Kumar. Once again, nice work. I think pretty interesting idea of estimating depth from ecos. I wanted to ask, I mean, in the data sets that you studied for this problem, what kind of data exists? I mean, how do you get the echo information, and how do you, if you can just talk a little bit about what kind of data exists in these data sets that you studied on? Is it possible to elaborate on that?
Hi, am I audible?
Yes, you are. Yes, yes.
Okay, thank you. So the dataset that we used was a simulated dataset. So it is a there is a simulator called habitat simulator, and there is a sound spaces on top of it. So they map every scene in the simulator to how the sound will be produced in that scene. So these are basically scans of rooms like inside buildings and all. So it is completely simulated, and so you give a sound, and the sound gets reflected from different boundaries or different surfaces in the room, and then the sound is collected.
I see. So which means the input to your model is both the image and the sound, or is it just the sound?
Yes, it's both the image and the sound.
I see. Okay. And you're trying to refine depth estimation using both these inputs. Am I?
Yes.
Okay.
Yes.
Okay. Because my next question was, would such a method dovetail into Kinect kind of data sets, right? I think probably that's the other kind of data sets that do a lot of depth estimation, any stereo camera for that matter. So if you had like a stereo camera with a mic, would this method work, was what I was about to ask, but I assume that that may not give you the kind of data you're looking for. Am I correct?
Yeah, in that case, you have to have aligned data like all the stereo input audio and the LiDAR like depth map.
I see. Okay, understood. Got it. Okay, got it. Thank you. Yeah, thank you.
Thank you.
Once again, call for questions. Any more questions?
There is one question. I can read it.
Please, yeah, please.
Kalyani is asking, this is to Praveen Nagar. How many numbers of frames are sufficient to split videos into subsorts? How many numbers? Yeah.
So basically, we have divided by 1 second small clip. So 1 second comprises approximately 14 to 15 frames. So the one subshort atomic, we call it atomic video unit, is basically 1 second length.
Thanks. I hope that answers the question.
Yeah. So that is kind of pre-processing. You are trying to maintaining the temporal dynamics present in the egocentric video.
Sure. Yeah, Dr. Vinith.
Thank you. Any further questions? If not, I wouldn't want to be the only one asking questions. I hope if there are any other questions.
Archit is asking something to KJ Joseph. So we have KJ Joseph here.
Yeah, I'm here. Hi.
Okay. So maybe I can read it out. He said, amazing technique you follow using a spreadsheet to record stuff. My question is how you maintain motivation of doing this record thing, because I guess you don't see any positive impact of this instantly and takes a lot of time. I usually lose motivation while maintaining these records. So yeah.
Yeah, I think so. I think Mike, response question to this, that's like, are you maintaining this record just because someone else asked you to maintain, or is it just because out of your own usefulness that you're trying to maintain this record? I think that would be another way to kind of position that question. So for me, like, I think the only reason why I use that is just to keep track of things for myself. And I've never been told to maintain a record by, I mean, in this format at least, by any of my collaborators. So, and I mean, initially I was using some kind of, HTML pages, and then like just notes, and then I mean, like it was a progression onto all these things. So, so I think, I mean, to answer you, I believe if you think, or rather, I mean, and the other part of the question is like we say something good about maintaining all these is all, I mean, such methodologically going about things only in a long time, right? So I think it's worth it. So once you get the, I mean, that positive kick out of maintaining all these things for one of your works, maybe then this will just be a habit in whatever you'll be doing henceforth.
Thanks. I hope that answers the questions to offer to Arpit. Yeah. So that's all from chat. Yeah.
Maybe is it okay to take 2 more minutes? Maybe just a couple of questions to the speakers. I know we have a tea break now. Is it okay?
Yeah. I think you can go ahead.
Okay. Maybe we won't spill over too much into the tea break, but just a little bit. Maybe one question for Soumya. Again, very, very interesting work, I think. I know Dr. Anand is also involved. But I was just curious, I hope is Soumya there on the call?
Soumya should be there.
Yes, sir.
Yeah, okay, great. Okay. Maybe one general question. Is it, I only realized that, yeah, the notion of looking at, say, VQA or problems such as this as one-way communication and trying to ask questions is interesting in general. Do you think such an approach would make sense for classification? Classification is also one-way communication, right? In some sense, you're giving an image to a model and it predicts. Can the model now go back and ask, do you want to know something more? Or do you want to know why this worked? Or do you want to know how much context was useful in my decision? I mean, do you see the usefulness of this approach more than just the VQA problem into a more generic approach for decision making in general, right? So VQA is perhaps in this context.
Right now, the context was to generate the questions. As you mentioned, these generation tasks can be extended towards explaining why the answer is generated. So it could be not just attention maps, which we are projecting back onto the images from where we obtain the answer, but also we can actually get a explainable text part to it. So why onto why that answer is answer to the asked question. So right now, the focus was more towards generating the questions and solving the one-way communication with respect to that. But as you mentioned, yes, this can be extended to giving explanations onto why the answer is the particular answer. So.
Got it. Okay. Okay. I see. In fact, you probably partly answered. I think that's an interesting thought, and you probably partly answered my next question. Is if transformers would be useful for such a task. I mean, considering this attention and things like that. Have you had a chance?
Yes, sir. Exactly. So yes, transformers are like one of the better solutions to this particular task. So yeah, future works might actually solve this task using transformers.
Okay. Thank you.
Thank you, sir.
Thank you. Yeah, thank you for answering. One question for Praveen. I think Praveen is here if I'm right.
Yes.
Praveen, one question on your work. Again, nice work. One question is, I mean, what kind of reward functions could be useful for the problem that you're trying to address? Because summarization, especially when you talk about personalization, I mean, can mean different things to different people. I know that you're probably taking user input. I wanted to also check if that can influence the nature of the reward function itself that you use while training. Did I make sense in the question?
Yeah. So for reward function, like obviously this reward function is something which is subjective to everyone. But ideally, we are having this pixel level information, right? So this distinctiveness and indicative reward try to capture that the selected subshot should be distinct and can reproduce the original video. But as a human, we don't do that. Sometimes in summarization, we select the summary by quite high level intelligence, like the trailer of the movie. I cannot generate the trailer of a movie from this pixel level information. You should have to have a high level intelligence. And often we have seen that the human focus on the surprising element present in the original video, which we cannot do it mathematically. So there is a lot of if and else for this kind of notion. So yeah, one thing you can do is that the personalization by taking just a feedback from the user is possible. But yeah, like it is having a lot of sense. Like the summary should communicate the story present in the video. So that is another future work or challenge, how you will incorporate the notion of story in the video. So that is the one thing which we are thinking in future, like how that human level aspect can be incorporated in the framework and try to generate a summary like this.
Okay, interesting. Thank you. Thank you for sharing your thoughts.
You're welcome.
And I know Pawan is not here, but maybe one question then for Daksh. Hopefully the last question for Daksh is, thank you again for the nice presentation and work, Daksh. Technically speaking, I was wondering whether to address the issue of anonymity, at least the way you were approaching the problem. Would adversarial perturbations also address the problem as it is? I mean, technically, you could address it the same way, right? You probably need to add an imperceptible perturbation that changes the class label, which in a sense is your objective also in this work. Did I get that right? Or maybe, yeah, you can.
Yes, this problem can also be framed as an adversarial attack problem properly, but that is what the work we are doing. We are actually making it a black box adversarial attack right now for targeting anonymization and activity recognition, and it good enough results. But here, since we had the models, we didn't model it as a black box attack. We actually model it as a white box attack since we had the trained model.
I see. Okay, got it. And I assume you would be looking at an untargeted attack, right? Am I correct?
We are looking at basically both kinds, targeted and untargeted.
I see. So you would want the identity to be somebody else's specific identity? Would that be of interest?
That so that can be that's not that much of an interest right now, but that can be really good interest when we are talking about in normal third person gate recognition, that if I can target somebody else and fail the gate recognition frameworks. So this we are looking as a gateway into the failure of normal gate recognition in biometrics. If from egocentric, then we can pass it on to the third person surveillance videos if we can do that.
I see. Okay. Okay. Got it. Thank you. Thank you. I think I was just curious about that perspective to this problem, but yeah, I got your answer. Thank you. Thank you very much for that. Okay. I know we have eaten quite a bit into the tea break. Any other questions for any of the speakers before we close this session and move to the next one? Okay. If no more questions, we can probably stop here. Thank you, Dr. Anand, again for helping coordinate this session. And congratulations to each of the speakers here again. Hopefully, you'll keep up the good work and also inspire others to publish at these venues going forward. Thank you very much to all the participants again. Thank you.
Thank you, Dr. Vineet. There is some announcement from Dr. Anil Tiwari.
I'm just actually, thank you very much, Dr. Vineet. I mean, you were coordinating this, the chairing this session so well. No, I thought, no, there shouldn't have been any other event. I mean, it was very interesting, summarizing the problem, interacting with the authors, and then, it was very, very nice. Thank you so much for being so nice. I
Thank
also
you.
express my thanks to all the panelists, other attendees, and also the authors who actually clarified many questions that was posed by the session chair and also by others. Thank you very much. So we shall be taking a break for about 10 minutes and we shall come back again at 4. Thank you. Thank you, Dr. Vineet.
Thank you. Thank you, Dr. Tiwari. Thank you very much.
Hello. Dr. Saket Anand, Roshan, are they there?
I'm here. Hi.
Yeah. So I'm sorry, actually, we got delayed because of some small technical glitch here.
Okay, no worries at all.
Anil Tiwari, I'm a faculty member in the Department of
Yes, I know.
I welcome all the panelists and participants. Some of them are, in a physical mode here in person, also online. Thank you for joining it. And I welcome Dr. Saket Anand and also Dr. Gaurav Sharma for chairing this session. Over to Dr. Saket Anand and Dr. Gaurav Sharma, please. Thank you.
Okay, thank you. I would need sharing privileges for my screen. I have a short presentation to make. If I can request the host. Okay, got it. Thank you. Okay, good afternoon, everyone. Can somebody please confirm if my slides are visible and they're transitioning?
They are.
Okay, great. So thank you again for having us organize this ICVGIP contest this year again. We had done one last year. Gaurav and I had again organized it with the help of students. So I'm Saket Anand. I'm an associate professor at IIT Delhi. And my colleague Gaurav Sharma, he's unfortunately unavailable because of time zone issues. He's in the US, and this would be like 3 a.m. in the for him. And he's affiliated with IIT Kanpur and TensorFlow as well. So in the presentation today, I will just be talking about the contest and the setup and how we prepared for encouraging participation. I'll briefly talk about the registrations that happened and what the next steps are. So the first task was an audiovisual retrieval task. So this is with the popularity of multimodal data analysis these days, we picked this task where we had audio video pairs, and the idea was to retrieve a video depending based on the audio and vice versa. So for this, we already had audio video pairs from which features were extracted and the embeddings were made available. And then the task was to learn embeddings in such a manner that the audio and videos could be used for associating one with the other. The data set was audio set ZSL. It's a large curated data set with about 23 classes and 80,000 training samples. Validation set was and validation and testing set were both about 26,000 each. The features were extracted from a pre-trained model and made available, and the evaluation metric that was used for is the class average MAP, and it's a combination of retrieval from audio to video and from video to audio, and an average of that. So this task was such that where the compute required was not very heavy, and at least some our baseline models were able to train on a CPU itself. And if needed, Kranti can add more details about that. So these are some examples. For example, dog, and of course the corresponding audio samples were there. Cat, car, clock, and these are some of the frames from the videos that were used. The next task was again with the popularity of AI on the edge. What we wanted was model compression through network quantization. So we had pre-trained models which were trained at full precision and or FP32, and these were trained on ImageNet on a high memory GPU. But then for edge devices, it becomes hard to run these for inference. And the task was really to quantize the network, but in a training and data free manner. That means that the training data was not accessible, and the models had to be quantized in order to have a large enough compression ratio while maintaining the same accuracy or as good an accuracy as possible. Again, this task was also picked in a. I mean, one reason for picking this task was also that the compute requirement was minimal. This could be run on a CPU easily, and these were the models that were used in the dev phase: ResNet 18, MobileNet v2, ShuffleNet v2, and then in the test phase, we released the pre-trained ResNet 50, Inception v3, and MobileNet v3. And the data set was, of course, just the validation set of ImageNet. And the evaluation metrics were compression ratio, which was basically the relative compression obtained with respect to the original model size, and the accuracy after quantization. So these two metrics were used for evaluation, and these are sample images from ImageNet. The third track that we had was an object detection track, which specifically the data set that we used were wildlife images from camera traps. So this was in the hope to inspire more vision applied to conservation or wildlife monitoring kind of applications. And this was an object detection task where a model had to be trained or fine-tuned using a reasonable GPU. And the data set was collected from the Leela.Science dataset consortium, and we took a combination of 3 data sets from there, and ensured that we were able to curate a reasonably balanced data set across these 20 classes. The images are reasonably challenging, and the data distribution was somewhat like this: training about 11,000 training samples, validation set which was about 1,600, and then a test set of about 3,200. And the evaluation metric used was, of course, MAP, which is the typical metric used for object detection evaluation. And these were the classes. There were some empty images, which often happens with camera trap images, and then there were common species which were detected. And if you see, many of them are small animals, which is harder to spot in an image. And some of the sample images are shown here. So, and it's also a mix of day and night images. We made sure that the data set contains reasonably balanced images between daytime and nighttime images, which the nighttime images are typically taken using an NIR camera with either an NIR camera or an RGB camera with flash. For the evaluation, we used this platform called Eval AI. This was also used last year in the contest, and we started we released the training set on October 10, and the test phase ended on December 17th, or so it was planned to end. During the dev phase, we allowed like a maximum number of submissions of 5 per day. This was across each track. and each team was permitted to register for many, all the 3 tracks, and each track would get, each team would get 5 submissions per day. So this was simply a text file or a JSON file that was to be uploaded, and the eval AI server would just evaluate it against the ground truth and publish the results. And there was an option to publish it either publicly or privately. And during the test phase, which we started around December 10th, based on the initial requests from the participants, and it ended on December 17th, and the maximum submissions per day were restricted to 2 in this during the test phase for all the 3 tracks. The prize money, the first prize was about 7,500, second prize 3,500, and the third prize is 2,000, and this was for each of the tracks. And it was supported by the Infosys Center for Artificial Intelligence at IIIT Delhi, and partly by TensorFlow. So along with this, we had also proposed the use of cloud credits and in a reimbursement model. I'll talk briefly about that a little bit more. In order to make it easy for the participants, participating teams, we did some preparation. So of course, there was a public website which was hosted and is accessible from the ICVGIP page, contests page, and we created GitHub repositories for each of the tracks, which was done by the organizers, and it was so the baseline models and the baseline code was released through Git, and the participants just had to download the code from the repository and download the data set, and they could just simply run it on Colab to reproduce the baseline results. Eval AI was set up, and there was a public and private leaderboard where participants could upload and just look at the results that they are getting versus the results that others are getting, and so on. We made we publicized this. Apart from the efforts that ICVGIP independently made, we additionally posted on social media in order to engage with teams. We created a Slack channel for participants for interactions between themselves and with the organizers. And we had a couple of video conferencing sessions where we basically showed we had how-to sessions for getting started with the baseline code available on Git, and how to use Eval AI in order to evaluate the model predictions and to see how other people are faring on the respective tracks. So with this, we had about 42 teams which had registered, and this is the distribution. On the left is the distribution of when the registrations happened. Most of the registrations happened in October, but then there was some in November and some in December as well. And from an institute-wise distribution, there was this is what it looked like. Many teams from KLE Tech. There were some companies which had also registered. Some teams from companies. We saw many IITs, IIIT Delhi, IIIT Hyderabad, and then College of Engineering Trivandrum. There are a couple of teams, one from outside India as well, one from ASU and one from UT Dallas, and then singleton images from many other places. So it was a pretty good distribution as far as the registration went. And in the registration form itself, we had we had sought information about which tracks the teams are interested in participating. So all the three tracks were permitted, and one team could participate in multiple tracks. So they checked all the check boxes which they are interested in. So this was roughly the distribution, showing interest in which tracks they were willing to participate in. And then we also checked whether there would be cloud credits for GPU compute and such. And most of the teams said yes. And finally, to basically decide when to do the test phase, we had given these four options, where most of the participants, most of the teams checked December 6th to December 12th. But then as we came closer to the date, there were some requests which were seeking extension. So we finally started the test phase on December 10th and December 17th, and ended on December 17th. So with all this, I mean, we got some requests for extensions. However, still during the test phase, we saw that the activity on the leaderboard and on Eval AI across the tasks was quite low, and based on some interactions, we understand that there was certainly conflicts with exams, because the semesters were shifted, and some teams preferred one time versus others. So for this reason, we are not ending the contest yet. And what we have, after a discussion with the program chairs, we decided that the test phase dates will be actually extended by a few weeks. So we'll have a test phase during the during the third week of Jan 15th to Jan 21st. And we'll open the registration. We have already opened the registration, so fresh teams can also register. So now if we see a good amount of activity, then on the Eval AI leaderboard, we will also extend some support for Collab Pro subscriptions for 2 months for each team. And at the end of the contest, the organizers, we have thought that we'll co-author a paper with the winners and submit this report onto archive, and maybe also submit it to the next conference, either in ICVGIP or at ICVGIP, but that will have to undergo a review process, and we'll see how that goes. And of course, every participating team and individual members get a participation certificate. So this is the plan that we have now, and we hope that we'll have more participation, and we look forward to your entries, and engaging with the organizers in any way that you think might help. Can be done via either email or the Slack channel, or our social media. So I think with that, I would really like to acknowledge the organizing committee. So apart from Gaurav and I, who were really just looking at the overall contest, I mean, there are a lot of people who contributed in creating the website, creating the GitHub repo, enabling Eval AI, the evaluation AI portal, and a lot of other things. Now, so finally, I would say that all this infrastructure that has been built with the website and the GitHub repo and the email, we will be passing it on back to ICVGIP, so that future contests can also be easily implemented using this. So with that, I'll just end my presentation here. Thank you very much for your attention, and I'm happy to answer any questions that there might be. So are there any questions about the contest?
Yeah. Hi, Saket.
Hi. Hi,
Uh,
Parag. Yes.
Hi. So will the information about the contests that will be updated on the contests website as it is right now?
Yes. So the dates are not posted yet, but we'll post it tonight, and we'll open up the Eval.ai portal again for the dev phase, and the test phase will be opened in January 15th.
And will you have, say, another round of I don't know, help calls or something of that sort, or are
Absolutely.
you?
So yes, so we'll do one round of advertisement if people want to register again. The registration is already open, and we'll have an interaction. And in fact, we have a recording from the previous interaction about how to use Eval.ai or how to use the repo on Colab and such. And we'll just post it, and we are happy to host another live session as well.
Okay. Thank you.
So are there any other questions from the attendees? I'm happy to take them, and you can also, reach out to any of us. Our emails are there on the website, and the Slack channel link as well. Okay, I think I suppose there are no more questions. So, Parag, I think the GitHub repo, and so we have created this one Gmail ID, and there's a GitHub repo associated linked with that, and the website that you know of. So we'll, after this contest, we'll hand it over to you for next editions of the contest.
Sure. Yeah.
Okay,
So,
there's one question.
Go ahead.
Will the leaderboard for AV retrieval be made public? So the leaderboard should be public, and in fact, the submission, the teams have the option to make it either private or public. So whatever, I believe that it should be public by now. Can one of the volunteers please confirm? Ashima, do you know if it is public already? Or Kranti maybe?
Yeah, I think it's public, but I'll just check and I see if it is not public.
Yeah, so in case it is not public, Dhruv, this is trying to answer your question. If it is not public, we will make it public. So the dev phase will be made public, and the test phase. The test phase will make it public only during the test phase. I see. Okay, so we will make it. We'll make it public through. So he's saying that the leaderboard for the other two contests are public, but not for AV retrieval. So we'll make that public. It must have been an oversight. Okay, I'm sorry, Parag. Were you saying something?
No, I was not saying. I was just reiterating that all this will go up on the ICVGIP website. It's the contest website is already linked, and so everything will be visible to whoever visits the ICVGIP website or the contest website directly, and people should just participate. Yeah.
Okay, cool. Yeah, so the tracks that we picked, these were sort of a combination of where GPUs might be required versus where we can do some some things just without a GPU altogether. So I'm hoping there will be a lot of participation. We'll see. Cool. I think we started slightly late, but kind of on time. I think we had a 30-minute slot, right? Okay, thank you.
Thank you, Saket. Back to the organizers.
Thank you very much for your very nice presentation. We'll be back in a few minutes. Maybe that Dr. Gaurav is coordinating with. Hello, am I audible? Yeah. So, Gaurav, so we might be going for the next. Okay, two. Yeah. So, Professor Chaudhary will be joining in a few minutes, and he will be giving a talk for about 30 minutes. Hello, Parag, am I audible?
Yes, you are audible.
Thank you.
So everybody, please stay around. We will just start with another session. Yes. So good afternoon, good evening, everyone. It we will now have a session by Professor Shantanu Chaudhary, where he will introduce the Technology Incubation Hub at IIT Jodhpur. So the TIH at IIT Jodhpur is focused on computer vision, augmented and virtual reality. And it opens up some very interesting opportunities for researchers, professionals, and academicians working in this area in India. I will pass on the stage to him so that he can tell us about the TIH.
Thank you, Parag. I'm audible? Yeah.
Yes.
So I shall tell something more about this hub with the help of a set of slides. So can you please give me the permission to share?
Can the host please transfer presentation rights? Yes.
Okay. So for ICVGIP at Jodhpur, this is an introduction for Technology Innovation Hub at IIT Jodhpur, which has been set up as a Section 8 company and established under a national mission of interdisciplinary cyber physical systems, which is a national mission under Department of Science and Technology, Ministry of Science and Technology, Government of India. We have given the name to this hub, iHub Drishti Foundation. So this is primarily focused at computer vision, AR, augmented reality, and virtual reality. In that sense, graphics is also integrated in the whole scheme of things of these hub. So in a sense, we have picked up this as our mission, that trusted vision for secure and better living. So the statement goes like this: to become the most coveted self-sustaining technology destination in CV, AR, and VR in the country, with a nationwide footprint, nurturing and supporting cutting-edge research and innovative technology deliveries through startups, MSMEs, and direct execution of projects. So therefore, what is very, very important that I want to communicate through this short introduction to iHub Drishti, that it is not a company for IIT Jodhpur. It's a Section 8 company which belongs to the CVPR community of the country. In fact, CV, graphics, image processing, pattern recognition, that entire community which is linked with computer vision, augmented reality, and VR for the country to come together and work together. This is the whole objective. In fact, each of these hubs which has been created by DST, this is a more outward looking and not inward looking, in the sense that these will work as a center which would bring together expertise across the country so that we can deliver new scientific knowledge, projects, and products for use of stakeholders in a variety of fields. And this is not just necessarily limited to the researchers in India. We are open for collaborations with researchers who are located anywhere in the world. The only limitation for that is we are not in a position right now, because right now most of our funding is through government funding, directly fund any of the researchers abroad. But if they are as a part of collaborators, they can work with us, and even when they, we can support when they are visiting in India for involvement, any kind of activity and involvement with Indian researchers, that can be supported through this hub. In fact, we are also in dialogue with NSF US to set up a strategic alliance with the researchers in the domain, not only just CV, AR, VR, but also other domains broadly, globally under the umbrella of the Cyber Physical Systems Mission, so that this alliance can have an international character as well. And in future also, if this company, since it's a company, as a company grows, there can be all kinds of exchanges which are beyond the rules of Government of India, which is more like a open space for collaborative research. These are the different areas. What we say that there are horizontals and there are verticals. The horizontals are data collection, curation, and annotation. Then real-time computer vision systems, which are primarily, we are looking at hardware development for computer vision. Then the questions is of dependability. So therefore, trustability and dependability of computer vision systems is something, is one of these horizontal running through the different vertical application domains. And the fourth is seeing and sensing. Therefore, they are also what we are looking at, that in terms of sensor development, a part of the sensor development, improved camera systems, also computational imaging, those kind of aspects is covered as part of these horizontal, which address different vertical domains. The verticals which are directly linked with computer vision is computer vision for autonomous systems, computer vision for healthcare and biosphere, computer vision for document analysis, then CV and VR for Industry 4.0. Any questions? There is some voice. And fifth vertical is augmented reality and virtual reality for any applications, including games and other spaces. And the sixth one is Rakshak, which was a special project initiated by DST for AI applications in COVID. If you look at objectives, these are all objectives of IHub Drishti, and I have highlighted the most critical objective, that promote innovation in computer vision, AR and VR, and use of technology foresight to predict and develop new technologies to address some of the national issues and support and nurture startup ecosystems. And the most important part of it is that it's therefore, it has, in terms of the vision, it actually targets towards a kind of a transformative contribution through CV, AR, and VR at least in the Indian ecosystem to start with. And it's an ecosystem. So what we're talking about is it's an ecosystem. So we are expecting to having academic collaborators, both national and international. We have domain partner institutions and research labs, that is the national labs, and in fact, it can come from any domain for that matter, because maybe medical institutions, agricultural institutions, space. So domain partners at one end. Then startups, MNCs, and local industry, MSMEs and local industry, as well as user agencies. User agencies could be line ministry, because this is something which has been very specifically identified, that line ministries can actually come to technology hubs for solving their problems. So many of the vision problems related to any of these, say, agricultural domain, industrial production domain, manufacturing domain. So these line ministries can look for such technology solutions from the hub. And hub is obviously not, hub is just located at IIT Jodhpur, but hub belongs to the community who are here for In fact, that is the key reason why I'm making this presentation as part of this conference. What are the grand problems? Because DST wanted us to identify some of these grand problems. And so one is building dependable vision systems for navigation and monitoring. Another is computer vision systems for healthcare, immersive and experiential technologies in the space of medical domain, heritage, haptics. And why we are bringing in dependability is today, dependability is a very critical construct because I can recognize, but what I'm recognizing, I need to know my probability estimate of any recognition and action that I'm providing with has a significance and explainability so that they can be used by an end user with a certain kind of a confidence. So if any system fails, it has to fail, but it also, we need to have an assessment when the systems are failing. I think this is one of the key problems which are preventing many of our techniques to be deployed at a practical applications in a very automated system. But even if it's not an automated system, even if it's like in a kind of an AI augmented scenario that where human beings and AI are working together, they're also an indicator of the fact that how dependable is the decision. Because in almost all of the cases, computer vision is making a decision. And even when you're using AR/VR system, the guidance or the involvement of AR/VR in solving problems also has a certain amount of a possible error can be involved over there. So we need a kind of assessment of those errors, that what we feel that when we develop an algorithm or a system as a unifying thing, we would like to make them dependable, and dependability as a layer can be used in these spaces. So this is a kind of an overall overarching vision for the developmental work of these of this hub. So therefore, the whole idea is to we are working through vertical coordination committees, and we are creating a pool of experts in this space and setting up state-of-the-art labs. And this Section 8 company, which is also important point I want to communicate to all, that Section 8 company is admitting now members. And all academicians who are involved in this space and people from research labs can become honorary member of iHub Drishti. You can just need to fill up a form. Once you become a member, you are an active participant in all of these activities. In fact, we can jointly bid for projects. We can jointly support any startup you have. We can support the startup. We can create an ecosystem. We are also creating an ecosystem to bring in funding support for those startups. So we can create startups together. We can do a project jointly with an industry. And if you think that we need to do a project as a consortium, then these iHub Drishti will create a consortium. iHub Drishti has also provisions for supporting summer interns, maybe not only within not just at IIT Jodhpur, but across the country. And also there are fellowships available. And it has already supported through a number of projects. In fact, about 20 projects it has already supported across the country at different institutions. And more such projects calls are there. So you would like all of you to participate, become member of iHub Drishti and work on projects and delivery of solutions to the industry, to the line ministries, and also at the same time provide a thrust to the startup ecosystem in this space. So lots of startups are also already member of this iHub Drishti, and we want many more startups that you are involved in or you might be knowing. You can also ask them, request them to become member, because then we can create an ecosystem for delivery. See, we academicians do research, and this research we say is at the level of TRL 3.4. If we have to take the research from TRL 3.4 to TRL 8.9 and become industry ready, we need to create an ecosystem where startups, industries all can come together and link up and create a strong bridge for this translation. And India, it is very, very important because we are numerically large but scattered. In recent times, the number of people working in this space has increased substantially, but also there is a need for the people who are distributed to come together and work together. If we can come together and work together, we can definitely make much greater impact than working individually. In fact, this is the whole objective of this structure that has been created. So we are doing collaborative technology development through extended partnership model. And I've talked about the partnership. There are onboarding industry members and who can take advantage of expertise of multi-institutional faculty group, co-development of technologies and products through joint investments, create proof of concepts with the support of the foundation for the client, and bid jointly for delivery of service or a product. So all of these are possible where industry can come together and work. And this is also, we are involved in a entrepreneurship development also. Technology Business Incubator of IITJ is the incubator identified. And we also have dedicated innovation accelerators, entrepreneurship in residence scheme that we have already worked out, and startups and spin-off companies. So any of the faculty members really interested in from any institute, interested in to have a startup initiated and supported, ICVGIP would be interested to look at that and can enable, in fact, incubation, because we are open to even support remote incubation, but they have to be registered with Technology Business Incubator Center of IIT Jodhpur, because we had to, there is a assigned incubator as per DST requirement, and TISC is the assigned incubator for IIT Jodhpur, for ICVGIP. So we actually developed this Campus Rakshak as a service, and for epidemic simulators, Campus SIM and suggestive action. This is also as a contact tracing app, and this is in terms of testing and health badge for generating the reporting scheme and database. This is primarily for COVID application, but why I want to show this example is this whole service was built through a collaboration between IIT Kharagpur, ISC Bangalore, IIIT Hyderabad, and IIT Jodhpur. So this is the kind of a thing that we are targeting, where we can multiple groups from multiple institutes can come together and work on projects. This is a dependable vision-based autonomous system. These are some of the projects which has been already initiated with the DRDO as a partner. Many more such projects are on the pipeline. And there are these now call for proposals which are live. These are actually in the area of AR, VR. And in fact, after my presentation, I shall ask Parag also maybe to add something here. So first is anatomy project umbrella. So this is anatomy project is essentially to create mixed reality applications which would facilitate anatomy teaching for medical students. And also that tool will be also useful for understanding some of these anatomy of the patients, and also maybe analysis of some of the critical anatomical issues and problems related to diseases. So this is a mixed reality. This is not VR. This is not VR or AR kind of a stuff, but a mixed reality in the sense that there should be an experience which is much more than like a VR-based kind of a tool where it is completely visual. And here it should be more immersive. And how to bring in the mixed reality immersion, that's exactly the challenge of this project with a specific application domain. And we are looking at this project as a kind of collaboration between medical professionals as well as graphics and AR/VR specialists and vision specialists as well. The next another call is that improving doctor-patient communication using VR, because doctor-patient communication, while we discussed with the doctors, we found that doctors are looking for tools which can facilitate doctor-patient communication, because communicating with patients with empathy is a requirement. And how can a doctor, a trainee doctor or a student doctor can really train himself into this kind of a scenario? So therefore, it requires a kind of a interactive avatar to which it might be reacted, or a group of avatars he might be reacting, and they may have the expressions. They can also be a chatbot, and therefore there is an image synthesis in terms of facial feature synthesis, facial animation, speech synthesis, understanding the expression of the doctor and reacting to it. So it's a really challenging problem for which is targeted towards improving doctor-patient communication using VR. So VR character is basically the doctor is talking to the characters in VR space, and it has to be interactive, and so that he can get a feel of the real life and get trained. The next is we have the project also in terms of under haptics-based medical simulators for palpation and telediagnosis, because haptics can turn out to be is a tool in AR/VR space and also has a huge medical application. So this is also a project call in terms of haptic-based palpation measure and simulations for palpations and telediagnosis. And therefore, all these calls are now open, and there you can access the calls at the site https://ihubdrishti.ai, and please submit proposals, maybe in a consortium as well, because in most of the cases, in this case, you may need a doctor as a member, and maybe there can be a startup or a company associated with it. So it can be a consortium of academicians in the area, academicians or researchers in this area, as well as doctors and maybe startups or the companies together submitting a proposal, because these kind of combinations we shall support, and we encourage such combinations to be built. The other call was content creation for solutions for AR/VR. This call is closed because we already got submissions and we are going through it, and we shall take a decision on them soon. The other call is this has been expression of interest from industry partners, because if there are industry partners, we are also asking for their interest when there's a project from external agency. This is a project design and development of virtual museums of Rajasthan. This was from Rajasthan Government Department of Culture. And this project has come, and we actually asked for bid from the companies who are linked with iHubDrishti, and based on that, we shall allocate this project. These are the calls for likely to come. AI/ML-driven document image analysis for supporting education and research. Here, our stakeholder is National Digital Library, and the collections of National Digital Library will be available for this purpose. Then development of data bank for medical imaging and digital pathology. Industrial CV and AR/VR technologies for manufacturing education, both R&D and education and workforce development. Document identification, verification, or face verification while on go. Then also there are a number of other calls which are supposed to come, and these are some of these problems which have been listed. And the key point is, please, because we are sending mails to the entire ICVGIP mailing group, and please respond to the mail which are going from iHubDrishti, and Chief Technical Officer of iHubDrishti is sending most of the cases the mails. So my appeal to all the entire ICVGIP community is, please respond to the mails, please come forward, become member of iHubDrishti, participate in project, participate in discussions. We should also plan to organize community events where and support community events soon. And so participation of all the researchers in this domain is critical for success of the hub. And that's the reason we would like you to be part of it. Just the way you have been part of ICVGIP and IUPAI community, there's an appeal to this ICVGIP community to come together and work together. It has been conference is one part, but this now TIH provides us an opportunity for working together to work on research problems together, work on technology development together, work on supporting startups together. So let's make use of this opportunity and take the whole initiative forward. Thank you. And these are all different kinds of other activities which are happening. And so thank you. And if any questions, I should love to answer the questions, queries. And Parag can also add anything if you have. Parag, then Uma, please add anything you would like to. Because both of you are involved with ICVGIP. So
Yeah, I would just reiterate that research in AR, VR, and computer vision is becoming more and more interdisciplinary. In that sense, the TIH ICVGIP is an excellent place to find people of disparate specializations and expertise and form consortiums that can solve larger problems which are otherwise very difficult to handle. So the open research calls or open project proposal calls are really good places to get this started. So please respond to those in large numbers and participate. Thank you.
I think I also echo the words said by Parag and Shantanu, and really the TIH ICVGIP is a very excellent platform for young researchers, startups, and many seasoned researchers to explore different areas and come to some integrated solutions. And I appeal all community people to use this excellent opportunity and then respond to call for proposals, call for project proposals.
And you also be member of the ICVGIP. This is also an appeal. So you can become member of ICVGIP. You can also have your startups and others, encourage them to become member, to take advantage of the problems which are coming to ICVGIP from different government sources, and also to get supported through the expertise which is available within ICVGIP. Thank you.
I see a raised hand from Chetan. Chetan, do you have a question?
Yeah, question and comment all request. See, I think it's a very good platform. I have received for giving, let's say, a platform to the vision and graphics community. I see that there is already some collaborative project with CIR and the other that Professor Chaudhary mentioned. But I would like to understand, or if it is already there, maybe. I mean, I think there is a good need coming from the industry where it's perhaps or mostly not sufficient for a single researcher to meet. But if ICVGIP can become, let us say, conduit in between as a platform to where multiple researchers can actually form a consortium and deliver through ICVGIP, I think that's also let's say sort of a big need.
Chetan, that is exactly what we are looking at. Okay, so this CARE was basically DRDO, lab and academicians working together. Those problems are not something funded by CARE. It is something joint work which is happening together, and maybe in future that can happen delivery. So all the proposals can be consortium proposals, and if you want some consortium to be created, and you are proposing that, okay, together with an industry, will take up this problem. Can IHAP-Drishti facilitate that? IHAP-Drishti is open for facilitating that kind of an initiative.
Yes, I'm actually, when I was saying that, some very loose analogy that I have is sort of an IDEX kind of a stuff. So where, let's say, the defense industry says that, okay, we would like this thing to be made. Can a consortium or somebody can made, and we will, I mean, in their case, they do not really, I'm not sure if they have a very big funding plan also. But in the case of IHAP-Drishti, we can also say, okay, this is, let's say, the challenge problem to be completed in next 3 years. Please propose a consortium with this much amount we are willing to fund, and let's make it. And then
Actually, these mixed reality problems, the calls that we have put across for mixed reality tools, teaching tools for medical profession, these are actually pretty challenging problems, and we're looking for those kind of consortiums to come forward to take up those challenges. And these problems have been framed in consultation with the end users, that the doctors, their need, there has been need assessment workshops, and on the basis of need assessment workshops, these challenges have been framed.
Right. So I perhaps in the future, I will try to suggest few more similar problem where I can even actually actively contribute.
Yeah, please,
I'm not
please.
anatomy, VR, I may be that active, but yeah, in the other more core computer vision kind of problems.
Absolutely. In fact, that is why there is a vertical on autonomous computer vision that is already there. These came under vertical AR, VR for applications.
Okay, thanks.
Any other questions? Yeah, okay, I think you can now move forward.
Yeah, okay. So thank you, Professor Chaudhary, for that introduction to the TIH. I'm sure everybody will rack their brains about that for a bit and hopefully will come forward and participate in the TIH. So now moving ahead with the remaining session for the day, I want to invite Professor Uma to take over the session for the IUPRI Dissertation Award talk.
Yeah, sure. Thank you, Parag. Am I audible?
Yes, yes.
So we are again, yesterday in GBM, we announced the doctoral dissertation award. The Ishant Sanu is the awardee, and I request Ishant, do you have a share options? I request the organizers to provide a share options to him and make him panelist.
Good evening, everyone.
Yeah.
I
Before
just got the
start,
share option.
Ishant, just a very brief bio of Ishant. Ishant is currently a research scientist in Visual Intelligence Department of I2R A-Star Singapore. He previously did a doctoral fellow in CSE department at NUS Singapore. And he received his PhD from CSE department IIIT Delhi under Chetan Arora. His thesis is optimal inference algorithms for higher order MRF map problems. So Ishant has two main tracks, CVPR 16 and 18 papers, as well as ECCV 20 papers. So he received a doctoral dissertation award by IIIT Delhi in 21 and Dean's Award for Innovation, Research and Development during Foundation Day in 2019. He also received the Vishwesvaraya PhD Fellowship from Ministry of Electronics and Information Technology, Government of India, from 2015 to 18. So he has received travel grant to CVPR 16 and 18. So we are eager to hear about your thesis. Over to you, Ishant.
Thank you, Professor Uma, for the introduction. I would like to thank the IUPRI team for giving the award. I am deeply honored to receive this award. And I would like to thank my advisor for his continuous guidance and support.
Professor Arora. So I'll just share my screen. Yes. So I'll be presenting my work during the PhD, which is optimal inference algorithm for higher order MRF problems. I done this work under the guidance of Professor Cheta and collaborators Professor S.N. Maheshwari and Professor Praksika. Many problems in computer vision can be modeled as finding the best labeling configuration. These labels can represent different things based on the problem. For example, for object segmentation problem, label is the object class to which a pixel belongs to. For the stereo correspondence problem, label is the disparity. If we model this problem as MRF map problem, then finding the best labeling configuration boils down to minimizing the energy function E, where E is equal to sum over C WCLC, where C is a clique, WC is called clique potential, and WCLC is the cost of assigning labeling LC to a clique C. As we can see in the figure, the clique can be of different sizes. And this problem is NP-hard in general. So based upon label and clique configuration, MRF map problem can be categorized into subcategories. MRFs with the MRFs with the cliques of size 2 are called pairwise MRF, and MRF with the cliques of size more than 2 are called higher order MRF. Based upon the labels that they can handle, we can call them two label or multi-label MRF. Further, they can have two types of clique potentials, either submodular or non-submodular. The agenda of my thesis is to improve the higher order MRF map inference problem for two label and multi-label MRFs with some order clique potentials. In recent years, deep learning have shown promising success for variety of vision problems. These architectures are based on convolution neural networks. Convolution operations are done by highly regular kernels, due to which the low-level information, for example, edge or boundary information is lost at the lower resolution layer of the network. Such information is required for reconstructing the boundaries, for example, in object segmentation problem. We can use MRFs to incorporate such prior information available to improve the quality of the results. As shown in the figure from one of our experiment on object segmentation task, in which we can improve the deep learning result by applying the priors and doing the inference for using MRFs. In any video or image, neighboring pixels are contextually dependent. And neighboring pixels are contextually dependent. It has been adequately shown that modeling the dependency among large group of pixels improves the quality of the results. As shown in the figure from one of our experiments on interactive segmentation task, in which user provides interaction about foreground and background, and for a given input image, we are required to segment the foreground and the background. As we can see, if we increase the click size, the quality of the results improve. Therefore, we are required to develop higher order MRF map inference techniques. We have worked on three important aspects of this problem. Firstly, we worked on two-level inference methods for higher order MRF map problem, in which we improve the tractability of a state of the art from 16 to from click size 16 to 1000. Secondly, we work secondly, we improve the quality of the results by including the smoothing priors, which can be done by including a small cliques along with the large cliques, for which we have proposed a unified framework to handle both large and small cliques. Thirdly, we have worked on multi-label MRF map inference problem, in which we improve the tractability of a state of the art from clique size 4 to 100 with 16 labels. Label 1 and label 0 for a pixel can be seen as inclusion and exclusion of a pixel in a set. Therefore, WC can be seen as a set function. If we assume the clique potentials to be submodular, then energy can be minimized in polynomial. Therefore, minimization of energy E becomes minimization of some modular functions. Before we go into actual minimization of some modular functions, let's look at how do we minimize a single submodular function. For that, in abuse of notation, first we define for a vector x, we define a set function x, where xu is the sum of all elements of x, which have indices in U. And now we define the base polyhedron BF as a set of v-dimensional vectors x, where xu is less than equal to fu and xv is equal to fu. Any point in this base polyhedron is called base vector, and any extreme point is called extreme base. We can find the minimizer of some model function f by finding a min-norm point in the base polyhedron BF. And the fastest algorithm to find the minimum norm point is MNP algorithm or min-norm point algorithm. So MNP maintains the solution vector as convex combination of extreme points. At any iteration, it adds, it enlarges the current set of vectors towards origin by including a new point Q, which satisfies that the solution vector X and Q has minimum dot. And after adding this new point, we find the minimum point in the current set of extreme points. And the algorithm terminates when the solution vector X has norm equal to the dot product of new vector X, Q and solution vector X. Theoretically, we can apply MNP for doing MRF map problem, but typical size of vision problem has million of pixels, which requires matrix inversion of million by million matrix. And also high degree of polynomial running time complexity makes it intractable. So as we know that MRF map problem is minimization of some modular functions. So we show that for a sum modular function f, defined as sum of modular functions fc's, then for a given vector, x in base polyhedron of f can be decomposed as sum of yc's, where yc's are belongs to base polyhedron of fc's. Now the norm of x can be minimized by applying block coordinate descent over blocks, where blocks correspond to yc's. And each block is minimized through modification of min-norm point algorithm. And we proved that this algorithm converges to the optimal. We ran our algorithm for interactive segmentation task. We took the input image of size 150 cross 200, and the interactions are given by the user. We have taken three average click sizes from 30, 100, and 700. As we can see, if we increase the click size, then the quality of the results improve. And even at the 700 click size, our algorithm only takes 46 seconds. Often now, let's go to the second problem. Often in computer vision, including the small clicks as smoothing priors improve the quality of the results. But such a configuration has million of small clicks, and in principle we can run SOSMNP, but it does not scale well because of the large number of small clicks. So now let us look at some observation for current methods. So SOSMNP does not scale well with number of clicks, but scale well with the large click size. On the other hand, GC or generic cuts does scale well with the number of clicks, but does not scale well with the large click size. So the natural question to ask is, can we use GC for small clicks and SOSMNP for a large click in a combined framework? So for that, we need to find out some kind of mapping between the free variable of these two frameworks. So GC models the problem as flow problem, where it maximizes the objective UP, where UP is bounded by these constraints, where the only free variable is VCP LCP, where LCP is the labeling of pixel P in click C, and WCLC is the cost of assigning labeling LC to WC. So, so GC uses this objective and model it as flow problem. On the other hand, SOSMNP maximizes the sum of negative elements of vector X in base polyhedron. We have shown that these two free variables can be mapped to each other exactly. But after finding this mapping, can we use GC and SOSMNP in a common framework where small clicks are optimized with GC and large clicks are optimized with SOSMNP? The answer is no, because GC minimizes L1 norm of X and MNP minimizes L2 norm of X. So for the optimality of the result, both the algorithms must optimize the L2 norm. So the question now is, how do we output the L2 norm solution using GC? So if we look at GC intuitively, for each pixel, it has metal ball at a certain height, and there's a magnet at level 0. As the inference progresses, the metal balls come as near as possible to the magnet, and they hangs at a certain height due to respecting the constraints. So after inference, we pick the balls at the source and the sink, and then put the another two magnets at their mean. So one is put at the mean of the source side, and the other one is the mean of the sink side. And we keep on repeating this algorithm and kind of do this divide and conquer until we find the minimum norm point. After finding this method for finding the minimum norm point for small clicks, we plug this method into our original block coordinate descent framework proposed earlier, where small clicks are optimized using GC and large clicks are optimized using MNP. And this again converges to the optimal we have shown. We ran our algorithm for object segmentation task, where the input is corrupted with a bit of Gaussian noise, and we fine-tune the segment with these noisy inputs. Even after the fine-tuning, the segment results degrade. So first we apply the pairwise prior and run GC, and the results are shown in the fourth column. Then we apply only the large priors and run our SOSMNP algorithm. The results are shown in the fifth column. And once we apply both the small and large clicks, and run our hybrid algorithm, results are shown in the sixth column. As we can see, the quality of the results improve if we use both the priors, small and large cliques. Now, until now, we have seen the inference for two labels, but often many problems in computer vision requires to label a pixel from a predefined set of labels. And to model the such problems, we require a multi-label MRF. For example, serial correspondence problem, it requires multi-label MRF where the disparity can be represented by labels. And also the semantic segmentation task can also be modeled using a multi-label MRF problem. So the standard way to solve any multi-label problem in MRF setting is by converting them into two-label problem using encoding, where for each label, we create L number of binary variables, and the labels are defined as follows. For label 1, we represent it as 1 followed by 0, then two ones and followed by 0. Such an encoding is respects the some modularity of the clique potentials. That's why we use it in such a fashion. But the problem is it increases the problem size by a multiplicative factor of number of labels and introduces exponential number of extra states to the 2 to the power n L minus L to the power n, many extra states, and which do not correspond to any state in the original submodel function. We call these states to be invalid states. Now because on these invalid states, there is no value for this function. So if we extend our function on these invalid states such that the overall function is submodular. For that, we define S bar as for any invalid state S, we define S bar as the state as a valid state which has minimum number of ones and contains S. Now we extend the submodel function f at invalid states as sum of S bar plus cardinality of S bar minus cardinality of S multiplied by a very large number L. Now the solution vector X can be represented as sum of convex combination of invalid extreme points and valid extreme points. Any invalid extreme point has many large values, and which creates floating point precision issues while running MNP algorithm. Now we define an invalid elementary extreme point which has only two large values adjacent to each other. And we have shown that any invalid extreme point can be represented as linear combination of elementary extreme points. Further, we have shown that elementary extreme points, the number of elementary extreme points is n times L. Then we show that linear combination of all elementary extreme points can represent any convex combination of exponential number of invalid extreme points. And minimum norm point in the convex cell of invalid extreme points can be found by computing a max flow on a simple flow graph, which I'll show in the next slide. So this is the flow graph that we create, where the blue edges are elementary invalid extreme points. And by finding the flow in this graph, we can find the minimum point of exponential number of invalid extreme points in only linear time. In fact, this graph has very simple structure which can be exploited, and we don't need to run the flow algorithm, which takes n cube time. Rather, we can run a dynamic programming algorithm which takes only n log n time. Now the X is represented as convex combination of invalid extreme points and valid extreme points. Now we can run the block coordinate descent algorithm on invalid block and valid block. For invalid block, we compute the flow on this graph. For valid block, we just run the MLP. Now we show the efficiency of the proposed algorithm. So first we compare our algorithm with the vanilla SOSMLP, such that if we are to encode the problem from multi-level to two-level and directly apply the SOSMLP, then the result is shown by this orange curve. It takes about 8,000 iterations to converge. And if we apply our compression, then our algorithm only takes 800 iterations to converge. And even after a huge number of iterations, MNP does not converge to the right point because of the floating point issues. And as we show in the figure 2, that our algorithm converges to the optimal point. Then we run our algorithm for semantic segmentation task. We compare the results with the DeepLab v3+, which is a state-of-the-art semantic segmentation model. We corrupt the input with a bit of Gaussian noise and fine-tune the DeepLab v3+ on these noisy inputs. And we can see that the results degrades even after the fine tuning. Now we apply various size of priors and run our algorithm. First, we apply pairwise prior and run the graph cut algorithm. And the results are shown in the fourth column. Then we take two kind of potentials. One is we called absolute potential and the other one we call concave potential. Take two configuration, small and big, and for small absolute potentials, the results are shown in the fourth column. Then we take a concave small potential and the results are shown in the fifth, and vice versa. These numbers are on the top right are the running time in seconds, and this is the IOU value for the results. Yeah, thank you. Please ask if anyone has questions. I think the mic is muted.
Sorry. Yeah, excellent work. So maybe we have time for a couple of questions. Please post your question at the chat box.
See the questions.
Yeah, like I have one question.
Yes.
So have you tried with like map MRF can be modeled for many problems? So other than segmentation, do you have any work?
Yeah, I have applied the multi-level MRF model for serial correspondence problem as well. Yeah, the results are in the main paper.
Any other questions?
I'm Anil here.
Yeah, please.
Yeah. So very nice work, Ishan. Congratulations for the award. Just curious to know that when you were representing 1, 2, 3, and up to 6, I had seen that they were represented by certain pattern. 6 was by 6 ones, I guess. something like that, no? Followed by all ones were separated by commas. Am I right? Am I audible? I'm sorry.
Yes, which slide?
Yeah. I don't remember that slide number, but I remember that no, you were talking about representation of some numbers like one
Okay,
by
yes.
one
Okay,
followed
okay,
by
yes, this
zeros
one.
and two by double one and
Yes,
something.
yes, 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 yes.
Yeah, this one.
Encoding, yes, yes.
I was just thinking that no, if have you also, I mean, is this a standard way of representing or it has some impact if the way it is being written, if this can be a different way, if there can be a different way, and what will be impact of it on the overall performance?
So because the function has to respect the some modularity, so yeah, I think the whole community have put a lot of effort in representing the or coming up with the encoding which has less number of binary variables, like order of log n, for example. This is the order of n. In fact, our one of our reviewer also pointed out that, and we kind of spent 2 weeks thinking about it and did a lot of survey. It's very, I won't say impossible, but we and our community have not found any encoding.
Thank you for replying that. I don't have any more questions, Dr. Uma.
So any other questions?
So I have a question.
Yeah, yes.
I'm not visible, perhaps. Yes, hi. Hi, Shant, and congratulations, of course. Those results that you were showing, right? The standard segmentation results that you were showing,
yeah,
was the beginning, which had the fence in front of the sheep.
Yeah, yeah.
Can you go to that?
Yes, no.
Yeah, where you compare with the ground truth and what you get and versus what the deep network fits and so on.
Yes, this one.
Yes, this, yeah. So I see that the fence is there in the ground truth and it's missing in your reconstruction. So what would it take to get those?
Yeah, because it's because the cliques, the image is very noisy, and the algorithm that I use for creating the cliques, it's either, if it's going to take that thin line in a clique, then there'll be a lot of small cliques only. Like it's not possible to get big size of clique and
Which is fine. I get that it's a limitation of the way you have formed the cliques in your, or the way in which it is formulated using MapMRF perhaps. And it is
No,
not?
it's a
No?
clique. It's a clique. It's a clique.
Okay, so it's the cliques. Okay. Now these fine scale details are obviously not captured by the deep network thing either, is my guess, perhaps.
Yeah.
Right.
Yeah.
So what do you think is the solution to this? If you want to get this absolutely as close to ground truth as possible, there is scope for improvement here. So what would make it better?
Yeah. I think what I have understood is like deep networks are more like intuitive and capture the big structures of global structures. And to handle this kind of problem, yeah, definitely we need some kind of structural procedure. Yeah, because deep networks cannot, because the operations are very regular and these kind of things are very detailed things. So yeah, maybe if we know that this kind of objects will be there, like small thin lines, or then we can kind of use it as domain knowledge kind of thing and impose a very restrictive optimization problem on top. I don't think in general we can do it with a deep.
Okay.
So, yeah.
Right. I don't have anything else.
Thank you, Ishant. Are there any more questions? If no more questions, again, we thank Ishan for a wonderful presentation.
Thank you.
Congratulations again.
Thank you, everyone.
So over to Parag.
So we are at the end of the session. I will just hand it over to Chetan now for the closing.
Before you hand it over to Chetan, so at the outset, I would like to thank all the doctoral committee chaired by Professor Rajgopalan for reviewing all the doctoral proposals and then arriving at a award winner. So I thank all the the doctoral committee members as well.
Thank you, Uma, for chairing the session first and for coordinating the awards process. Yeah.
Thank you.
Over to Chetan.
Yeah, thank you. So we have reached the last session of the conference, which is the closing ceremony. Can I share my screen? Let's see. Is the screen visible?
Yes, Chetan.
How do I make it a full screen? Sorry.
Maybe on slideshow. That button that says slideshow beside share.
So there is share here.
No, on the right hand
On
top.
the top right.
Top right.
No. Okay, so I see.
Slideshow.
Okay, thank you. And thanks everyone for bearing with us so far, listening to such a nice presentation. So we are on the last session of this. So before we go further, I would like to announce the Best Paper Awards for the ICVGIP 2021. The review or the shortlisting process was as follows. So we shortlisted a few papers on the basis of the reviewers. So the paper with the best reviews. And we suggested those papers to an independent committee which discussed the papers, their reviews, as well as attending to their presentation. And based upon that, shortlisted two papers, the best paper and the best paper runners-up award. And the award announcement is, so the best paper winner is paper ID 185, realistic talking face animation with speech-induced head motion. And the authors are Sandika Biswas, Sanjana Sinha, Dipanjan Das, Rajeshwar Bhomik, all from TCS. Congratulations to all the authors and a big applause for all of them. The best paper runners-up is paper ID 82, and the title is GPU-based centroidal Voronoi tessellation using local search on the thinnest digital surface. And the authors are Ashutosh Soni, IIT Kharagpur, Piyush Kanti, Techno India University, Kolkata, Partha Bhomik from IIT Kharagpur. Congratulations to the authors. Good job. Now, the other formalities, the acknowledgements, first of all. So we thank all our speakers, the plenary speaker, Olga, Babatosh, Christine, Jonathan. We would also like to thank the speakers in the workshop, the invited talks in the workshops, Vijay Chandru, Arnab Bhavsar, Ganesh Ramakrishnan, Louis Gomez, Manohar Paluri, Ajit Gupte, and Vijay John. And last but not the least, we thank our sponsors and who spoke about their companies, their work, Pavan Baheti, Lokesh Bodegada, and Jayavardhana Gubi. Thank you, all of speakers. Next, I would like to thank our authors and the speakers for the oral papers, for the poster, and the participant in our doctoral symposium, Sini Mohammad, Riddhi, Parimala, Praveen, Ankit, Prasan, Puneet, Firoz, Prerna, Jisha, Sai Sagar, Arpan, Daksh, and Anirban. Thanks to all of them. Thanks to all the authors. Thanks to participants for the doctoral symposium. Next, I would like to thank our speaker. We just had a talk from the Ishan. Thank you, Ishan, for your wonderful talk. We would also like to thank the panelists in our Industry Academia panel on Vision for Social Good, Varun Gulshan, Angelica, Vivek, Vijay Narayan, Dipinder, and Saket. It was a wonderful panel discussion, and thanks for Dipinder and Saket for organizing it. I would also like to thank the speakers in the Vision India's session that we had today, Pranay, Kranti, Joseph, Soumya, Praveen, Pawan, and Daksh. Thank you all. And I would like to thank the team that made the ICVGIP possible, our esteemed area chairs, our reviewers, which spent a lot of time in reviewing, sifting through all the papers and brought out the best of them, brought the best paper for us to listen to. I would like to also thank all the session chairs, as well as the best paper and the dissertation awards committee. Thanks for their time and their effort in selecting the papers. I would also like to thank the ICVGIP 21 team, which made it possible. All the chairs, the demo chair, contest chair, Vision India chair, industry co-chairs, doctoral, as well as the publicity co-chairs. Also the publication, and a big thanks to our organizing team, Dr. Gaurav Harit and his team at IIT Jodhpur. A big thanks and a wonderful work done by them. Thank you. And again, last but not the least, I thank our sponsors. So we had Qualcomm and Samsung as the diamond sponsors for the ICVGIP, and the TCS Research for the platinum sponsor. Thanks to all of them for the support. And again, last but not the least, thank you everybody who participated, who listened to the talks, asked the question. Thank you so much for being an awesome audience. And thanks from all of our team. Thanks to all the audience. Subhanshu, you would like to add anything?
No, thank you. You summarized it very well. So it was wonderful experience organizing it. I wish it was in person, because it was. I've been part of ICVGIP for many years. When I was a student, I organized a tutorial. So it's a wonderful way to connect with the community, and also visit the young researchers who go on to become graduate students, professors in various places over time. So so I hope this continues, and once the pandemic is over, this would be a vibrant way to get the community together. And it's great to see this grow over time, and perhaps we'll start to make this yearly instead of every other year, if there's more enthusiasm. So thank you very much for attending. Thank you to all the speakers and co-organizers, and have a great holidays.
Thank you. Thanks, Subhanshu. And see, we have not seen Gaurav talking too much, so maybe if he's around, we allow him to close the conference formally from the organizing team.
Yeah, before Gaurav takes up, congratulations and thank you to all the program chairs. 3 cheers to all 3 of them.
Thank you.
Thank you.
Yeah, I completely agree that program chairs did a fantastic job. And we should thank all of them for having a fantastic ICVGIP.
Thank you.
Yeah, over to Gaurav now.
Yeah, and thanks to all, and we would like to thank our wonderful colleagues who have helped so much with all the last minute requirements, and they have shouldered many of the responsibilities absolutely in an independent way. So our colleagues like Anand, Rajendra, Raj Lakshmi, and Yashasvi, and Himanshu. So all of them, thanks a lot, and thanks to our technical support who have been working so hard for the last 3 days and getting up in the morning, reaching here by 6:37 and staying up till late. So thanks a lot to Akash and our admin support, Deepak and Vikram.
So you have been muted, Gaurav, for some reason. Okay. We have you back.
Hello. Is it that Dr. Gaurav was not audible?
No, just the last few words, I think it got muted for some.
He was expressing his thanks to all the technical support he got from various office bearers. I'm adding those lines, the last ones that he spoke. And actually, it's all because of efforts by the program chairs in particular. The event became really successful. Thank you so much for being so efficient and managing things in timely manner. Thank you.
Yeah, I would.
Yeah, Parag.
Yeah, thank you once again. And I would like to invite Professor Chaudhary to come and deliver the closing remarks and formally close the conference.
Okay. Final remarks, final comments of closure of ICVGIP 2021. And I'm closing this conference with an invitation to all of you to join us for ICVGIP 2022 at Gandhinagar, at IIT Gandhinagar. And that will be possibly the first edition of annual ICVGIP. And we hope to also meet you in between when there will be NCB Pripchi somewhere during the summer months, possibly at a cooler location. So all the best to all of you, and let's have this kind of a vibrant spirit of ICVGIP continue for years in future. Thank you.
Thank you.
Thank you.
I think we should all give an applause for ourselves.
Thanks to everyone. Thanks to Professor Chaudhary.
Yeah.
And see you all in Gandhinagar now, hopefully physically.
Yes.
Yeah, we should see in person, and then actually that is altogether different experience than the digital image.
Yeah, it was good initially to stay at home meetings, but now it's getting a little too much. Okay. Bye-bye. Bye.
Bye-bye. Yeah.
Everyone.
Bye, Shubhranshu.
Bye.